think the recording is started. Okay, welcome everyone. Thank you very much, for coming to today's AIAA Los Angeles Las Vegas section mini conference, New Space mini conference 2021. We have very exciting topics and speakers, so you will enjoy this event tremendously. So before we start the program, just a few words for logistics. First, we thank AIAA headquarters for providing us this great Zoom platform. It's a really great opportunity for us to keep doing, great events for everyone in this pandemic. And this event, I think most of the session will be recorded and it will be posted after the event, and we'll send a notice to everyone. And the thing is, if we have some internet instability issue and somehow it got disconnected, please keep trying to reconnect. It should be resolved right away. The other thing is, if your bandwidth, internet bandwidth is limited, you can try to use the, telephone dial-in. Then this way you might still have very good quality. And please try to sign in Zoom with your real name so you can be identified. And please type your question in the Q&A. For the first and second presentation, we prefer you to wait till the end of the presentation. So you have the chance to raise hand and speak out interactively with the speaker. But you're welcome to type your question in Q&A, and the speaker will, most likely wait till the end to answer your question, but we can see. And during the event, please don't mention, any sensitive information, personal, private issues, because Zoom is getting more and more secure, but still, if you working on some sensitive project or anything, and if you don't want to download your Zoom app for security reason, you can use the web Zoom on the web or just dial in. Just a few words about Southern California. We are very lucky to be in this area. We have many exciting aerospace activities and the individuals. So this is just a few examples, and we just heard this recent very exciting Mars helicopter, Ingenuity, and the Perseverance, and the SpaceX, Virgin Galactic, and many defense companies and space project. Well, membership is very important part for AIAA, but I don't go into further detail. So basically, we have quite several events to keep everybody moving, get interested, get inspired, and stay connected during the pandemic. So the first presentation, we welcome our distinguished speaker, Dr. Daniel Raymer. He's our AIAA fellow, and he's our keynote speaker today. He's the president of Conceptual Research Corp. He has a very famous bestseller book, textbook. Everybody love it, along with other very exciting publication. Then we have Mr. Jaspreet Singh. He's a lead designer from India. He got a master in design from India Institute of Science and a bachelor in mechanical engineering from BTU. Then we have another speaker, Mr. Aviv Levy from Israel. He's the president of Aviv Innovations. Then we have Mr. João Marcos de Souza. As a graduate student from University of São Paulo, Brazil, is Department of Aeronautical Engineering. So let's welcome all the speakers. And so Dan, is yours.
Okay, let me steal the screen. And that should be this one. And put it full screen, just one moment. Okay, there it is. Well, good morning, everyone. If you're in the Los Angeles, Las Vegas area, it's morning here. It's different times other places, and I appreciate people on the other side of the world. I hope none of you are in the middle of the night there, but thank you so much for joining us. I'm Daniel Raymer. And I've been asked to give this talk, and it's actually a continuation of a talk that I gave a year ago at this conference. A year ago, I was invited to give a presentation subject of my own choosing, and at first I was going to pull out one of my old sets of view graphs. I've got dozens, probably hundreds of talks that I've given through the years. Many of them are on space-related projects that I've been involved in, so I thought I'd pull one of those out. And then I just thought, oh, come on, even I'm getting bored with my old projects. And so I decided with about 10 days before that I would design something completely new and present that. And it just popped into my head that what the world really needs, not this world, but Mars world, what Mars really needs is a manned airplane. Because if Elon Musk gets us all over there sometime in the future, well, as soon as you have 2 bases, you have to get between them, plus the fact that we need to fly around for exploration. We don't want to have little rollers and rovers, little cars to go around in. That's going to take forever. So I thought what they really need is an airplane, because I like airplanes. So it just sort of popped into my head, and I started doing some back of the envelope calculations, actually a spreadsheet, of course, and it looked sort of kind of possible. So I fired up my RDS aircraft design software and came up with a design, and I gave a presentation a year ago, and it actually looks like it would work. As a part of that presentation and one more presentation I gave later, I got volunteers, people saying, wow, that looks like cool, can I help? And I wound up with a team all over the world of people working for free. And here are some of the names in the blue box to the right are the ones who aren't here today. And then, of course, you see on the main screen myself and 3 others who will present today. So we're all volunteers, but some very substantial work has been done. We've had structural finite element analysis, computational fluid dynamics, propulsion analysis, quite a lot of work on the crew integration. So it's kind of moving forward. And of course, my hope is that at some point, somebody, maybe NASA or maybe some crazy rich person that wants to show Elon Musk that they can do something even crazier, might decide to start funding this. But in the meantime, it's a volunteer effort. As a volunteer, I did not try to run a tight ship. I didn't pass out exact assignments and tell everybody exactly what to do. That's no fun. They're volunteers. So I basically kind of threw it open and said, here's my design. I'll give you all the design information. I'll give you IGES files. I'll give you all the calculations done so far. And you're a volunteer. Do what you think is fun. And it turned out we got a pretty good mixture of people doing good things, including some of those technical things I mentioned. Those are reported in detail in an AIAA paper I gave at SciTech. And if you want to see that technical paper, go to my website, aircraftdesign.com, and you can download it for free, or you can go to the AIAA website, and I think they make you pay for it. So the choice is yours. But anyway, at aircraftdesign.com on the main page, there's a link towards the bottom that has all this stuff. It has my paper, and it has all the technical reports of all the volunteers who have helped on it. So feel free to have a look at that. For today's presentation, I'll give a brief overview, and then we had time for 3 volunteers. We actually had more than 3, but the first 3 got the slots. So next time we'll let some others come in. And they will go through the particular material that they did, performance calculations by Joabi from Brazil. And then Jaspreet Singh did some cabin layout and human factors work, including some calculations of the structure. And Aviv Levy did more interior design work and some renderings. And you'll notice that we are not tightly coordinated. In fact, there's substantial overlap and there's differing ideas. You'll see 2 and actually 3 different suggestions for what the interior could look like. I love them all. They're great, and I'm so happy to see this work, and we have a long time until somebody has to down select. So we'll let everybody run open loop. Great work is being done, and I think you'll see some very creative work later in the presentation. So that's what we're going to do. Let me just jump right into a top-level overview, somewhat repetitive if you saw it a year ago, although there's been a lot of work done since then. You'll notice on the front slide here that I asked Robert Zubrin, who I've known for 35 years, to write a haiku for this project. And his initial response was, "You got to be kidding me, Raymer." And I said, no, you're the perfect guy. So he never wrote a haiku before, and he went off and wrote us a very nice haiku. Zubrin is running a conference later this year, I think September or October, on Mars. He's done a lot of these conferences. And I have submitted this as a possible presentation at his conference. So we'll be able to have a further update then. I'm pretty sure he's going to accept it. He might reject it, you never know, but I think he'll accept it. And I'll go ahead and give another presentation of this. I don't recall the date offhand, but it's easy to look up. Mars Conference, Robert Zubrin. I'm sure you'll find it. Okay, for the first slide, I actually just kind of want to show some eye candy, and you'll see a lot of eye candy later by the people here who are here today. But one of the fellows, Jean-Francois Clavrel, sorry, I'm sure I mispronounced it. He's done a lot of eye candy renderings, and I just thought you might like to see it. So this is his vision of this thing after having landed somewhere on Mars, and people get out. And there's a flag showing the different entities assumed to be contributing to this project, including the Raymer Manned Mars Plane Company, which he assumes will be in existence by then. I have my doubts. And it seems that our two aviators, Marsiators, whatever you call it, it seems they've gone out to visit the site of the recent landing, and there's the little helicopter there. Not sure why they did that. And also, I have no idea what the astronaut in the back is holding in his hand. It's kind of a running joke. We all have our guesses. I'm guessing it's an artifact from an ancient Martian civilization. Maybe it's a wormhole portal or a toilet seat. I'm not sure what it is. In any case, I get a kick out of his renderings. They're pretty cool. Okay, project started basically, as I said, with just the broad general idea. We'd like an airplane on Mars. Okay, what are the requirements? You always need requirements to start a design project. So what's it going to be? Well, no customer, no requirements set by anybody else. So I did what I always do. I made them up. And I made up the requirements by just thinking about what kind of vehicles in the past have been successful, and what could you say is more successful in this category than the World War II Jeep. The basic Jeep was designed before the war to carry 200 people or 500 pounds. So I use that as kind of the point of departure. And you want lots of range. So the Jeep had 260 nautical mile range. Let's have at least that. We wound up with a lot more than that. Of course, the Jeep doesn't normally fly, but if you hit a bump hard enough, you can do what this fellow's doing. So that was my basic idea then. Let's just have a vehicle that'll do what a Jeep does, carry a couple of people. Now, one slight difference is that we want the ability to fly unmanned. And today that's an easy thing. Back in the time of the Jeep, that would have been impossible, but today it's a pretty easy thing. So you can have two people fly it, and whatever their weight is, whatever weight's left over, maybe another 100, 150 pounds for payload, or you can shove stuff into it and push a button and it flies itself somewhere. So I think that would be a very useful capability. And that's really what we do a lot of times in advanced design. We just sort of imagine a useful capability for some future customer. So that's kind of where the whole thing started. I am assuming that this thing is already on Mars. Somebody else gets it there or gets major components there and assembles the rest in place. It's somebody else's problem. To go back to Hitchhiker's Guide to the Galaxy terminology. So it's all covered by somebody else's problem. And it's also somebody else's problem to set up bases there. And these bases are assumed to have lots of electrical energy available. So we can easily charge up batteries and we can easily crack out propellants and do all these other things. So we don't have to send that with the vehicle. We don't have to somehow get it there. We don't have to fold this vehicle up to get it to Mars. It'll be fabricated in place from some wise mixture of components built locally. I'm assuming by then they'll probably have large 3D printers and things like that. So some components locally, some components shipped from the Earth. So that's the basic ground rule. And with all that in mind, I did some vehicle design. I'll show you how it looks like in the end, and then I'll get to the details. So here we come in for the landing. You'll notice we have large propellers and a wing for forward flight. But when you get near the ground and want to land, I went through lots of thought and calculations, and I just don't see the possibility of making any kind of a rolling landing until they build runways, and that'll be quite a bit in the future. So instead, we're going to fire up some rocket motors. So we're using rocket motors for takeoff and landing, and also probably for acceleration to flight speed, and large propellers with electric motors and battery power for normal flight. When we take off, we fire up the rockets, go vertical for a short distance, and then start accelerating into forward flight. So that's the basic idea. There's other ways of doing this. I didn't look at any of them. This is a volunteer thing. I did not go through the typical system engineering trade studies that you would if it was a funded project. I just made a guess. I think I'm right, but everybody thinks they're right at the beginning. And some good calculations might show a better way of doing it. Maybe a giant helicopter, except I do want fast travel. I want to move quickly. I want a high cruise speed. Kind of hard to do that with a helicopter, and tip speeds on Mars are going to be a problem. The speed of sound is lower on Mars, so it's even worse than a normal helicopter. There may also be a better answer with just some kind of a rocket jump buggy sort of a thing. Maybe you just have a lot of propellant and you simply use rocket power, blast off vertically, go into a parabolic trajectory, 0G, and then make a landing on rocket thrust. I don't know. I didn't do all those studies, but this is the one I did, and I think it works. Okay, so it's optionally manned. The crew does not have to be good pilots. They are not really flying it. They're giving instructions to the autopilot, and we'll come up with some set of commands, probably some kind of a joystick controller, and later you'll see some nice designs for that. And they will use the joystick controller and maybe a keypad, maybe a virtual keypad. Maybe they'll talk, maybe they'll just think at the computer. But somehow they will say, okay, I want to turn right. Okay, let's go up to 600 feet. Okay, let's cruise at max speed. Oh, let's land at that thing down there. Okay, that's what the crew will do. They won't actually be stick and rudder pilots. You'll also be able to simply pre-program it and tell it, go here. And in that time, we'll have sensors, we'll have enough smarts to be able to figure out if the ground is safe in real time, all that sort of thing. Sizing calculations assumed that you would pre-store the electricity. You'd charge up batteries enough, and you would put on board enough rocket propellant for 2 complete cycles. In other words, you take off, you fly somewhere, you land, you take off again, you fly back, and you land again. What if you need more? Well, then somebody has to come get you. You can't allow for infinite capability. So at this point, that's the design. Somebody later may say, oh, we need more capability, and you can sure do that. It just gets bigger, more costly, and more problems. So that's my assumption. Later, we should do more trade studies. So this is the design I came up with. Came up with it pretty quick, but I think it's a good one. I was surprised at how well it turned out, actually. It starts out with what looks like an autoclave. The crew compartment is pressurized. And I'm assuming that they're wearing Mars suits, which are space suits, but they aren't the big, bulky, air-filled ones. Instead, I'm assuming that they perfect the technology of a skin-tight, elastic-type spacesuit that literally presses on your skin rather than using air pressure. So that's why the guys in the artistic rendering didn't look like they were wearing spacesuits. They're wearing these skin-tight suits. There's still a helmet and a connection from the neck. How does that all work? I don't know. Somebody else's problem, but I know there's people looking at it. So our people are in the pressurized compartment there, and they can take their helmets off. But basically, they'll keep the suits on the time, and if they need it, they'll pop the helmets back on. The front of the pressurized compartment opens just like an autoclave, and it is a complete transparency that opens like an autoclave. So you have a good vision forward, and then I gave them a couple of little windows on the side. Certainly, there are other ways to do this. There could be lots of trade studies, but I thought this might be a good way of doing it. Certainly, we know how to design autoclaves, and we know how to make them very, very structurally efficient. You'll notice that the wing is up high because we need ground clearance because we don't have nice, clean landing places on Mars. So you need lots of ground clearance. And you'll also note that I did not provide a vertical strut going directly down to the cabin, and there's a method to that madness. The reason for that is if there ever is a hard landing, I don't want the wing to press a strut into the pressurized compartment there. So if you look at it, if there is a hard landing in a vertical direction, basically the wing will break off and those struts will go down, but won't disturb the pressure vessel. So it's a safety aspect. I don't know if it's a good idea. I don't know how bad the weight penalty is, but that's what I was thinking at least. I realize that mass is far more critical than weight on Mars. So the weight of carrying the thing upwards isn't nearly as important as the inertia mass effects. If you have a bad landing, all that mass of the wing and the rocket motors and the electric motors, everything, batteries, everything is above the crew pod. So I definitely did not want that to push down and crash into the crew pod. Okay, there are 4 electric motors. There are 2 in a tractor configuration outboard. And those are in little nacelles that extend to the rear and hold the tails. Originally, I was hoping to get away with only vertical tails, make it basically a flying wing in the pitch axis. But it turns out we had some airfoils designed. One of the volunteers designed up some nice airfoils. And the good airfoils have rather large pitching moments. So given that they're rather large pitching moments, then we need a horizontal tail for trims. So later versions have a horizontal tail added to those nacelles. Modern nacelles and basically pods. You'll notice that the inboard nacelles have propellers in the pusher configuration, and that's primarily to keep them away from the passenger pod. I don't want blades going through the passenger pod. So that's where they are. And also those nacelles give a good location for the rockets. So you'll see in there are 8 small rocket motors. And Jim French, who many of you know, he's a co-author of the AIAA rocket design book. He designed up these rockets, and he's been looking for many years at rockets that use propellants that can be cracked out of the Martian atmosphere. So these are carbon monoxide and LOX rocket motors. And that's rather an easy chemistry to crack those out of the atmosphere. In fact, it's easy enough that he thinks that we can put the equipment inside the flying vehicle at a reasonable weight penalty. And I said, great. And once that's proven, we'll do it. But I didn't put it in the baseline. So the baseline assumes that you actually have enough rocket propellant and electrical power on board to do the entire mission out and back. Same thing with solar cells. I've actually assumed a weight for solar cells, but I didn't take credit for those in the cruise performance. I wanted to make sure that we're proven that this thing works and not relying on technologies that may or may not be readily available. Especially if we can't make solar cells on Mars, then they all have to be shipped from Earth, and that would be perhaps difficult. But if it becomes easy, if we think we can do it, great. I've got the weight penalty for solar cells into this. Okay, so anyway, that's the basic design. You'll notice it lands vertically, so it has helicopter-like skids. There are also a couple of skids outboard that hold the wings in place when you land, so you don't tip sideways. Okay, I think that's enough about the basic design. You'll see a lot more about it. You can see the weights there. It's a 6,000-pound weight. That's the Earth weight. We should show it as mass, but if you say how many slugs you have, nobody knows what that means, including me. 500-pound total payload. You see the length, not bad. The width, 345 feet. So this is an extreme wingspan vehicle. So of course, structure is very important. We did get some structural analysis done. We're not going to show that here, but it is in the papers that I mentioned before. All right, well, I went through a bunch of spreadsheet-like calculations to see what we could potentially get out of this with a bunch of ratio inputs for things like battery efficiencies, densities, propeller efficiencies, and things like that. And it looks like actually we should be able to get out to something like 1,000 nautical miles radius, out 1,000 and back 1,000. Now that's probably optimistic, but if we get half that, that's still very useful and more than the goal. So it starts to look kind of interesting. Did a bunch of calculations on rate of climb, and that wound up sizing the motor power required. Very boring stuff to see, but at least be aware that we did do this kind of stuff. And it looks like it exceeds the stated requirements, even if a lot of things don't go our way in the boat. So we did do some CFD analysis. Here's some of the work done by Mr. Felix Finger, and he's now Dr. Felix Finger, just got his doctorate degree. And so we've lost him to industry. He took a real good job. In any case, he did do the airfoil design, and he also did computational fluid dynamics on this. I won't go through the details, but the lift to drag ratios weren't as good as we had hoped. Okay, so that takes away a little bit of our range. Like I said, probably various things will nibble away at the range, but it looks like there's still more than enough margin. Let's see, this is some of the airfoil design work that he did. And some of those airfoils are not airfoils that you could reasonably use, very thin back ends you can see, but you can see what the computer program is trying to do. It's trying to extensively aft-load the back of the airfoil to get good efficiency in that thin Martian atmosphere. And that's what led us to require a horizontal tail because of the pitching moments. Let's see, I think I've got the chart. Okay, so this is the one that was chosen to move forward. So that is the one currently on the design. We also had structural analysis. This was done using, I forget, sorry, I forget which computer program he used, one of the major FEM programs. In any case, done in a fair amount of detail, including flexibility analysis. Yes, that long wing is very flexible, but that was included in the analysis and included in the sizing criteria. Jaspreet is going to talk about this in more detail, so I won't go into it, but he did sizing of the cabin pod itself using basically classical equations. This is all handbook stuff, the stresses of a pressurized vessel. He'll talk about that later. We also had some stability analysis done. This stuff is all described in detail, both in my paper and also in the volunteers' own reports. They all wrote reports on what they did. So look at different options for tails, and finally wound up going with the one in the middle, where basically we just add a horizontal to the end of those nacelle booms. And went through the stability analysis, all pretty straightforward stuff, and showed that we can make this stable to the level that we want. And of course, we don't want it real stable. We want it pretty close to neutrally stable because we don't want BPM drag penalties. And of course, it'll be a completely computerized flight control system, so we can make it any level of stability that we want. We just have to put the CG in the right place. Okay, directional stability also looked good, surprising with that huge wingspan. We will mechanize, in addition to the rudders, we're also going to use differential thrust from the electric motors on the two sides to help control it in yaw, and we'll use yaw to help roll. In fact, currently we don't have elevators. We'll get some roll authority out of differential motion of the horizontal tails, although we have to be careful because of flexibility effects. But we'll get a lot of our roll authority by basically skidding it a little bit, by yawing it slightly. And with this wingspan and some dihedral, we'll get all the roll authority we need. Eventually, that'll probably set. Oops, wrong button. Eventually, that'll probably set the required dihedral, maybe outboard panel dihedral as well. Okay, it's not advancing. Hang on a second. Okay, there we go. Matthias Manjan, who is not with us today, did some performance analysis, including doing a dynamic simulation of the actual vertical takeoff, acceleration, and climb to cruise altitude, and it all works, and it matches the preliminary numbers for the amount of electrical energy and rocket propulsion expended. So that's looking good. Again, I'll refer you to the paper, but here's some of his spreadsheet results. And then we've got more details on the cockpit, and Jaspreet is going to go over this, showing how he laid out the cockpit and then come up with some alternatives, including that staggered seating, which is potentially a very good idea for this application. So still a lot of options out there. We're not saying we have the final solution on any of these things. You'll see that more later. Aviv will talk more about some of his cockpit work. So again, I will skip past that and let him do it properly. This is the second version of the design that we came up with in my RDS software. And as you can see, we've added these small horizontal tails. Otherwise, it's pretty much the same geometry with the new airfoils, as mentioned earlier, and the horizontal tails. And you'll notice the wingtips are tipped upward and raked back a little bit. And that's to give more roll authority with yaw. I don't want to put giant ailerons on this thing because the structural impact of that, it'll just twist it like crazy. We'll have to add a whole lot of weight, so we're going to avoid that. Okay, more images from Aviv. He'll go over more in detail. So in summary, it looks like it works. You know, it's crazy, but it looks like it would work. Pretty straightforward calculations. I didn't assume any giant magic. Just sort of high-end application of technologies that are out there now or in development, and I think it would work. Whether it's useful enough to be necessary, well, eventually it will be. Maybe it's in 2040, or maybe it's in 2240. But at some point in the future, there's going to be enough people living there, and they'll need a way to get around. So that's my basic presentation. And with that, I will switch now. Joabi will take over. So,
okay.
All yours.
Hello to all. I'm Joabi Marcos. I'm a master's student at University of São Paulo, and I work as a performance and flight science engineer at Embraer. First of all, it's a great honor to be participant of this conference, present some results of what can be the first manned plane to fly on Mars. Well, Next slide. Okay. The first step was to model Mars' atmosphere in function of height. Even knowing that our mission is to fly near the surface, like a Earth sea level. At this condition, near the surface, the temperature is about minus 31 degrees Celsius, and the pressure is about 145 times lower than the Earth, and the density is about 8 times lower. As a consequence, the lift and drag forces are lower than in Earth, and because of the lower gravity, the weight is also lower. Other consequence is that a conventional engine or a gas turbine may suffer to operate on these conditions. The good news is that we are using electrical motors, and and then its efficiency is not so dependent of the air density. Okay, next slide. Well, so the first approach was to evaluate how much power is required to satisfy some basic constraints. In function of the wing area, uh, in this constraints analysis, it was considered a constant propeller efficiency of 80% and an overestimated value as we saw later. Also, other considerations were done in order to meet the requirements, like the power needed to get a cruise speed of 150 knots, a rate of climb of 1,500 feet per minute, and a 30-degree sustained turn at the cruise speed. This study showed that a total power higher than 160 horsepower is necessary to comply with the mission requirements. Also, the propeller efficiency should be better estimated. Next. Well, then, using momentum theory, it was built a propeller efficiency map. The current design has 4 electrical motors with 125 horsepower each, totalizing 500 horsepower. For this configuration, this analysis showed us that the propeller efficiency is much lower than we thought that would be. It's about a value about 5% and 50% and 55%. We were considering 8%, so it's much lower. Next. Well, before the performance analysis, it was estimated a drag polar for a trimmed condition. As we can see, the minimum drag is about 160 drag counts, and the total drag for cruise condition is about 250 drag counts. Other interesting, next slide. Here is the, yes. Other interesting graph is the lift drag ratio in function of the lift coefficient. As can be seen, the efficiency presented is very high, and the main reason is the aspect rate of the wing, a value about 57. Next. Okay. So with the propulsion and aerodynamic modeled, it was performed a cruise analysis where it can be seen that in the first design, the airplane has an expressive excess power. For this study, it was considered a ratio between the battery weight and takeoff weight of 13%, a battery specific energy of 500 watt-hours per kilogram, a 90% of efficiency from battery to motor shaft, and also a 3% losses due to the installations. Next. For these same considerations, it was verified that the best speed for range is cruising around 150 knots, as previewed in the first analysis. And for this condition, the range is higher than 1,200 kilometers. Next. Next, please. Okay. And well, can you come back on another side? I don't. I don't know if, yes, this one. And finally, for climbing, it was verified that the aircraft is capable to maintain a rate of climb of at least 3,000 feet per minute and in a great range of velocity. Okay, next. Here are some opportunities that were identified. The first is the reduction of the total power from 500 horsepower to 200 horsepower in order to meet the emission requirements, avoid oversizing. The second is the usage of lithium sulfur batteries with specific energy equal to 700 watt-hours per kilogram. This is considering a time frame of the next 15 years. Also, it was identified that it's good to reduce the wingspan to avoid structural issues. So we could reduce the wingspans until the maximum lift drag ratios reaches a value about 30. But it has to be considered the wing area because we have solar panels in all of the surface. And finally, we can consider using a distributed propulsion strategy to increase the maximum lift coefficient. So and this will help us to avoid structural issues, reduction the wingspan too. Here are some references. The first one is the NASA to model, was the NASA website to model the Mars atmosphere. The other ones is about the distributed propulsion. Okay.
Okay, Robbie, thank you very much. That was excellent. And let's see, we'll move along to, do I have 2 copies of your slides?
Okay.
This is you again, right? Yeah. Oh, somehow I have 2 copies of the slides. Well, sorry, let me run ahead to the next presentation. Okay, Jaspreet, over to you. Thank you. Just say next when you want the next slide.
Sure. Thank you, Dr. Raymond, for this cool opportunity. And a big shout out to everyone who's watching. So I'll be taking you through the sizing and architecture of the crew cabin. Next slide, please. So we'll cover a discussion on prior art and how and why it is important on this kind of a project. Subsequently, we'll discuss the pressurized cabin as an approach on how one might design it. We'll move into weight estimation, a discussion on human factors, and how all this comes together to create the fuselage pod. And I'm saving the best for the last. We'll discuss cabin architecture, interior layout, and systems layout. Next slide, please. So, well, at the onset, we realized that there weren't any systems which we could compare one-to-one for what we had set out to do, as in design a crewed-powered aircraft for Mars. So we looked at early crewed spacecraft to get a fair idea of what kind of pressurized volumes worked in the past. And we looked at Mercury, Gemini, and Soyuz because respectively, they housed 1, 2, and 3 occupants. And we sort of got a fair idea of what the trend for pressurized volumes might look like, and gave us an indication of what the right ballparks could be. The figure on the right shows a variation of the nominal free and pressurized volume per passenger, as in specific volume, as a function of the number of seats abreast. So free volume is generally defined as the volume that would allow free mobility of the occupant within the pressurized cabin. And pressurized volume here represents the gross pressurized volume inside the cabin, so to speak of. So we also notice here the 2 bookends shown by the fighter aircraft, which have a very tight space packaging requirement, and business jets, which give a lot of prominence to comfort. So with this in mind, we move forward to the next slide, wherein we see, pardon me, On this slide, on the right, we see a variation of the pressurized volume as a function of the volume parameter, LD square. So it is interesting to note that because spacecraft typically have a very intense mass constraint, it's acceptable to optimize, to estimate internal pressurized cabin volumes with respect to their external dimensions, because the wall thicknesses are expected to be quite less. So the top figure shows a trend line for various spacecraft along this idea, and the bottom one shows how the pressurized volume varies with respect to the number of crew members. So one thing to note here is that typically for spacecraft, a nominal value of about 1 to 1.5 cubic meters is the free volume that is necessary to give astronaut or the occupant enough room to maneuver and feel comfortable as well. We'll keep this figure in mind as we go forward. Next slide, please. So we also, apart from spacecraft, we also looked at comparable systems like very high altitude gliders. For example, the Airbus Berlin 2, which is designed to soar at 90,000 feet. For obvious reasons, this was interesting because this is designed to operate in rarefied atmosphere, very thin atmosphere, with the density of atmosphere expected to be very low, like Mars. It's a two occupant aircraft and has an empty weight about 680 kgs. And one interesting thing to note was that for their maximum operational altitude of 90,000 feet, they were targeting a pressure altitude of about 15,000 feet, which meant an internal cabin pressure of about 6.5 to 7.5 pounds per square inch. So this also provided a good ballpark to kind of keep in mind as we started the design of the pressurized cabin. Next slide, please. So with the former in the background and noting that Mars's atmosphere is about 0.88 psi, less than 1% of Earth's value, we looked at various pressure altitude for trading what kind of cabin operating pressures we would like to have, because these eventually have a bearing on the overall mass properties of the cabin. So on the right, you will see an idea of the cabin, how it developed. So basically, it's imagined in three parts for the ease of analysis. A hemisphere, a cylindrical, and isotensile end. In fact, if you would imagine the side elevation as a complete cylinder with flat ends, we would come to know that the internal volume is about 4 cubic meters, which gives a specific volume for two occupants of about 2 cubic meters. And since we remember the prescribed value of such figures for the spacecraft was about 1.5 meter cube. So this puts us in the right ballpark and became the sort of right estimate to start designing the cabin. The shell weight and thickness for each hemisphere, each part was computed, and then highest values obtained were used to compute the overall shell weight. Next slide, please. So I won't go through I won't read all these relations here, but suffice to say that these kind of relate the thickness of the shell structure with the operating pressure that we are designing for. So, we also kind of looked at a maximum design pressure of 14.7 psi, which is the equivalent of Earth's surface atmospheric pressure, and found that it was able to withstand a high bursting pressure. So you see that all the three segments of the shell structure are kind of sized according to the relations shown as per the reference indicated. Next slide, please. So this slide shows some of the calculations done on Excel. We programmed in Excel and ran a couple of trades to come up with the final value of about 390 pounds or about 176 kilogram, noted on the right-hand corner bottom, for a thickness of about 25 mm for the shell. Next slide, please. So in this, we go into more detail to show how different shell segments were considered for different materials. For example, the front needed to have transparency, and we sized it using appropriate plexiglass material. The central part and the latter half is sized with high performance carbon composite structure with titanium alloy imagined to accommodate for certain structural hard points. And of course, a foam insulation is also considered in order to work out the thickness for the shell, to give a total shell weight of about 390 pounds, as noted earlier. Next slide, please. Yes, so here we see how these sort of cabin architecture begins to form. So we have two occupants, and we sized it for the 95th percentile male with heavy clothing. We were keen to provide, because they're not meant to be or expected to be seasoned pilots, and certainly we're not designing a fighter plane. We wanted to give enough room for comfort as well as easy mobility within the cabin. Also, the earlier figures noted of about 1.5 meter cube free volume versus the final pressurized volume of about specific pressurized volume of about 1.65 meter cube. We noted that there wasn't, we would need to architect it in a way that there was a lot of free space around each occupant, and hence a staggered configuration was suggested so that both occupants can have enough movement envelope around them. On the bottom figure near the hip area, you would notice two datum symbols. These are what we call edge points or hip points, and are basically driving design points for positioning both the occupant and concomitant hardware or other structural hard points around the occupant within the cabin. And this is how we came up with this upright seating position for the considered VTOL operations for this aircraft, so as to give very good visibility all around, especially from the front and sides, for both the occupants. Next slide, please. So over here, I will sort of walk you through a visual representation of how the cabin architecture came about. It's actually an iterative process, but here, for the sake of simplicity, it's presented in a linearized manner. One click, please. Next slide. Next slide, please. So here, so earlier you saw the shell structure imagined as the from the carbon composite structure, and over here we begin to sort of imagine a floor and place it as per calculations. The aft part of the floor is shown in transparency, and you see the two bulkheads at the front and one at the rear, and also some internal structure within the cabin to house control hardware and armrest positions for the occupants. Next slide, please. So over here, as you can see, we've got the idea of the windows worked out and how the overall fuselage is tapering at the back becomes evident. Next slide, please. The positioning of the seats. There was this idea that perhaps the seats themselves could be shell structures, much like the cabin itself, to be lightweight seats. And over here, they're represented notionally. Next slide, please. So now we begin to see towards the aft part of the cabin, which is basically outside the pressurized hull, cabin, aft part of the fuselage, where one could perhaps imagine external hatches to place samples or some other payloads. And on the inside, you see a projected flight navigation information display. And an idea of what it could look like with autopilot and return to base being quite readily accessible to the occupants. The next slide, please. So this is how the overall cabin architecture looks like with the pressurized bulkheads and shows the architecture in a full cutaway mode. Next slide, please. So, yeah, I think we missed a slide. Next one. Next one. One more. Yeah. So we wanted to show how basically the ideas around this concept developed. We wanted to give an all-round information display to the occupants, to the crew, and also realize what kind of spaces we had to design, as you see on the top elevation on the right top corner, and how perhaps the space beneath the floor can be used to house samples that are collected on various trips by the crew. Next slide, please. Yes. So this shows one approach where, as I discussed earlier, because we wanted to have a largely free cabin internal volume for easy mobility of the crew, we have these foldable seats which are basically just metallic frames with the cushion in between, and they can fold on top of. They can fold down and give more access space to the crew. Next slide, please. Yes, and an alternative approach to cockpit interior where the insulation material or the foam material is itself fashioned in the form that it becomes a volume by itself where the seats are supposed to be, and the seats are basically and what is underneath is a hollow volume to access lockable space, and also becomes a shelf-like structure for various equipment, and shows how the autoclave concept might look like. Next slide, please. Next slide. Yes. So with the occupants, how it might look like. Of course, you will see a lot of cool creative exploration on these ideas going forward when the next speaker presents. And now I'll take you through some system layout visuals. Next slide, please. So, as mentioned, it's a pretty large span aircraft, and idea was to showcase how solar panels, wing structures could look like, could be embodied within this concept. Next slide, please. Next slide. This shows, for example, in the top figure, you can see the small astronaut figure for comparison. So it gives you an idea of the scale of the plane. And in the image on the foreground, you can see how the propulsion system is basically laid out and how it sort of feeds into various thrusters that are within the pylons next to the fuselage. Next slide, please. This shows a detail of the structure that came out of wing structure analysis discussed earlier by Dr. Raymer. And on the left, you see a detail of the rear thrusters and the tankage and the firewall commensurate to that. Next slide, please. So this is a final image showing the aircraft concept coming for a landing somewhere on Mars. And that concludes my presentation. Thank you very much for having me.
Thank you, Jaspreet. That was excellent and interesting, I think. And we'll go on to Aviv Levy. So over to you, Aviv.
Hi, hello to everyone. So I'll present today my part, which was I was responsible for the interior design and its rendering. So we will see it. Next slide, please. So some short intro about myself. My name is Aviv, and I'm an aerospace engineer. I'm running a company called Aviv Innovations, which provides R&D services, especially in the field of aviation, from ideation to production. Next slide, please. Basically, I was dealing with aviation all of my life. I was competing many years in competitions of radio control helicopters, which led me to study later on aerospace engineering at the Technion in Israel. I worked in several places in the industry. And about 2 years ago, I decided to open and establish my own brand, Aviv Innovations. And we will start now with the actual presentation. So next slide, please. So some intro about the process we'll see today. As you may know, the interior design may consist a lot of components. Each component individually requires a lot of work and process. I will focus on two main products, which is the joystick and the seats. And we will see the design process that I've been doing for them. So we will start with the requirements. We will see the sources of inspiration, the research that has been done about them in different fields, which everything eventually has to meet the requirements. We will see how it is transferred into CAD and later on to the final renderings. Next slide, please. So basically, as Daniel Vermeer mentioned before, there are different system requirements, and I think some of them is to be emphasized for the interiors. First of all, there are two occupants, which is the main cabin, and another parameter is the lightweight. It has to be really, really lightweight. So I highly prioritize this parameter. And we are aiming to 2030 technology. The way I see it is the technology that is up to date and a bit more. Next slide, please. So I've started with an inspiration board just to get the vision for RCIC things. As I mentioned before, we are aiming to the year of 2030. As I see it, probably we will use a lot of technology of additive manufacturing, which already happening today. 3D printing is mainly used in the industry, but is starting to becoming more and more popular, and not just for prototypes, but is also for functional parts. It enables us to create complex shapes that it is impossible to create it with traditional manufacturing technologies, which is something really great because it's an opportunity for us to create something new. And also, more and more exotic materials are becoming popular, and I assume that by the year of 2030, it will more materials will be available. And also, I assume that AI algorithms will be more in use in this kind of products, as we will see. Next slide, please. So the way I see it is a sort of an hybrid approach between the manual products and AI products. VR helmets and goggles are also becoming more and more popular. I think that it can be used also here in the interiors, but also it can use also the approach of sensor fusion. I mean, you can imagine to yourself that there are sensors that are distributed in the cabin, and it can receive different body movements and hand gestures and maybe vocal recognition in order to operate the system, and also maybe to flight. Maybe you can tell the aircraft, I want to go there, and then it flies there. The way I see it, it will be combined with traditional products that we know today, like joysticks and screens. And maybe the pilot has the option to choose whether he prefers to use this method or the traditional method. And also, I think it's important for redundancy reasons. Next slide, please. So I would like to focus now on the joystick. Basically, it has the same requirements that I mentioned before, but in this specific case, I would like to emphasize the lightweight and its comfort, because it's something that we hold, and it has to be comfort for the end. Next slide, please. So I started with some inspiration board to look for lightweight structures. We probably all familiar with the traditional truss structures. The structure that I'm going to present is maybe an alternative way, an alternative approach for these traditional structures. I think it's also something that becoming more and more popular, and we can see it with 3D printers technologies. And we can create different complex shapes and geometries and structures. And so I was looking for different patterns to make hollows in the geometry in order to reduce weight. So I've been looking for different patterns, especially from nature. One of them was the Voronoi pattern, which is there is an interesting story about this. Voronoi was a Russian mathematician, and there is a specific definition which I'm not going to go on to more details about this, but basically it enables us to split an area in a specific pattern. And we can see that there are many applications for it. in nature, in architecture, and engineering. In nature, we can see it like in giraffe spots. We can see it also in a turtle shell. It has the same pattern. Also, it appears in dragonfly wings. Also, the same pattern exists there. And now it's becoming also popular in different new architecture structures, like this stadium in Beijing, and in different structures for engineering products, like this one. It's a GoPro stand. You can see it here. So this one is hollowed in the pattern of Voronoi, which make it very, very light. Next slide, please. And this is the form research and the process that has been done for the actual handle for the joystick. So I was thinking about different organic shapes that it will be comfort for the end. And I was thinking that the pier was a good start to start with for this reason. So I actually took a pier, cut it, and started to explore it and to develop the actual form from it by sketching. So was the ideation sketches. Next slide, please. And also there was an anatomic research in order to make sure that it fits the hand and it's ergonomic, it's comfort, and so on. Next slide, please. And this is the summary that of this form research that has been done for it by sketching. We can see the whole process, how the shape of the pier and the anatomic study are integrated to the final ideation for the joystick. Also, there are different components like this wheel that can be adjusted and rotated for different purposes, either if it's for maneuvering or we would like to adjust it for other functions. Next slide, please. This is how it was transferred from sketches to CAD 3D model, which helped us after to make stress analysis and make sure that the design it meets the requirements. Next slide, please. Another approach that was done here is the use of generative design, which is something that I find really interesting. Generative design is a tool that uses AI algorithms like machine learning and deep learning. Actually, we tell the software what are the constraints of the geometry, which area we would like to preserve, and what are the loads. And the software offer us many configurations. The way I see it is like having a lot of talented employees which offering us different configurations. And beyond this, I think that up to date, there is no a human being that can create such complex shapes, because in each single point, it optimizes the configuration according to the requirements and the constraints. And everything was validated by stress analysis. So the way I use it, it's possible to choose a specific configuration from here and use it. But the way I use it is choosing one of them according to a specific parameters and use it as a source of inspiration. And later on, I integrated all of the aforementioned requirements that I've mentioned into a single product. So it was a sort of a iterative design, and there are a few cycles until I reached the specific configuration that meets all the requirements. And I think this is a place to say that it's a very sensitive balance how to integrate the different fields in a correct way. So everything will be meets the requirements, and every field will take the place. I mean, it's very sensitive game here. So next slide, please. And this is the final results for the joystick. And we can see it's rendered with all the materials and everything. It's lightweight. It can stand the loads. It's aesthetic. It uses all the inspirations that I showed you before. It's comfort for the end. I'm happy with the result. Next slide, please. Here are some more examples for different components that probably will be assembled in the cabin, like different switches, emergency buttons, and so on. But this is just for the reference. Next slide, please. Here should be, it's a little my mistake. It should be system requirements for the chairs. Basically, it's more or less the same as the joystick, but in the seats, the main big difference is the ability to fold, and we will see why later. Next slide, please. So more or less the same design process I've been conducted the same design process here. I started with ideation sketches. Also here, different patterns was trying to reduce weight. I was iterating it to get the optimal result in terms of this balance between the rigidity and lightweight stiffness. Also, an anatomic research was conducted in order to ensure that it's comfort and it fits the human body shape. Next slide, please. And this is the vision for how I saw the interior design. We have the seats, we have the joystick and other instruments in the middle. We have a screen and we have shelves backward, and this is why it is important for the seats to be folded, because it allows us to put the storage and take it out later on. Next slide, please. So these are the final renders for the interiors. We can see that everything that I was mentioning here is integrated in the final rendering photos. Different materials was explored until we got these final configurations. We can see that we have 2 seats. Here are the shelves. The seats are foldable. We have a place for the leg. We have the joystick, different components like the switches and emergency buttons. Next slide, please. Here is another different angles for the interiors. Also, this is the place to say that the data can be projected to the glass, like we see in the right photo. Next slide, please. And these are some of the exterior final renderings from different angles in flight. Next slide, please. Here we are seeing it from a side view. Next slide, please. Here also we can see it from different angles, and also here we're seeing that in a front view, and the interiors as well as the projected screen. Next slide, please. These are more views and also different color schemes that was also explored in the process. So that's all basically. This is the process that I've been doing for the interiors.
Okay, Aviv, thank you very much. And I love the work you did. Just excellent. And we're right on schedule, just about finished. And let me remind everybody that this was volunteer work. I think they did fantastic work. And of course, under funding, they could do even more fantastic work, and hopefully that'll happen someday. But I really appreciate all the good work that they did. If their presentations in a couple of places seemed a little bit disjointed, it was probably my fault. I think I went through and did a little bit of editing to their slide order, so maybe I confused them a little bit. Sorry about that. I thought I was going to send it to you, but I remember now I don't think I sent it to you. So my apologies if I confused you a little bit, but I think the presentations went great. And again, I'll call your attention to the website, aircraftdesign.com. And on the front page of that, towards the bottom, you can click and go to a link where you can see the reports, the detailed reports of all this work by all the different volunteers, and also slides and some other stuff. Let me close with just a little bit more eye candy. You've seen quite a bit of excellent eye candy. And like I said, they're all different because everybody was encouraged to run open loop and work on the part that they like. So one other volunteer, Jean-Francois Clavrel, did some more renderings, and they're really cool also. I love all the renderings that all the volunteers did. So here's what it would look like in flight, and I think you get an idea of the size of the thing, the span. And you can see, of course, the pod there where the people are located. And here it would be coming into land. You can see the front hemisphere, just as was shown in the earlier presentations today. Slight different variation on it. Like I said, everyone is giving it their own shot. Here it would be coming in for a landing with the rockets turned on. And the things in the front of the nacelles are actually landing lights, which is a good idea. I didn't think of that, but that's a very good idea. We're going to need it. So here it is on the ground, and there's our astronauts. This is the same scene as the picture I showed at the beginning, but from a slightly different angle. So it looks like they've landed in the middle of a really bad shag carpet. But in any case, it's a great rendering, and don't know what they're doing there. Now we have more detail, and it's not a shag carpet. It's actually the surface of Mars with a bunch of mountains in the background. So now it looks like Bakersfield, California. In any case, being a little silly there, but that's our presentation, and I thank you all for sitting in. And why don't we back up to one of these cool renderings? I think I'll back up to. I'm trying to back up. It's not backing up. Well, PowerPoint's not backing up for me. In any case, we can open it up for questions now. And we have about 15 minutes left for questions. Feel free to ask questions of myself or anybody else. And let's see, I guess I'm not seeing the question screen. There's questions. Let's see. Oh, okay. What Reynolds number does it operate at? Like most of these things, it's pretty much like flying at a little over 100,000 feet on Earth, and it looks like it optimizes at a relatively higher speed. So that gets us up into the Reynolds number of maybe 200 to 400,000. So it's quite a low Reynolds number. It's right at that ragged edge transition where low Reynolds number effects really start to hurt a whole lot. Let's see, the second question we have, I think it's supposed to be ergometrics and generative approaches. What algorithms did you consider? And I guess this question, I think, is for Aviv. Is that right?
Yeah, so basically I've used Fusion algorithms, Fusion 360 as a built-in application for it. And basically it's pretty easy to use it. You, as I said, you give the software your constraints, like loads, the area that you would like to preserve, like fastening areas, and the area of obstacles, like if you have a specific volume that you want to preserve. And then you click on generate, and it gives you a lot of options. Then you can choose and compare different configurations according to a specific parameter, like manufacturing of technology, costs, mass, strength, and so on. And then you choose the configuration that you would like. Then you can also manipulate in order to continue to develop it on your own or take it as it is. This is the basic idea of the generative design.
Great. Let's see, somebody is saying VTOL with dedicated rockets sounds really interesting. Was there any consideration given to pivoting the main propellers instead? Those propellers wouldn't provide enough thrust. It would take a lot more disk area than those propellers. So you can certainly imagine an alternative design more like an eVTOL that had propellers that were at a vertical axis, but they would have to be quite large. So I didn't do that as a trade study. Like I said, I did this as one pass. My best guesses as to what would work, and it looks like this does work. And the appropriate thing now would be to do a lot of trade studies with those ideas and others. Next person is saying, where can I find those papers again? www.aircraftdesign.com is my website. I've had it for decades. And at the main screen, towards the bottom of that, you'll see Raymer Manned Mars Plane. If you go to that, there's a dedicated page with all the papers and such. Let's see, my old friend Santosh Kumar is asking, where is the landing light you mentioned? It's at the front of the nacelles, those inboard nacelles. The back is the pusher propellers, and the bottom of those nacelles has the rocket motors for takeoff and landing. And the front of that has these landing lights, which I think is a good idea. I think it was Jaspreet who came up with that, or maybe Aviv, I'm not sure. Somebody else thought of that, so good idea. Let's see, here's a question. It says, when is the Holotech going to be made? Holotech is the hovering screens. I'm afraid I don't know what that is. I thought it said holodeck. I thought it was a Star Trek joke, but it's something I'm not familiar with. Let's see, with that large flat of a wing, no dehedral, it's going to be tough to land. Well, there is actually dehedral outboard and also a bit of sweep to give you some dehedral effect, but we don't want a lot of dehedral effect. If you have a lot of dehedral effect, then any side wind causes you to roll a lot. So it's a real trade-off there. I'm trying to avoid the need for ailerons. If I had to, I could put spoilers, which don't cause that twisting moment. That's what I'm trying to avoid. But a lot of trade studies are needed, and maybe in the end, the answer is that ailerons are required, or maybe even we go so far as to use the rocket motors to handle any extreme upset. For example, if you come in on landing and the wind lifts a wing a lot, maybe you fire up a rocket motor real quick. Anyway, lots of trade studies need to be done. Let's see, more questions here. Is it to be assembled in Mars? My assumption was yes, and I didn't put anything in the design intended to allow it to fold up and then quickly unfold. There's been a lot of other designs looking at vehicles that would be sent to Mars in basically one piece. In fact, many of them will self-assemble while coming down under a parachute, which kind of puts a timeline on it, doesn't it? But that's a whole different thing. Here we're talking about a situation where there is a presence on Mars. There are people there already, and they will put the thing together on the ground, taking their time with a combination of parts sent from the Earth and parts made on Mars, hopefully with 3D printers, which I assume will be one of the first payloads to Mars, and hopefully they'll be much advanced a decade from now. Let's see, I saw total weight, next question. I saw total weight on Earth, 6,000 pounds. Yes, and they said ambitious, and the answer is yes, it's ambitious. We have quite a long ways to go. Also realize that this is supposed to be a very expensive project, not a self-funded, not a privately funded project, probably. In any case, the person writing this put a whole bunch of data on solar impulse with the weights and all that, and great. But this is hopefully in the future with more technology and a whole lot more money spent developing it. In any case, yeah, it's very ambitious. No kidding. It is ambitious. Those weights are going to be difficult. How much hardware is developed using 3D printing? I don't know. It depends on what 3D printers can do at that point. It would be wonderful if they could print out the entire wing structure in one piece. I don't think we're there yet. You know, more likely we'll put it together in smaller pieces and maybe glue it together the way you do with a lot of 3D printed model airplanes these days, although those aren't necessarily the lightest weight. I'm just not sure exactly how much is 3D printed. Certainly a lot of the smaller components, nacelle pieces, that kind of stuff, interior pieces, that stuff can all be 3D printed, I think, assuming that we get large 3D printers on Mars. There's also quite a lot of chemistry. There's a lot of materials available in Mars, both in the soil and the atmosphere. And people are talking about mining those on Mars, and hopefully some combination of those materials can be used to make structural parts. Let's see, and they're saying, oh, okay, that's, never mind. Okay, somebody says thank you, and that's the last question I see. We still have 7 or 8 minutes, so happy to answer more questions. Well, I don't see any more questions. Ken, back to you, and we can start with the next presentation, or everybody can take a 5-minute break. Maybe that's a good idea too, but up to you, Ken. We'll turn it back to you.
Okay, all right, thank you, Dan. This is really amazing. So if people have no more question, then I think, yeah, you're right. Maybe we just, let me see, Tracy, are you here? Are you able to start, or we should wait for 5 minutes?
Hello, I'm here. We can either start or wait 5 minutes, whichever you prefer.
Oh, okay. Yeah, so maybe we wait, yeah, because some people might expect your talk to start at 11:40.
That sounds
All right.
good.
Yeah, sorry. Yeah, very good. All right, so we take a 5-minute short break here. We'll start with the next exciting talk at 11:40 sharp. If you have more questions for Dr. Dan Raymer and the 3 co-presenters, you're welcome to type your questions. While they're still here, they can still see it and try to answer.
I see somebody asks about cabin air conditioning, and we didn't do that in any detail. There's something in the weight statement for environmental control system. I forget how much I put in there, but it's probably ambitious weight-wise, but just we can get something lighter than a ginormous system. Anyway, that wasn't handled in any detail so far. Are you volunteering?
Yeah. So folks, if you have more questions, you are welcome to click raise hand, and you will be muted, and you can speak out, or you can continue to type in the Q&A box. And you want to chat with fellow attendees or speakers, you are welcome to use the chat box. And the link for this webpage for Dr. Raymer on his website is posted in the chat room. Then in that link, you will be able to see a link in the middle to the publication.
Let's see, a couple more question. Aviv, what's that blue thing behind you?
I guess they are talking about the drone.
Yeah, tell them.
Yeah, so this is a drone that I have designed. Actually, it's now being tested in test flights. So it's still a prototype, but it's going to be a final product that will be released for everyone, for the market. So if you are interested in more info, you can check on the different social medias, Aviv Innovations, There are a lot of info about it.
Somebody asked, how long will it take for the longest flight range? And I don't remember off the top of my head. I'd have to pull out the spreadsheets. I think it was like 5 hours or something, but I don't remember for sure. Somebody says, are there any volunteer positions within your group? What are those? Well, I would turn it the other way around. What are you good at, and what would you like to do that can help? We're looking for lots of things. We haven't had anybody really take a good look at the motor installation, the batteries, the sizing, the controller, and those sorts of things. That was all done by ratio analysis by myself. Solar cell installation, haven't had that looked at in detail. So if anybody really wants to jump in on that, that would be marvelous. But like I said, whatever you think would be fun to do, and we can chat a little bit, and I can give you the data we have so far, and you can jump into it. So send me an email. If you go to my website, aircraftdesign.com, at the bottom is a link you can click there and send me email.
Sure, I'll do that. Thanks for sharing those
Great.
information.
I'm going to take a break myself. So any more questions the other guys on the team can answer? So be back in a minute.
Okay, so everyone is 11:40 now. So we'll start the next presentation. It's very exciting. You're welcome to continue to type your question, but in the Q&A box, but please indicate which question, which speaker your question is for. For example, if it is still for Dr. Dan Raymer, please mention for Dan, for Dr. Raymer. If it's for Tracy, then you can say for Miss Train or for Tracy. All right, so Tracy, you are here. Great, wonderful. Yeah, so our speaker, Tracy, she's a system engineer from NASA Jet Propulsion Laboratory. Her passion for space grew from an early love of science fiction series, movie, and books. She earned degrees in mechanical engineering at the University of Kentucky and the Georgia Institute of Technology, and began working at JPL in 2000. In her 2 decades at the lab, she has participated in the development and/or operation of multiple missions. The Mars Reconnaissance Orbiter, which is a science relay orbiter at Mars, the Kepler mission and exoplanet Hunter, the Juno mission and orbiter at Jupiter, and the Psyche mission slated to launch in 2022 to the Psyche asteroid. She is currently the lead flight systems engineer for the Europa Clipper mission, slated to launch in 2024. So let's welcome Ms. Tracy Drain for this very, very exciting talk. This is really amazing. Thank you.
Hello, thanks for that introduction, Ken. I appreciate it. I'm going to go ahead and start up the video or share my screen with the presentation. Let's start. Okay, I'm going to give you guys a little bit of a high-level overview of a couple of the missions, and you've heard of two of them that I've worked on that are intending to explore the Jupiter system. This is me, Tracy Drain, working at the Jet Propulsion Laboratory. And I'm guessing most of you are familiar with the Jet Propulsion Laboratory, but I just threw in a slide by way of introduction, just in case. This is one of the NASA field centers that is, there's about 10 of them across the United States. We are the ones in Pasadena, California, federally funded research and development center running JPL under contract for NASA. It's this pretty large facility. There are about 150 buildings, about 6,000 employees right now. And we're working on multiple missions at any given time. There are about 40 missions that we're working on in operations now for spacecraft that are visiting other places in our solar system, orbiting platforms that are studying things in our solar system and outside our solar system, and instruments that we might have on various other platforms that are generated by other companies and international partners. You guys may be aware of the Perseverance rover that recently landed on Mars. I had nothing to do with that one, but kudos to all my colleagues for their blood, sweat, and tears to get that safely down on the ground. Looking forward to some really exciting science feedback from that mission. So as you heard earlier in my quick bio, I have worked on multiple missions in my 20 years at the lab. The Mars Reconnaissance Orbiter, which is still in operations at the Red Planet and is serving as a relay orbiter for the rovers that are there. The Kepler mission, Exoplanet Hunter, its mission has ended, both the primary and extended mission, but discovered a truly phenomenal number of planets. If you haven't learned much about Kepler, do yourself a favor and do a quick Google search. It's pretty fantastic. The Juno spacecraft, which is in orbit at Jupiter now, and I'll tell you quite a bit about that in this presentation today. Psyche, which is going to be launching 2022 to study one of the more intriguing asteroids out in the main belt. And now I've left Psyche to join Europa Clipper as a lead flight systems engineer, which is launching in 2024, heading back to the Jupiter system, but for a focus study on Europa, one of the more intriguing moons of the solar system in my opinion. So I'm going to start off with just a little bit of an overview on how we do spaceflight project design at the lab and at other NASA centers and space companies. We begin with the science questions. What is it that the scientists are trying to understand? And therefore, what kind of information do they need? What kind of data? What instruments do they need to use to answer those questions? And then we start to mix some engineers into the mix in order to determine what do we need to do to get the data for the scientists. Can we study something with a platform far away and just point it at the target? Can we get enough data by doing a flyby? Do we need to go in orbit? What kind of orbit do we need? How long do we need to be there? All of those things go into the mission design. And then we have a proposal for a spacecraft that is going to support the instruments, and we work on refining the detailed design. We have requirements that the design has to satisfy so that the entire system comes together and is able to accomplish the objectives. And then we get to a point where we are assembling the major parts and testing them, and part of a time period that we call ALLO. As you can imagine, these things are going really far away from the Earth, so we can't exactly go grab them and fix a piece of hardware if we have a problem with it. So we have a pretty extensive test program, and then we put them on the top of a rocket, launch them on their way to where they're heading, and are into the operations phase. And sometimes, like you'll see with Juno, the spacecraft take a really long time to get to where they're going. So we have a lot of cruise operations as well as science operations once we arrive at our destination. And I meant to mention, by the way, before I started, I'm probably not going to be able to multitask well enough to pay attention to the chat and catch questions. So if you have questions and I fail to see them, I will definitely circle back to those at the end. So in the development of the Juno spacecraft, which JPL did in a partnership with Lockheed Martin, there were a lot of key engineering challenges that had to be met. One of them is a very high radiation environment at Jupiter. Jupiter is a huge gas giant. It's made mostly of hydrogen and helium, and that hydrogen and helium are super compressed because it's so big. You can fit about 11 Earths across the middle of Jupiter. It's so big so condensed. There's a lot of high pressure and temperature as you get deeper and deeper under the clouds toward the interior. And as you get deeper inside there, the pressure is so high that the electrons are essentially squeezed off the atoms and can free flow around inside. Jupiter, even though it's so large, way larger than the Earth, it rotates once in every 10 hours. And so now you have a rotating electrical field, which contributes to generate this truly massive magnetic field that then captures charged particles from, for instance, solar particles from the sun that get accelerated to relativistic speeds around the magnetic field and create this really strong radiation field around Jupiter. You can almost think of Jupiter as sitting in the middle of this donut of radiation. And even though we do some things with the plan of the orbit around Jupiter in order to minimize the spacecraft's time in that radiation zone, we do dip through it every time the spacecraft does one of its orbits around Jupiter. And in order to make sure the spacecraft can survive long enough to do its mission, we have the sensitive electronics inside a radiation vault that's tucked up under the high gain antenna, made primarily of titanium, that knocks the radiation environment inside the vault to something much closer to what we would see at a planet like Mars, for example. And there's spot shielding in various places around the spacecraft, and in order to make sure the components exterior to the vault will survive the mission duration. The spacecraft is going a really long way away from the sun. I'll talk a little bit about that, or has gone. I'll talk a little bit about that on the next slide. When the spacecraft was launched, it was the furthest mission that was going to be solar powered that we've ever done. So the solar arrays have to be really, really large in order to generate enough power to run all the spacecraft components and keep everything warm all the way out at Jupiter. You can get a sense of scale from the size of these people here doing a walkout test of the solar array at Lockheed Martin. The arrays are about a little under 9 meters long in order to generate as much power as we need. Again, I'll talk about that in a second. There are, of course, as you see on all spacecraft, thermal blankets, and there are electric heaters in various places and radiators in order to maintain the temperature on the spacecraft, keep components from getting too hot or too cold, as we're all the way out there 5 times farther away from the sun than the Earth. For telecom, the spacecraft is going a long way away from the Earth. And so to communicate back, we have this very large high gain antenna, which we use to point very, very accurately at the Earth to get our maximum data rate to send back science data and also engineering telemetry. And if you have really sharp eyes, you'll notice that there are a couple of other telecom antenna on the edge of this one and at various places on the spacecraft. The medium gain antenna we use when we're not pointed quite as accurately. And then the low gain antennas we'll use when we have to be pointed quite far off the Earth. For instance, if the spacecraft is in safe mode and might not know exactly where the Earth is located. To get into orbit, we have a really large main engine that the spacecraft needed to fire for about half an hour to slow down enough to get captured into the gravitational field around Jupiter and go into our long orbit. And we'll talk a little bit more about what that looks like too. So at Jupiter, again, as you think about the sun going, the light traveling away from the sun, expanding in a sphere, as you go farther and farther away, any given area sees the square root of the distance of the amount of light. So if you're twice as far away from the Earth, you get 1/4 of the light. If you're 3 times as far away from the Earth, you get 1/9, all the way out at Jupiter. 5 times farther away from the sun, we get 1/25. And so the solar array needs to be quite large. It stretches pretty much end to end on an NBA-sized basketball court. And at Earth, theoretically, the solar arrays could generate something like 14 kilowatts of power. We have to limit the number of cells that are in use when we're that close. Otherwise, you would just totally overvoltage the battery. All the way out at Jupiter, they generate something more like a bit over 500 watts of power. And about half of that is used for heat for the spacecraft. And the rest of it goes to power all the engineering components and all the instruments to do the things that the spacecraft needs to do to get its job done. And speaking of instruments, there's quite a complex instrument suite on Juno. There are a lot of things that the scientists are trying to discover, things like understanding how deep the clouds go on the surface, about the atmospheric composition, how much water vapor there is on Jupiter in the clouds. We're trying to understand what the size of the core is. And to do that, we use the telecom system for gravity science. And there's also a magnetometer out here on one edge of the array to get it away from the magnetic fields generated by the spacecraft that is used to do a global mapping of the magnetic field. And there's also a camera, JunoCam, which is used for science, but also for public outreach. If you haven't seen some of the really cool images the Juno spacecraft has taken back, I dropped a couple in this presentation for you, but you'll also want to go check out the JunoCam gallery and see our completely new view that we've got on the planet. One of the systems engineering tools that we use, I'll talk a little bit about the kind of work that I was involved in, is a tool called fault trees that we use to identify potential faults. When we send spacecraft really far away, particularly when they're so far away we can't joystick them and they have to be able to take care of themselves until we can get in touch with them, we have to go through this rigorous thought exercise to figure out all the different things that could go wrong and whether we can either design them out of the system or make the spacecraft robust so it can handle those issues if they crop up. And I'll give you an example that is kind of from our launch phase. In order for launch to be considered successful, you need to both have enough power, you're not running out of power, you're generating enough power. You need to have communication with the spacecraft, you need to be on the right trajectory to where you're going, and you need stable temperatures. You can't be getting way too hot or way too cold in any of your components. And so those are some of the things we think about for a launch to be successful. And then we take each one of those different areas, say power, for example, and we ask ourselves, well, what are the reasons that we might not be doing a good job or the spacecraft might not be stable for power? So maybe the solar arrays aren't generating power, maybe the batteries aren't supplying power, and we continue going down that set of branches. And then we ask ourselves, well, why can the arrays not be generating enough power? Maybe they didn't deploy. Maybe we're not pointing them at the sun. Maybe there's some failure with part of the array. And we ask ourselves, okay, so why didn't the arrays deploy? Well, maybe the release mechanisms didn't work. Maybe a hinge seized up. Maybe a damper failed. Maybe the commands didn't go out, and so on and so forth. And we do that across all these different branches until we get all the way out to these leaves. And for each of the leaves, we ask ourselves if there's something we can do in the design to prevent that thing from happening altogether. Or is there something we can do in the design so that if it happens, we're robust to that and the spacecraft is okay? For example, if we have a hinge that could seize up, maybe there's two rotating surfaces in that hinge. So if one of them seizes, the other one's fine, and therefore the array will fully expand. So this is the path that the spacecraft took to get all the way out to Jupiter. We launched it in 2011 at the Kennedy Space Center. And then we couldn't send it on a direct path all the way out to Jupiter. We didn't actually have a launch vehicle big enough with enough throw capacity to send us on a direct trajectory. So we sent the spacecraft on a trajectory that took it out past the orbit of Mars. That's this red line, if you can see that. We had to do 2 deep space maneuvers, which is using that same main engine on the aft end of the spacecraft, burning for half an hour, and each of these maneuvers separated by a couple of weeks, to make sure we were lined up to be on a trajectory to go back by the Earth for an Earth flyby a couple of years after launch to get the rest of the momentum we needed to get all the way out to Jupiter 3 years later on July 4th, 2016. And you can see here, I've noted our science phase was intended to begin shortly after that. I'll talk a little bit about that. And then extend for originally about 1.25 years once the science phase began. But the expectation was always that we'd be able to seek an extended mission. And then some things happened along the way, which caused the primary mission to take a little bit longer, which I'll tell you just a little bit about in a second. So we had some interesting times during cruise, even though we went through that whole thought process that I had mentioned about developing fault trees and then figuring out the ways to make the spacecraft robust to them. Because we do a lot of things for the first time, we're modifying designs, we are exploring new territory. There are always things that crop up and surprise us along the way that we then need to respond to. And some of the interesting things that happened during cruise, right out of the gates, while we were still around 1 AU, there were some components that were warmer than we expected them to be. And so we wound up taking some engineering models and putting them into some thermal vacuum chambers so that we could suck all the air out, make them seem like they're in flight, shine some sunlight through there in a sim in order to update what our thermal model was to help us understand what was going on with those items and whether they were going to be at the temperature we needed them to be by the time we reached Jupiter, or if there were going to be problems along the way in cruise when we were at our closest point to the sun. And all of that turned out fine, thankfully, but that made for some interesting times. One of the other interesting times in cruise, the way that the spacecraft orbits Jupiter, it's a polar orbiter, which was important for us to be able to get some of the science we were seeking. But if you can see my hands, if you guys are the sun and Jupiter is the planet, and my finger is Juno, we were orbiting the planet this way, such that the sun, the Jupiter planet, was never between the sun and the spacecraft. So we were not going to have long eclipses just based on occultations at the planet. We would know we would need to use our batteries, because in order to do the orbit insertion, we had to turn the spacecraft 90 degrees to the sun so that there wasn't any sun on the arrays, but it wasn't due to being behind the planet. At the Earth flyby, we actually were going behind the planet, and we were going to have an eclipse of about 19 minutes. And we did all the analysis. We made sure the power system was sized appropriately so that that was not going to be a problem. But it turned out that we did have a bit of a surprise, and 12 minutes into the 19-minute eclipse, the spacecraft declared that it had an issue related to power and turned off some components that weren't necessary to stay safe, entered safe mode, and phoned home. And this is all of us in the mission support area over at the Jet Propulsion Laboratory, looking very unhappy on that day. It turned out we were able to understand what happened fairly soon after that, and it turned out to be kind of a blessing in disguise, because it caused us to do some refinements of the way that we were doing power modeling and prediction on the spacecraft, and we were in much better shape once we got out to Jupiter to have a pretty tight story there for the low power situations we were seeing when we were in the expected lower power conditions we were seeing when we were at the planet doing science operations. Those weren't the only fun things that happened during cruise, but there were just a couple that I decided to choose for examples to tell you about. When we got to Jupiter in July of 2016 and fired our main engine for 35 minutes to get captured, all of that went very, very well. And you can see our colleagues out at Lockheed Martin. I was actually there with a couple of other folks from JPL with the Lockheed Martin element of the team, and some folks at the mission support area at JPL, all celebrating, looking super happy. Google even made us a doodle, very nice of them. Excited that the spacecraft got into orbit insertion so that we could then get everything checked out and get ready to start taking science. Now, another unexpected issue that happened to us thereafter, we originally in the plan were to get into orbit, which went fine on July 4th, and then we were to do these two large 53.5-day capture orbits and turn on the science instruments for that next flyby, 53.5 days after orbit insertion, collect a bunch of science data, see that all the instruments were working fine, and we were getting what we needed in terms of data. All of that went great. And then we were to do the second 53.5-day orbit and configure the prop system to do our last 35-minute main engine burn in order to shrink our orbit down to a 14-day orbit, and then do the rest of those, 32 of those, to complete the full science mission. And it turns out that in the last run-up to configure the prop system to do that main engine burn, there were some unexpected signatures that we saw, which caused us to wave off that burn and stay in the 53.5-day orbit so that we could go pull together an anomaly response team, understand what happened, and decide what we were going to do about it. And it turned out through that whole process, took us a couple of months, we decided that it would be too great of a risk to burn that main engine again. And the scientists had enough time to determine that it would actually be perfectly fine to get all the science data that was desired if we stayed in the 53.5-day orbit and did 32 of those. As you can imagine, that was going to take longer. This is about almost 4 days longer than our 14-day orbit. And so there were conversations with NASA headquarters to make sure that that was going to be a fine thing to do. And ultimately, that is where we landed with the mission design. And it had some benefits, because staying in the primary orbit longer meant that we were going to see more of Jupiter's year as Jupiter orbited the sun. It takes about 12 years, if I'm remembering that right, for Jupiter to go around the sun. So we get to see a quarter of that, as opposed to a much smaller percentage in our original mission design. So that was a nice example of making lemonade out of lemons when we had that issue with the prop system. And so since the spacecraft has been there orbiting Jupiter, taking science data, there've been a lot of really cool things that we've learned. I mean, I'm on the engineering side of the house. I was the deputy chief engineer in operations for Juno. But one of the reasons we send spacecraft here is for the science. And it's really cool to get to be at the forefront, hearing the things that the scientists find and tell us about as they're telling the world about it. And so if we think about Jupiter as we knew it, this is the image that comes to my mind. Wouldn't be surprised if this is the image that comes to your mind. We're used to seeing these tan and kind of reddish bands of Jupiter because the missions that visited Jupiter in the past either flew by near the equator, at the equator, or orbited around the equator. And so we never had any direct data of what the poles look like. And so one of my favorite pictures is this one of the poles. You can see, I think this picture is a little bit color stretched, but it is a bit more purple and blue near the poles. And you get kind of this soup of cyclones happening. This is an image of the South Pole, which has about 5 storms around a central storm in visible light. I really love this image, which is of the North Pole and infrared, where you can see this kind of amazing pattern of 8 storms that are sort of symmetrically spaced around a central storm. I love that these 4 storms look similar. These 4 storms look similar. So there's some really interesting atmospheric patterns happening there at the planet. And this is the North Pole with a combination of visible and infrared. So you can just see on the North Pole those 8 storms, but kind of what they look like instead of in this infrared where the lighter areas are warmer and the darker areas are cooler. This is kind of the visual signature of that. This is a close-up of the Great Red Spots, which the spacecraft flew over, I think once while I was there and a couple of times more since I've left that mission. This is a 2D image, but I think it's cool because you can see enough of the details and the patterns of the clouds. It almost looks like you're about to be sucked down in there, which is amazing. And this is one of my favorite pieces of constructed science information that came from the team as well, because it shows how we can layer information from a couple of different instruments. This is the visible image from the Juno CAM instrument, and you can see the Great Red Spot here and the clouds around it. The microwave radiometer has the ability to kind of penetrate the cloud top down to about 350 kilometers and see differences in temperature. You can see where it's warmer, lighter, and where it's cooler, it's darker. And also some composition. This is the instrument that is used to determine the water composition of the atmosphere as well. And one of the things that was intriguing for the scientists is that the storm sitting on the surface, you can see that it has an influence all the way down to the lowest depths that this instrument can penetrate, all the way down to 350 kilometers. There's a difference across the storm from in these latitude bands. So the roots of at least the Great Red Spot go pretty deep on the planet. So for me, I left Juno in 2018 to go join Psyche and then stayed with Psyche for just a couple of years before getting pulled over to the Europa Clipper mission. That's what I'm doing now. This is a lovely image of the moon Europa taken by the Galileo spacecraft, which orbited in the 90s to about 2003. And a little bit of history about the Galilean satellites of Jupiter. Galileo back in 1610 discovered the 4 largest moons. They were also discovered by Simon Marius around the same time, but I think Galileo was just the first to make it to publication. These are the 4 that he could see. Originally, he thought that they were stars, but he realized that those stars were changing position around Jupiter on successive nights that he was observing them, which made him realize that they must be orbiting Jupiter the way that the Earth orbits our star. Ganymede is the largest of the moons. It's actually a little bit larger than Mercury. And Europa is the smallest. It's a bit smaller than our moon, but it's still the 6th largest moon in our solar system. Galileo is the spacecraft that studied the Europa system, the Jupiter system, including Europa from 1995 to 2003. Now there's some interesting things about Europa's surface. Number one, it's pretty smooth. It has some craters, like this really large one near the southern hemisphere, but you don't see a very heavily cratered surface like you do with the surface of the moon. And scientists believe that that's because it's being resurfaced or has been resurfaced in fairly relatively recent geological timeframes. It has a lot of these ridged plains and chaos terrains where you have ridges that go in different directions as if the surface has been cracking and shifting and allowing water perhaps to seep up and resurface it. There are also these little lenticulae, which is a word that means freckles on the surface that the scientists want to learn more about as well. One of the things that's the most intriguing about Europa is its interior. Scientists think that it has an iron core with a rocky mantle, kind of similar to Earth, and has a thick shell of ice. And underneath that ice is a tremendous amount of water, about 2 times all of the Earth's water combined on a surface that, or on a planet, on a body that is about a little bit smaller than our moon. And so there are some clues to why we think that there is water there, to why the scientists think that there's water there. And some of them came from Galileo. Galileo carried a magnetometer, which was there to measure the magnetic field of Jupiter and determined that where the magnetic field lines of Jupiter intersect with Europa, those lines were bent. And the way the scientists are understanding this is that on the Earth, salty ocean water acts as an electrical conductor. And as that water moves around, it interacts with the magnetic field that's generated by the Earth. And so there's a good clue that a similar thing might be happening with Europa, and that there's some conductive fluid under this ice shell like water that has dissolved salts in it. And the first question that people tend to ask is, okay, well, Jupiter is 5 times farther away from the sun than the Earth is. Why would there be enough heat there to make liquid water under that ice shell? And the answer to that is tidal flexing. Europa orbits Jupiter in an orbit that isn't exactly circular. It's a little elliptical. And when it's closer to Jupiter, it gets pulled a bit more strongly by Jupiter's gravity. When it's farther away, it gets pulled less strongly. And that creates essentially this kind of pulling, relaxing action on the moon, which generates friction inside the moon's material. And that is the source of heat, which scientists think is enough to make a lot of that ice melt and give you this layer of water underneath the ice. Scientists don't know how thick that ice is. There are some estimates that range between 15 to 25 kilometers, and estimates for the ocean depth of anywhere between 60 kilometers to 160 kilometers. And that's part of the thing that the Europa Clipper mission is intending to help us determine is how thick is that ice, how much water might be down there. Why does that make Europa intriguing? Well, our understanding of life here on Earth is that it requires water. Essential elements, there's an acronym called CHNOPS: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Those things combined, as well as an energy source and stability, are the things that scientists believe are necessary to develop life as we know it here on Earth. And this video that you're seeing here is from hydrothermal vents down at the surface of down at the bottom of the ocean, where the water meets rock, and it's very hot down there around vents where there is heat escaping from the Earth's interior and providing a source of energy for life down there, which is so far down below the surface that sunlight doesn't actually penetrate. So this is life that's really driven by that chemical energy by the energy of heat from down below. And scientists wonder if a similar situation could exist on Europa. And it's been there for a really long time, with potentially enough time for microbial life to form and develop the way that it did here on Earth. So the way we're going to end up studying Europa in terms of mission design is to not put the spacecraft in orbit around the moon itself. Europa is nice and nestled inside that donut of radiation I talked about earlier around Jupiter, and that would be really difficult for us to design a spacecraft to be able to handle. And so we're going to be orbiting Jupiter, but in such a way that we do multiple flybys of Europa, using the flybys themselves to target us for the next one, and make a web of flybys around the moon, about 50 of them, fairly low altitude. There's a range of altitudes, but the lowest ones are down to as far as 25 kilometers above the surface in a little under 4 years. And that'll give us an opportunity to do kind of a global regional coverage of Europa from that orbit of Jupiter, to keep us out of the high radiation environment most of the time, but give us a really good data set from the moon. Similar to Juno, Clipper has a lot of different science instruments that are looking for a lot of different things. There are particles and fields instruments that will be kind of examining what we can see around the surface. There is an ice penetrating radar that will help us plumb the depths of that ice shell. There's a magnetometer, which will help us sense the ocean properties. And there's a thermal imager that'll let us search for hot spots on the surface. There are instruments that'll allow us to detect plumes, if there are active plumes there at Europa Clipper while the spacecraft is there. Lots of fun and games for the scientists to get their data back and help learn as much as we can about the moon. For the spacecraft itself, the engineering challenges that needed to be overcome were similar to the ones that Juno had to face. This spacecraft we're partnering with APL to develop, and many other partners and contractors for both the instruments and the spacecraft body. We had to deal with the long Jupiter sun range, and similar to Juno, the spacecraft is solar powered and has really large solar arrays that stretch off the edge of a basketball field, and has 3 lithium-ion batteries. Unlike Juno, the spacecraft is expecting to see fairly long eclipses at Jupiter. The spacecraft is designed to deal with 9-hour-long eclipses at the max. We are also needing to deal with the radiation. There's an electronics fault on this spacecraft as well in order to protect the electronics. Thermal, really far away from the sun, as opposed to Juno, which had electric heaters and radiators and blankets. This spacecraft has a heat redistribution system that has a pump that pumps refrigerant around pipes that are trying to take what would otherwise be waste heat from the electronics vault and pump it around the propulsion module so that we can be as efficient as possible in keeping the spacecraft warm. And it does also have some electric heaters and thermal blankets and radiators. For the long distance to Earth, you can see again a similar large high gain antenna, and we have a medium gain and several low gain antennas. The spacecraft has X and Ka band downlink capability for sending its data back to the Earth. And similar to all spacecraft, we've got a command and data handling system. This one has a mix of behaviors like very complex activities that are kind of hard-coded, baked into the software, and also a flexible sequencing architecture that lets us send it a series of commands to do very specific activities. And similar to Juno, we have fault protection so that if things go wrong, the spacecraft can take some action and keep itself safe until the ground can get back in the loop. For the propulsion system, unlike Juno, this one does not have a single main engine that we use to get into orbit, but we use the thrusters, the same thrusters that we use for attitude control, and just burn them for a really long time in order to get the spacecraft into orbit. And there's an active pressure control system, pressurize both the fuel and the oxidizer when we're doing those long maneuvers in order to get the spacecraft into orbit. And then we have the fairly standard attitude control, the star tracker, sun sensors, inertial measurement units, all for attitude knowledge, and then reaction wheels when we're not on thrusters to control the spacecraft attitude. So where we are right now with the spacecraft, we got through our critical design review in December, which is one of the major gate reviews that we need to talk through all of our design of the spacecraft and the mission system and the ground data system and the instruments and all of the various elements of the project to a review board, which contains members from NASA headquarters and industry in order to go through all of our design and make sure that we are touching all the things that need to be fully refined as we are now moving into the stage of manufacturing hardware and looking at starting our assembly and test period in the spring of next year. And I think that's the last slide that I included, and I left us a little bit of time at the end here for questions. Nope, wrong one.
Oh, fantastic. Yeah, fantastic, excellent talk. It's really, very exciting. So that gave us almost like 30 minutes. So I think Daniel has a question. Mr. Giddy is from Astrobotic, the company who got the NASA tipping point contract for doing the lander rovers located in Pittsburgh, Pennsylvania. So he's our speaker later today for site tour and for the lander rover. He has extensive experience with launch operations. So I think, Daniel, Mr. Giddy, welcome to speak out.
Oh, no, just awesome job. I guess one quick question. What would you say is the largest challenge on these deep space, long duration missions you face from a spacecraft design perspective? For example, is it more thermal, comms? What do you think is the most challenging area of all the things you hit?
The funny thing is I'm laughing because I'm imagining any of my subsystem engineers standing next to me would be like, my system's the hardest. No, it's not. I personally tend to, and maybe it's because I spend a lot of my career working with our fault protection teams in order to develop fault trees and try to figure out how to keep the spacecraft safe. I tend to think of it as the fault protection just because there's so many different things we have to keep in mind and so many options we have in order to deal with those issues. And we have to come up with a balance between making the system so insanely complex that you're trying to figure out how to respond to 57,000 different things. And then you get yourself into trouble because that complexity could spawn some problems of your own that you didn't anticipate. And making the system overly simple so that you don't respond to all the things that you need to respond to. So finding that right balance and then making sure you have time to develop all that software and do all the verification, validation, testing of that software, and then still have it be flexible enough so that when you come up with new surprises you didn't anticipate, that, in my opinion, is one of the hardest challenges, but one of the more fun ones too.
Okay, thank you, Daniel. I wonder, Tracy, would you be able to see the Q&A box?
Yeah, I'm taking a look over there, and I see someone's asking, can you let me know where I can read the details like power and telemetry design that you've mentioned in the presentation, or failure analysis if I want to avoid calamity that happened with the rocket in Oregon, my son in the learning phase. So yeah, there are some folks on the project who've been writing published papers if you want more details about the system. I think if you do a search for Europa Clipper and then type the piece that you're interested in, like power system, and then you might be able to get some papers that pop out that way. If I have a minute at the end of my talk while the next speakers are talking to go find a couple of things, I can pop them into chat for you. But Google is your friend. There's a lot of really good stuff out there. And there is a mission page, and maybe I can find that one. And the mission page itself probably has some links to recent publications too. So I'll stick those in the chat momentarily. Let's see. And the next question, any plans to have a probe reach the Europa Ocean? Yes, indeed. There are lots of people who are working. They're still in the early phases, right, of coming up with what technology would be necessary in order to first just put a lander on the surface and then figure out how to get a probe below the ice. The things that are challenging about going below the ice, well, there are lots of them, but some of them are just the thickness of the ice, right? If it really is 25 kilometers, that's a long way to go to get something below. You might be able to find places that are more hotspots by using like some of the data that we'll have on our spacecraft, looking for places that are warmer and therefore theoretically have thinner parts of the ice. But we also are super concerned about not contaminating the subsurface of Europa. If it really is a place where there might be life that has developed independently of life here on Earth, like it would just be terrible if in our efforts to go down and examine that, we brought along Earth organisms and then contaminated it and found something and thought it was developed there, but it wasn't, or even worse, like something that was gonna be harmful to the life that might be down there now. And so a lot of people have been trying to figure out ideas like that. I don't know if you're familiar with Lake Vladivostok in Russia, but there was efforts in the past, I read about this a really long time ago, to figure out how to get below the surface of the ice of that lake, which they think might have been frozen over for a really long time. And so had some scientifically interesting things to go and explore. So that's a place where people can practice ideas of how to get below the ice with something that's sterile, be able to get your data all the way up back through the ice to whatever asset you have on the surface, and then let the scientists get that information to study what's there. Let's see. Nothing on this mission like Ingenuity. So not on the Europa Clipper mission. We are purely an orbiter. We're going to go there. We've got the instruments that can sense the particles and fields and the magnetic field from where we are, and the instruments that can sense like surface composition and get through the ice. But yeah, we don't have anything on Europa Clipper that's going to try to get down to the ground or detach and fly around. Ingenuity is pretty cool. Hopefully you guys are keeping an eye on the news feeds to see how the little helicopter on Mars does when they're able to get it off the ground.
Hi, Tracy, this is so exciting. But you mentioned about that you have a couple of flight low altitude. Are they all low altitude, or some high altitude, some low altitude, and how low it would be?
They're a mix. I think that the highest ones are something on the order of 1,700 kilometers, but the lowest ones are like 25 kilometers. I swear, when I first joined the mission and I saw that number, I was like, is that a typo? Is there a zero missing? I'm like, wow, that's really low. So that's going to be kind of amazing in terms of just the quality of the data we're going to get with the instruments flying that close to the surface, and our ability to be able to detect plumes to like, wow, I personally can't wait.
Yeah, 25, that's, it's kind of scary, very low.
Yeah,
so.
It is. When I'm looking out my window, like I'm about that far away from downtown LA, and I'm thinking, wow, is that like,
yeah,
is that really what we're doing?
It's amazing. It's amazing. Yeah. So it looks like there's no, but anyway, there's no topography, right? It looks like it's kind of, there's no up hills or mountains, so there's probably no tension.
Yeah, and that's a good question, because I know when we looked at that one picture earlier and you could see like the cracks in the terrain, you could see some of the craters. I don't know what the topography is, right, from the things that you can see there, but there isn't like Mount Everest, I don't think. There isn't Mount Olympus like there is on Mars. So I think those are the things that make it feasible for us to fly such low altitude.
Yeah,
but I'm going to have to go talk to my scientists and see if that's really the case.
Yeah, please. Because and actually another scary thing is what you mentioned, because it move around, right? And the shape become very oval shape. So actually it change. The shape change. Because the gravity. Is pulling, and they become.
A little, yeah. That was
Yeah.
extremely exaggerated in the picture that I showed you.
Yeah. So the error, the margin of error needs to be very, very small, I guess. Because of the expansion of the thing. Then the other thing is the beautiful picture. Is a virtual background. You see a lot of surface structure, those stripes. Yeah. So initially it looks like it is like a river bed, but it's probably
Right.
not. Can you comment on those structure? What is possible?
Yeah, I was just looking that up because someone had asked me that the other day about what those are made from. And I found that, so the Galileo spacecraft took a spectrometer along with it. It was more like near infrared spectrometer. And people can use the Hubble Space Telescope to do visible spectrometry on the moon. And what I found is that they think that that kind of rusty red surface that you're talking about is made of water ice mixed with some hydrated salts, maybe magnesium sulfate or sulfuric acid. And I think the idea, and again, me, engineer, not scientist, so go use Google, and I'll go back and talk to Bob Pappalardo, who's our lead project scientist. But I think the idea is that those cracks happen and then water can come up and resurface. And I don't know if it's being in the radiation environment that is interacting with whatever that is on the surface, that the water with hydrated salts, that is causing them to discolor in that way. But it is interesting that you can see so much of the features based on that.
Yeah, but you see, that's a very interesting, engineering point of view. Since you mentioned that the lowest flyby will be 25 kilometers, you can just drop some very tiny, rover robot, right? it just drop, 25 kilometers. Why not?
That would be cool.
Yeah.
I'll go back to talk to people, see if they can.
Yeah, why not? It's still time. Put something there, and everyone gets so excited.
Yeah, that would be amazing. A lander on with a team. There is a team of people who are working on a proposal for a landed mission on Mars, and it's so, or on Mars, on Europa. And one of the things that is super challenging is, so landing on Mars, also very hard, but you do have some atmosphere to work with. Those of you who watched the Perseverance landing or are familiar with the Curiosity rover landing, you've seen the huge parachute that is used to help slow the rover down before it then lets go of the chute and switches to retro rockets to come the rest of the way down. There's no atmosphere really to speak of on Europa. You can get some little bits of water vapor when you have the plumes, but there's nothing like that. You can't use a parachute. You're really going to have to deal with coming down in a powered descent. And the thing that is a little bit scary about that is, again, very pristine place, might have all the ingredients for life, really don't want to put any earth junk down there. And so you have to be concerned to make sure not only that technically all of your components work to get you to the ground, but in that what if hypothetical situation, something goes horribly, horribly wrong and you were going to have an unintended crash landing onto the surface, you have to make sure that even in that condition, you're not going to be contaminating the surface with whatever it is that came on your spacecraft. So that's a pretty huge challenge for the Europa lander team to work their way around as they are trying to develop a mission plan to get down on the surface of that moon.
Yeah, actually, I'm asking this for some of our people, because sometimes we have the space architecture events, and there are people asking, can people live on Europa Clipper? Do you think it's a good environment? Is the surface stable enough? There's water. Now there's water, so it should be good for habitat or something like that.
Yeah, that's a really fun thing to think about. I don't know how many of you guys watch The Expanse, but that's one of my favorite shows right now. And I think that they had like farms right on both Europa and Ganymede. And because there's lots of water there, you think that it'd be an interesting place to explore for human colonies. One of the things that people are going to have to figure out how to deal with is that really, really intense radiation environment that the moons are just bathed in all of the time on Europa. And people ask me in other talks too, like, well, why do scientists think that there might be a possibility of life there if the radiation is so intense? It turns out that water and ice are a pretty good radiation shield. And when you're below 25 kilometers of ice, then there's a more protected environment down there where there's liquid water. And then as you go farther down, there's even more water above you in the radiation environment. And you have the heat that's welling up from the moon based on the tidal heating. Like all of that stuff makes it still a pretty good environment for life under the ice. If you're talking about humans who are trying to have a colony or some kind of presence on the surface, now you got your work cut out for you to figure out how to protect people from that radiation environment long term.
Yeah, that's good. And also, this is a kind of side question, because you mentioned in your bio, you're inspired by science fiction and movies. Which one you like most? Which one?
Oh gosh. So when I was growing up, definitely Star Trek. Not The Next Generation. Sorry, Mom. She did make me watch that one, but I liked. Yes, The Next Generation. I liked that one better than the original series. And what else did I like most? I mean, I had to like Star Wars because you had to as a kid in the 70s and 80s. But I think Battlestar Galactica was one of the shows that I really liked.
Me too.
Yeah, and even though some people didn't like the new one because they changed some of the characters around, I really enjoyed that one a lot. So that was great. But right now, The Expanse has to be my favorite sci-fi show.
Yeah, actually, I have the same feeling too. Initially, I saw the new Battlestar Galactica. It was a little bit strange, Starbuck become a woman,
Exactly.
Things are sort of strange. And it didn't have the initial, like romantic, epic, kind of feeling. But you are right. I agree. That kind of fun stuff. Yeah. It is pretty cool. Yeah. Yeah, very good. Yeah, this actually indeed very inspiring. And actually, some of our Apollo engineers, or shuttle engineers, they said they were inspired when they were kids, by earlier sci-fi, like a Destination Moon, those kind of stuff, so it's really fun, thank you.
I find that a lot of times that myself and my colleagues and the people that I talk to all have this deep connection to science fiction. And it's the thing that made us really want to get involved in the space industry and do things to help push mankind a little farther down that path. One of the things that's really cool about living in Los Angeles, there's this group called the National Academy of Sciences Science and Entertainment Exchange, and they work with people in the industry, writers and producers, and try to get them connected with folks who do the kind of work that we do, and also a bunch of other fields, so that they can inject the kinds of movies or theater plays or books or whatever they're coming up with more realistic science and technology, both for their plots and also for characters. It's a really cool thing that they're doing. And so my life has a little bit come full circle from being inspired by science fiction to want to get a degree that allows me to work for NASA, to then work with people who are trying to make better science fiction to inspire the next generation. It's kind of fantastic.
Yeah, that's good. Did they ask you to act in some of the movies?
They have not. That would be scary. That is not one of my skills.
Yeah, it should. It's a brief balance, with science engineering to the film. Actually, you're right. I think that's also AIAA want to do, and also you and JPL, because it's important to that those movie producers know some realistic things. So that's inspire the next generation properly. It's not to write off something with science and engineering principle. So that's very, very important. So kind of this, of course, there's certain things are still in design, but among all the engineering, tasks for the Juno and the Europa Clipper overall, can you tell us, one thing you think is more exciting or challenging, something like that?
I'll tell you, one of the things that is my favorite is we do a series of tests called mission scenario tests. When we are going through the process of verifying and validating that a spacecraft works, you have to start with the basics, right? With all your subsystems. Do these specific individual components work by themselves? We have a lot of people who are doing code testing of pieces of the software. But I like when you're getting toward the end and all of the things have come together and you're trying to show that the spacecraft hardware and software works together when you're trying to put it through its paces in sort of a day in the life, and you're running the whole launch scenario, or you're running the whole orbit insertion scenario, or you're running a whole bunch of things strung together that have to be done in cruise. I particularly like that because it's your opportunity to really see how the spacecraft is working and get a chance to see if there are surprises where things aren't going exactly the way you expect them to. So there's that set of tests. And I also really enjoy the fault injection cases where we can't throw like all the different faults we would like to at the actual hardware that's going to fly because you might break something. And so we do a lot of testing on our test bed or in our software only sims. And that's cool because when you get to throw problems at the spacecraft and see how it responds, things happen that are different than you expected all the time. And that's when you learn the most about your system. That's when you have an opportunity to make some final changes before you launch it. I think those kinds of things are pretty exciting.
Yes, and also, you know, you mentioned this mission for the Europa Clipper is about 4 years. So after that, is it just continue to do things, or you know, is there any plan, or you just continue to orbit, you know, or somehow until the battery run off, or
yeah, and to tell you about what might happen with Clipper, I'll tell you about what's just happening with Juno. So Juno was intended to just do 32 science orbits, and then they were going to, just like they did with the Cassini spacecraft, deorbit it into Jupiter to dispose of it so that it will never accidentally at some point in its future, like crash onto Europa, for example. And recently, earlier this year, actually, they got granted a mission extension. So NASA approved additional funding for the spacecraft to do another, I want to say, another 40 orbits, maybe, like at least until 2025, or until the spacecraft runs out of fuel or has some fault so that it doesn't work anymore. And so a similar thing with Europa, our mission plan right now is to do the 50 or so flybys of Europa, plus a couple of the other moons. And that's how we define our budget. That's how we are making sure all of our requirements for the components need to survive that long. It kind of is intended to end there, and then with the disposal of the spacecraft at the end. But the expectation is that the spacecraft's doing fine, and we can show that it will continue to do fine for some time, then there can be an opportunity for us to request a mission extension from NASA, and then we'll see if it gets granted.
Actually, there's a question in the Q&A. I have another question, but I think give it the chance to the attendee.
Yes, for instruments. Is there any redundancy? Do you have anything? Wow, that's a lot of things in one question. Let's see. So sensitivity of the instruments does make a difference. When the scientists are trying to figure out what they want to learn about Europa, that kind of folds into what kind of resolutions, for example, is required for the instruments to be able to produce. We think about things like how accurately the spacecraft has to be able to point so that the instruments can get the data that they need at the right level of accuracy to do their science data. What backup mechanisms are in place? We have a lot of primary and backup components, like we have 2 star trackers, we have 2 IMUs, we have 4 reaction wheels. There are a lot of things so that if a specific component fails, the spacecraft can swap to the other one and keep going. So yes, that's redundancy in systems. Do we have something in place to avoid space debris? So I think about it this way. We do have to keep in mind micrometeoroids, and there are things in place that are intended to protect us against the environment that we expect to see. So yes, for that. We already have lots of satellites in space, maybe not millions, but there are lots. Do you employ formal verification techniques for hardware and software design? Yes. I'm not sure what the lots of satellites ones mean, but we do use verification techniques. There are a lot of specific ways we go about checking out the software, specific ways we go about checking out the hardware. There are things that we need to tailor our test and analysis program for each new spacecraft, because their objectives are a little bit different, their requirements are a little bit different, the hardware is a little bit different. So you have this combination of standard types of things plus special things for your mission folded together.
Oh, actually, Tracy, you got me so pumped up. I'm so excited right now. You mentioned about this mission will also observe the other moons, right?
Yes,
so,
it'll make a couple of flybys of
wow.
I think Ganymede and Callisto. Yeah, and some of that is just because I might be wrong about this. I have to go check with our mission design guys. But in order to set up the spacecraft to do all of the flybys in the altitude and the timing that we want for Europa, I think we have to use some gravity assist from a couple of the other moons too.
Yeah, but for those, it's just like imaging, or they also do some kind of scientific detection.
Yeah, we'll take all the data with our whole suite of instruments for every single one of them. Yeah.
Wow, see, I'm so pumped up. You know, this is so exciting. You know, not just Europa, and also Callisto, Ganymede. This very
it is going to be pretty great.
Yeah, it's crazy. This is really fun stuff you're doing. You know, really cool. So I just want to remind anyone, do you have any questions? This is a great opportunity. Tracy is, you know, as you said, very dynamic, very very, a dynamic speaker. So it's a great opportunity. It's very knowledgeable as well. So if you want to say something, ask your question, you can raise your hand, get muted, or type in Q&A.
Well, I think the next speaker was supposed to start at
45.
Okay, so there's still another 10 minutes unless people need a bio break.
Yeah, thank you. Let's see. Yeah, okay.
I must have talked too fast through my slides.
Oh, I see. Oh, you mean you want to show your last slides, or?
Oh, no. I said I must have talked too fast through my slides and left lots of time for Q&A. You've been asking great questions though, Ken. Thanks, I appreciate that.
Well, I actually answer that sometimes I do, because a different speaker, different style, some speakers that prefer to, interactive exchange with the speaker, the attendee, and some speaker has tons of deck, of slides, and almost no time for questions. So, sometimes I ask some question to make sure, the interaction could be, and then sometimes actually some of our attendees are a little bit shy, they kind of, sometimes they get warm up a little bit, after the kind of fun question to break the ice, then, they start to get heated up. So, but basically, I think this mission ultra exciting, is coming soon, and is really very, very important to carry out those, for the moons and more Jupiter system. It's just amazing, and those for the also historic meaning, because these are the Galileo moons. Yeah, it has kind of historic meaning. When you can explore them in more details.
Yeah,
a lot of great meaning. If you think about the difficulty Galileo went through, he was almost kind of the church, Vatican Church, didn't like him. So he thinks it's a heresy. What do you mean? Earth move around the sun. It's crazy. And I heard the story was actually very fascinating, because actually the Pope at that time, the Pope of Vatican, was his childhood best friend.
Huh.
Yeah. So the Pope asked him. Yeah, actually the story was actually, if the Pope was not his best friend, he would probably have been put on fire, been burned. Yeah.
Wow.
But because the Pope was his childhood buddy, so the Pope has telling him multiple times, tone down, just don't talk so loud, and he will try to cover him. But Galileo would not stop. He just said, this is truth. He just kept going.
Wow.
And it got so bad, and the Pope had to put him, house prison. But he, a lot of people want to burn him, heresy, something like that. But I think Pope was his buddy, so the Pope would not do that. So it was very.
I had not heard that. Wow.
Yeah, I heard that. It's really amazing. So I think that this journey, as you say, Europa Clipper, Juno, has very deep meaning for human, this reasoning and scientific exploration, because Galileo, perseverance of Galileo, that's come to all this.
I agree. And one of the things that I think is really cool is that a lot of us who work on missions like this, and the people who help us decide how to connect what we're doing with the public, they like to reach back and tell the stories of how Galileo and people were involved. And you guys might not know this, but on Juno, there's these little Lego figurines made of aluminum. And one of them is Galileo holding his telescope, which is really cool, because we're trying to give some props to Galileo for the discoveries that he made. And there's also a little plaque that has an etching of it that is a page from his notebook when he was taking notes as he was discovering the Galilean satellites. That is like an aluminum thing that's etched and is on the spacecraft body too, that is now out there at Jupiter, which is really cool. It'd be nice if there was somehow we could go back in time and tell him that was going to happen. He'd be super excited and happy about it.
Yeah, he's something, because it's one person against all the church system, and he would not back off. He could have been put to death, but he just well, anyway. I think, sorry for that, but I think there's a few more questions. Would you be interested in
Oh, sure. I see this question in the chat. How big are the fault trees that get developed for the design? Yeah, I don't actually remember how big the Europa one was, but when I think about the one for Juno, we had one for launch, we had one for orbit insertion. And I know on MRO, when I did them, we had one for aerobraking. And I think that you could get to the point where on any one thing like launch, you might have like 800 different things out there on the edges of the leaves that you then have to go figure out what to do about. And then you'd have another one for the different major phases. So that's a good question though. I have to go look and see how many are out there for the Europa fault tree. But yeah, you can imagine it's kind of an incredible amount of work to then go figure out what to do about each one of those. And that's like the fault trees are the top-down way of looking at it. And then there's the FMICAs, which are the failure mode effects and criticality analysis, where you're looking at for each individual component, if something inside that component fails, what happens and what are its symptoms. And that's the very like grassroots bottoms up. And then you want to make sure that those two things meet in the middle and you're taking care of all the different things that can happen across all of your hardware and software on a spacecraft.
Yeah, I think we have one time for one more question. So Santosh, Mr. Santosh Kumar raised hand. So Santosh, do you want to unmute yourself? That's the last question for Tracy.
Yeah, can you guys hear me?
Yes.
Yeah.
Okay, cool. I was just going to comment on Galileo. I think the issue with Galileo was that the Catholic Church at the time had an Earth-centric view of the universe that believed that everything orbited around the Earth as opposed to the sun, and the sun orbiting, of course, around Sagittarius A star in the galaxy and so forth. And so, because he conflicted that view, he was risking excommunication from the Catholic Church. But the Church has, of course, since changed its view, and now they revere Galileo. So that's an important part to notice, that they now fully embrace him. So it just took some time. But I believe it was Apollo 15 or 16. I think it was 15. Dave Scott actually did a tribute to Galileo, if you guys famously remember, on the surface of the moon. Although I'm not sure if he got himself confused with Newton, but basically he wanted to demonstrate that in the absence of an atmosphere, that gravity affects all objects equally. And so he dropped a hammer and a feather and showed in absence of atmosphere, they both hit the deck, the surface of the moon, at the same exact time, and that was his tribute to Galileo.
Nice.
Yeah, that's why Galileo is so highly regarded and respected. Because he not only had the knowledge, he has the right sense of the human reasoning and scientific principle, and he had the courage. That's something really amazing, and that's also our speaker Tracy has. Let's say is working on this. She's working on this, and for expanding the human vision and also the human the scientific scope of the understanding of the solar system. So thank you so much, Tracy.
There was actually one more tidbit I wanted to add, that it was kind of interesting that the Catholic Church went from that kind of a view to the whole idea of the Big Bang and expanding universe. It was actually a Catholic priest. I can't remember. I can't remember the guy's name. It begins with an M. If you look it up online, you'll find it. Who was the biggest proponent of that view of the universe, that we have an expanding universe and the Big Bang and all that. And who'd have thought that they would go from, the view they had back then to now embracing the Big Bang. So they've made quite a swing from one to the other, one side to the other in terms of views.
Yeah. Not know that either.
Yeah. Okay. Thank you so much, Tracy. This is fantastic. Stay in touch.
My pleasure. Thanks for having me.
Oh, our honor. Thank you so much. All right. So I think our next speaker, Tanja, Ms. Schroeder is here. Okay, so let me do this. So are you ready?
Hi.
Yeah, you're ready. Okay, great.
Hello.
Hello, wonderful. Okay, so I'll just say a few words.
Okay.
So our speaker today is for us is the Southern California Recruitment Coordinator for the famous INCOPS STEM Teachers Program. Basically, this program is to provide success, the STEM access and the closest achievement gaps for students in low-income communities by supporting industry professionals becoming teachers. INCOPS' vision is to realize a day where all students, regardless of socioeconomic status, are inspired and prepared to pursue their dreams. Through her work in COPES, Tanja is constantly inspired by the industry professionals, for their knowledge and sharing their expertise with the next generation. So let's hear more the exciting, efforts from Tanja. So welcome.
Hi, thank you so much for having me. I have a few slides to share, so I'm going to share my screen quickly. Let's see, play from start. All right. So thank you again for having me. I'm just going to share a little bit more information about Encore STEM Teachers Program. And again, my name is Tanja Schroeder, and I am the Southern California Recruitment Coordinator. So thank you so much for that introduction. So at Encore, we are STEM professionals providing high quality education to close achievement gaps for students in low income communities. And so the next few slides will just tell you a little bit about why we exist. But here, for example, since 2014, you can see that in the state of California, the schools have had a teacher shortage crisis. And so these two lines that you can see, the blue is the estimated new teacher hires that will be needed. And then the red is the amount of credentials that are being issued. And so those two lines are going in opposite directions. And so it just kind of shows the teacher shortage that's happening and that has been happening for years. And what happens is our students are the people affected by this shortage. So in the state of California, only 40% of students are meeting or exceeding their math standards. And when you look at that statistic by demographics, you can see that the students that are affected the most are African American and Latino and Hispanic communities. They are at the bottom of this graph. And so again, what Encore is doing is we're trying to change these statistics by working with STEM industry professionals who are transitioning to becoming teachers. And we do this because STEM industry professionals bring real world expertise and relevant STEM education to the students who need it the most. Encore has two opportunities at the moment that can make an impact in education. So the first one, as you know, is the Teaching Fellowship. This is a pathway to becoming a full-time teacher. So this would be for someone who is talking about a career change, or maybe they're approaching retirement and they're considering to teach for a few years before fully retiring. We work specifically with high need schools, which are the schools that have higher communities of the populations mentioned previously. And then we do this with a flexible timeline. So someone who becomes a teaching fellow through Encore has about a year to 3 years to transition into teaching. So we try to accommodate people depending on what pathway they are on. And we do this currently in the state of California and in Colorado. We are looking to expand and create more partnerships in other states, as this is a need in more places, but at the moment we're just in California and Colorado. And then we have a volunteer opportunity. So for people who want to make an impact in education, but not necessarily transition into a full-time teaching position, we have a virtual math tutoring opportunity. Again, we're working with high need schools, so a lot of the similar schools as the fellowship. This is all volunteer run. So our STEMx tutors are volunteering for about 2 hours a week throughout the duration of a semester. And they're partnered with one student and they do one-on-one tutoring sessions. This is a very flexible program, as the tutor and the students can pick a time that works the best for them. So we have tutors who are meeting their students on virtually on Sunday mornings or Wednesday evenings or their Monday afternoon lunch break. So it's a really flexible program. And it's also a national program because it's virtual. We're able to have volunteers from all over the United States. So that's been really great. We have volunteers from about maybe 30 different states joining us for this program. So I just want to share a video that shadows the two fellows, and they really speak about Encore the best and just what it means to them to be able to introduce their STEM industry experience into the classroom and share it with the students.
I grew up in the South Bronx. Didn't have any interest in aviation or aerospace until I met my 7th grade teacher who happened to be a pilot, and realized, like, I want to be like Rough Garden, because he flew a Cessna on the weekends. Prior to becoming a teacher, I was the director of operations for the U-2 aircraft, responsible for mod, maintenance, and flight operation.
They always are surprised when I say that, oh yeah, I used to be an architect or an engineer. My daughter was in middle school when I realized that students don't like math and they don't really know math either, and it's not even their fault. So that's when I decided that, oh, I always wanted to be a teacher. I always liked teaching math, so maybe I should look into getting a career in teaching.
I've worked on some of the most amazing aircraft that's out there. That satisfaction equals the satisfaction of a student who comes into class with no awareness for aerospace engineering, but by halfway through, they are 110% engaged, and you can see them embracing that knowledge.
So I think if you just walk into an Encore classroom, into our aerospace engineering classroom with Julian Lewis, you can feel a difference. It's palpable. And I think the difference is that rich body of real world experiences help students understand, to really see their own future. And Julian brings that every day.
Oftentimes I'll walk in and I'll find him putting up pictures of past projects that he personally has worked on in his professional career and drawing the students into what it must have been like for him to be working both in the team and on his own in the real workplace.
So when I first thought, well, I'm gonna look into how I could become a teacher, I did a lot of research and I was like, yes, I don't have to do this on my own. I can have somebody help me figure out how to get a credential, help me figure out if I would be a good teacher.
Encore was very instrumental. That was the roadmap to getting me into the classroom. It's very rewarding. At the end of the day, what's going to be your legacy? What have you impacted? And as I share my experience, they are realizing that I too can do that. They will be better individuals because I'm here. And that keeps me getting up. I truly enjoy it.
All right, so I hope that that helped everyone kind of see the essence of Encore and just how it feels to be a fellow and to be able to give back your experience to the students and make an impact in their lives. And then just to touch a little bit on the STEMx tutoring program, I just want to share about our students. So on the screen, you can see the demographic of the students that we're working with. Right now, we're partnered with Alliance MIT in San Fernando Valley and Accelerated Schools in Los Angeles. We are looking to create more partnerships. So right now, we're just in Los Angeles with the STEMx tutoring. However, we are looking to expand to have partnerships in schools all throughout California and ideally in other states as well. But right now we're working with middle school students, grades 6 to 8. And then the courses that they are in is geometry, pre-algebra, and algebra 1. And the unique thing about this STEMx tutoring program is that we have access to a site coordinator at the school, and we have access to the student's curriculum online. So as a tutor, you're coming in with awareness of what the student is what the student is doing in class, and what their lessons are like, how they're doing on their homework, how they're doing on their assignments. And you can exchange notes back and forth related to the tutoring sessions with the site coordinator. And so we really do want to make sure that the time spent tutoring the students is being tracked and that we can see an impact at the end of the semester. I also do want to add that there is no formal curriculum that we're providing. So every tutor that comes into this program has the opportunity to express their own creativity when they're working with the student, which is really cool as well. All right, so thank you for taking a little bit of time to hear about Encore and the different ways that we're trying to make an impact in education. I hope that you enjoyed hearing about Encore a little bit. And if you do have any questions for me or want to get in touch or would like some more information, I did provide my email address right here. So please feel free to share that with someone that you know who might be interested in this program, or also reach out to me. And there's our website as well for more information. Thank you so much for your time.
Great, thank you so much. And the education is very, very important part for aerospace. And we're so happy to, to have you and in Corps, showing up, tell us what you were doing. That's a great program. Before anybody has any question, we still have a few minutes. Our next speaker is here, but just a quick question. You mentioned about those teacher and accelerator school. Are these for it's more you provide the school to those teacher to those schools, or is kind of after school program?
For the tutoring program, it's kind of like an after-school program, but since it's virtual, it's very flexible as far as what time the tutoring sessions can be scheduled at. But for the fellowship, it would be someone becoming a full-time teacher. So having a classroom of their own and being there on campus, or right now virtually.
Yeah, and you're absolutely right. You know, a lot of aerospace people, they're passionate. You know, you're absolutely right. I feel the same thing. They're passionate. They want to share, and they want to, do it. Some do it by themselves, individual efforts. But you are putting them together, give them some training. I think that's just great. But for what do you expect from those people? Because if people still at work, their schedule might not be flexible. For retirees, they might have more flexible time. So how did you kind of help out? Do you also, if somebody retire, are they okay to work with the program, or you?
Oh yeah, definitely. Yeah, this program is very flexible. So if someone were interested in pursuing teaching, they can contact us and we can talk to them a little bit more about what that process entails. But it is a very flexible fellowship. And so most of the people most of our fellows actually still have a full-time job in the industry, and they know that maybe in a few years they're going to be retiring. So this is an opportunity for them to kind of dip their toes in teaching and get their teaching credential and kind of look into the ins and outs, so that as soon as they retire in 2 to 3 years, they're able to jump right into a classroom and become that full-time teacher. So it is a very flexible program. And then we do have a lot of fellows who come in to the program who, especially now with the pandemic, kind of find themselves in a place where they're open to trying something new. And then they go through the fellowship full-time and become full-time teachers as soon as possible. So we have people on all ends of the spectrum as far as how soon they're willing to get into teaching.
I see. All right. So yeah, this is really amazing. I think there is I don't know if you can say, but Basic Pratik is asking, do you require licensing? Can you see it?
Oh yeah, so in the state of California, everybody needs to have a teaching credential. In Denver, or in Colorado, it's a little bit different. They do require a credential as well. So every state that we're working in, we provide that support for everyone to be able to navigate the schooling, all the paperwork and resources and coursework that they need. It can be a little bit confusing. And so a lot of our fellows have told us that they've thought about teaching many times, and sometimes they'll look it up, but then they get so much information that they just give up on it or decide that they'll do it later. And so that's exactly what Encore is here for. When someone comes into our program, the very first step for them is that they have a welcome call with someone on the program team, and they've all been teachers or principals before, so they know exactly how to navigate the school system. And so they kind of work with each individual like a consultant and create that pathway and that timeline and set those milestones and those target goals for each fellow individually.
I think this is great because it provides opportunity and a platform for aerospace professionals, to share their passion, to help the community, and the next generation. So it's really so stay in touch, stay in touch. So anytime, come back again, to tell people what your progress and what you offer. That's amazing. Yeah,
Definitely.
thank you so much.
Thank you so much. Thank you for having me, everybody.
Yeah, very exciting. Thank you so much.
Bye.
Bye. Thank you. All right, so our next speaker is the keynote speaker for the afternoon. To start the kick off the afternoon session. Mr. Daniel, I'm sorry, this is the wrong one. I clicked too fast. So it should be this. Okay, so Mr. Stephen Isley is our keynote speaker right now, and he's the vice president at Virgin Orbit. It's very, very exciting. He's an executive with over 13 years of international business experience managing multi-million-dollar companies and startups across numerous industry and markets, includes the aerospace and defense, government, commercial industries. commercial space exploration and satellites, film, fashion, startups, and nonprofit organization. It's very multi-talented, and this is what people need in aerospace right now, especially with the new space. He has expertise in business development, marketing, e-commerce, branding, sponsorship, acquisition, and development, global PR, consulting, business strategy, and operations management. It's let's see. As he has a lot of aerospace executive experiences. He was also the corporate advisor, also U.S. government relations. He was with NASA, NOAA, many places, and also Capitol Hill's advocate in the film industry. And he also raised multi-millions, for capital formation. And he's very media savvy. So we have the great pleasure and honor to have Mr. Stephen Eisele, the Vice President of Virgin Orbit, for the keynote speaker today. So thank you so much, Mr. Eisele.
Okay, thank you so much for that introduction. I don't get my bio read to me very often, so I appreciate it very much. It's really great to be here with everybody. I'm really, excited to talk to you and, provide you a little bit of an overview of what Virgin Orbit is doing, but also kind of what is the broader impact in the new space market, in particular for entrepreneurial companies, but also how is it impacting the broader space economies. So I have a presentation that I'd like to share, and I will try to keep it light, excuse me, and make this as interactive as possible. So I'd like to take maybe the first half hour to provide you a little bit of insight into our world, and then talk to you guys about sort of trends that I'm seeing in the market and where things are heading. And so please indulge me, and really appreciate you all listening today. So, first off, I am the Vice President of Virgin Orbit. I'm in charge of all commercial, international, civil government, sales, business development strategy, and also work on our spaceport network. Virgin Orbit, of course, is an air launch system, and you see a lot of fun adjectives. I don't think our marketing team could settle on one. So we have a lot of good adjectives there that really describe the system, but it is truly unique. And I think part of this trend of like change and different types of mission operations that will enable the new space market. So what I'd like to do today is just give you a little bit of overview of who we are. And again, this isn't going to be a sales pitch. I do just want to kind of share our unique technology, and then give you an update on our launch mission. So we have had one, successful mission to space and orbit, and we're planning on many more coming down the pipe. And in fact, the next one in a few probably a few weeks from now, less than 2 months, let's say. And then kind of what's next and what the market outlook looks like, and then love to open up to questions. So I will be very cognizant of the time and make sure that it doesn't sound like I'm droning on. So, obviously Virgin Orbit, maybe for those, we are part of the Virgin Group, and this is our founder, really cool guy. He is, very engaged. He visits the team, of course, pre-COVID, on a regular basis, and it's just really inspiring. I mean, his goals in life were really to set forth the best customer experience in all the different industries that he put forward, and to do it unique and also in a company culture friendly kind of way. So Richard is been really a force for us and helping us kind of navigate through these troubling times, and as part of the vision for what this setup is. So what you see here is what Virgin Orbit is offering. This is called our Launcher One system. It is an air launch flying platform, if you will, to deliver rockets and satellites in particular to low Earth orbit and beyond. So our system consists of a 747-400 plane, which you see here, which is aptly named Cosmic Girl, came out of the Virgin Atlantic Fleet. And she was modified we took out all the seats and made some modifications to the wing, of course, built a pylon in order to hold the rocket. The rocket is a 2-stage rocket, liquid, oxygen, kerosene rocket. So the rocket itself, it uses proven technology. It's nothing too new, nothing, everything that still falls within the rocket equation. But certainly the magic is in the mobility. And I will talk to you a little bit about that in a minute. But as you can see, as an air launch system, we have a lot of flexibility. So we are really driving to be not only just a low-cost provider, but really a launch on demand system. And that system can be called up in short time frame. In the future, we hope as quickly as 24 hours. And more importantly, though, it can really deliver satellites and payloads to different orbits. So you can fly to different azimuths where you can drop the rocket and effectively deliver the satellite to any orbit, low inclination to high, polar, fly west, fly east, a lot of different things that you can do. So it's pretty cool. The thing you don't see here, which I'll get to in a minute, is we have a mobile ground equipment. And the mobile ground equipment is really all we need to support our full launch operations. We don't have launch pads. We need a runway, but that is the main, the main item we need to be able to launch from a specific spaceport. And finally, we're looking at doing between 300, 500 kilograms to low Earth orbit and beyond. And I will get to the beyond a little later. So just for fun, I kind of like this because it shows you sort of the headlines from Aviation Week over the last 4 years. Notably, March 2017 was, in fact, when Virgin Orbit was founded, and sort of gives you an idea of how far you come if you go from left to right and just seeing the evolution of our system. So, of course, being founded in 2017, we did already start development under Virgin Galactic. So the name of the company was switched over to Virgin Orbit. But importantly, that does mark our Founders Day, if you will. And then through the last few years, we've been really ramping up, of course, testing, development, and getting this rocket operational. We had our first launch in May of 2020, so we could have had the headline in 2020. That one was a success in the sense that it tested out the air launch system. And it was not a full success in the sense that we didn't make it to orbit, but everything we learned there really helped us and informed the process for our successful launch in January 2021, which was very exciting. And I'll tell you a little bit about that day in a minute. So why air launch? Like, what makes us differentiated? What makes us cool? I think it's cool. So for a few different reasons, Virgin Orbit as an air launch system, why did we choose air launch? Because we really wanted to put something to the market that was truly differentiated and that could really offer a different operational mode of conducting missions. So the mobility factor is, of course, obvious, but having an air launch system, we are able to branch around to not just be to fixed launch sites, but we can go to really any spaceport that can accommodate a 747. And I'll show you a map, our spaceport map, in a minute. More importantly, though, an air launch system really enables different activities. So because of the nature of how we launch and the preparations have to be done, we can really tighten the window a lot faster than a ground launch vehicle. So our cadence can be incredibly high. For example, we could turn around 2 launches in a day if that were a requirement. It takes about 8 to 12 hours right now for us to fully operate, load, and take off the plane. So in theory, we could do 2. I'm not suggesting we're there quite yet, but that is an operational capability that we think one day we can achieve. In the short term, though, launching successful missions a few days apart, a couple weeks apart, is no problem. And really, it's just going to be about coming down the learning curve and gaining that kind of knowledge, how to expedite the operations while keeping it safe. The other part of, and this is part of the new space era, of course, I mean, you have to be able to, back in the day, you would wait in the queue in order to launch, and schedules were unpredictable, and you never knew when you could go off and so forth. I mean, I still remember my days when I was working at Surrey Satellite, and I think we waited 3 years for one particular launch, and that, and of course that doesn't close the business case. That doesn't keep things moving. And so for launch to be there for the customer base, the consumer base, we have to be able to launch on demand, launch rapidly. We have to be flexible in the manifest. So if one customer maybe delays, we might be able to move another rocket, to the left, so to speak, and push up the schedule. And the way we do that is we've invested heavily into our factory. So we use 3D printing, we have additive subtractive machining. We, of course, are streamlining our flow. Most of what we do is vertically integrated. I'd say over 90%. And that way it allows us to keep kind of the quality in-house and just kind of keep things moving at our pace. So we do build to rate rather than to mission, meaning we will be doing, upwards of 20 or more launches, developing over 20 launches a year. And that rate, of course, will help assist the new space market and the economy, whether it's for national security purpose, commercial, civil government purposes, to have launches essentially on demand or very tight schedules as they may be required than in the past. So we're really excited to provide sort of that. And of course, that makes us stand out in the crowd. I mean, I like this image kind of because it just shows that, rocket technology hasn't really changed that much in the last, 50 to 60 years. And certainly there have been aero launch systems or at least one for satellite launches in the past. But in an era where business cases are really driving the new space economy and the our way of life depending so much on satellite technology and staying connected, we need to think a little differently about how we deliver payloads to orbit, how quickly we can turn around schedules, how we prepare for anomalies and infant mortality of satellite constellations, or how we look at augmentation of different constellations and things like that. And then of course we want to be good stewards, like how do we mitigate against orbital debris? How do we, all these kinds of questions, I think, have to be addressed by having a more responsive and flexible launch system. And certainly that is part of where we think, we can really provide that benefit. And so this just gives a brief example, comparison between ground launch and mobile air launch. And I think most of you can kind of probably see them from, on your own, but nonetheless, we see these as being some benefits. All right, so now that you know a little bit about our launch system, where are we going? How does this kind of all fit together? So having an air launch system really, I think, is going to give us some key strategic advantages. Obviously, as I mentioned up front, being able to reach any orbit. So you're a customer, you're a partner, you want to go to 0 degrees, you want to go to high inclination, certainly we can do that. But it is about assured access. So many, strategies coming out of governments. The UK has set up their own space command recently. Others in Europe and South America, Asia, and so on are really taking note. I'm noticing governments in particular are picking up a lot of what the commercial, launch satellite solutions options are, and they're starting to change the strategy. They're starting to change the dialogue. And this is not, I would say this is a growth. This is really more organic coming out of what the new space commercial industry has been able to provide the market and to drive. And so it's pretty exciting to see national strategies incorporating things like assured access and recognizing the need that space is no longer just for science exploration or maybe telecom and geo, but rather there's so many different opportunities that are hitting so many different market segments, not just national security and telecom, of course, but as agriculture, maritime, oil and gas, environmental, and on and on and on. Where we can really leverage those space assets. And I'll talk a little bit of some of those examples later, but that assured access, we see that as being absolutely necessary. And I touched on that. But then the third point, which might be a little different and how we think different, is we do see ourselves as a global space solution. I think differentiating ourselves is important. As some of you may know, there are actually over 100 declared new space rocket companies out there. That's it's amazing. That's like more rockets per satellite company out there practically. But of course, a lot of them are still, what I call paper rockets. They're still PowerPoint presentations or their ideas, but certainly quite a few of them are coming to the fore and are looking like they will be, very successful and very capable launch systems. So, with that in mind, then, like as a company like Virgin Orbit, I have to think about how we can set ourselves apart. And in addition to kind of the reasons that we mentioned prior, there's this idea of, can we help stimulate markets? Can we help stimulate new space ecosystems around the world? And that is this idea of potentially creating spacefaring nations. Given that we can pretty much pick up and go with our entire launch system, and I'll explain how that works in a minute, we can, set up shop in a spaceport or an airport or an Air Force base practically around the world. There's some qualifications which we'll get into that are required, but nonetheless, if you can have a spaceport in your backyard, then you can start really changing how a region or a country looks at the space market. You will obviously be probably investing, doing things like small space clusters, having stimulating, the ecosystems, the local ecosystems. A lot of those don't need a lot of capital to start up. I mean, when governments throw money at launch, it sounds like a lot of money. It could be 10, 20, $50 million. But the reality is I would venture to say all launch companies will require significantly more funding than that. And that is, of course, a challenge to raise when it's not necessarily the highest margin, industry. So where I think the money can be made and where, and also the investment, the most impactful is on things like data stream, downstream applications. So the data analytics markets, yes, the small satellite market, but in bundling some of those capabilities together. And so that is really where I think a lot of this is going, and where future nations would be benefit to support. So here's a little bit of a map of kind of like where we are currently, and I'll share some insight into where we're looking at going next. The three American flags represent our US footprint. So we have a spaceport in California, in Mojave, where we launch and operate out of primarily. Our company is based in Los Angeles and Long Beach, so it's only a 2-hour drive, so that makes it really convenient. The flag on the East Coast, that's Florida, so the shuttle landing facility we plan on offering that as a backup. And then the flag you see in the Pacific, that's Guam, and that is a partnership with the US Air Force Base called Anderson Air Force Base, which we plan on using as a blueprint to be able to launch from almost any Air Force base that the US or maybe the Five Eyes allies have around the globe. And so you can really start building out a spaceport network, and that has some significant impact on how we launch and how we can do business in this market. The other international flags you see, so the UK, we have a partnership with the UK Space Agency to launch from Cornwall, and in Japan, that is Spaceport Oita in the southeastern part of Japan with the local government there. And we really, Japan and UK, as you all probably know, have really burgeoning small satellite and new space economies, but they don't have a, I would say, dedicated small launcher vehicle company. Obviously, Japan has launch capability, but the flexibility that this affords and the mass class of the rocket being a smaller rocket just opens the aperture for the new space economy there. And they are some of the strongest ones. And those were why we, in part targeted those regions. But this opens up then not only the space access to space for the UK, but it will do it for the broader European region. We see the same opportunity in Japan to help broaden access to a dedicated launch for small satellites in Asia. Italy is actually more of a Virgin Galactic potential launch place, but Virgin Galactic's, which are sister companies, they do space tourism. Their requirements for runways and spaceports are actually very similar to ours. So it is something that we could follow them in, or they could follow us in. So I just noted that because that was made public. But you're looking around the world and you're saying, well, there's no Southern Hemisphere launch. We are looking at a few places in the Southern Hemisphere. Haven't made any announcements there yet, but we will in the future. And now, as you start looking, you start seeing a distributed map. You see a global map, and this will really open the aperture to provide regional launch, but it also does some unique things. So, for example, you have if you have a large constellation that you need to get populated really quickly into different planes, different RANs, and so on. If we were to launch, let's say, simultaneously from 2 sites. Maybe a US site and maybe a Southern Hemisphere site, or Japan, UK, you can actually populate a constellation much faster because you can direct inject the satellites into actually the right orbit, instantaneously, essentially, by leveraging the different spaceports. So that could be a really unique feature when you start thinking of responsive launch constructs. Finally, the only other thing I want to mention here is that You know, the spaceport network, we're looking at probably having what we'd say hubs. So the flags you see will have some kind of permanent presence. It could be just ground equipment, maybe even a plane. And I should mention, we have one plane currently, but are looking at growing it into possibly a fleet, definitely more than one. And they could be permanently potentially stationed at some of these other spaceports. So you will have these spaceports, which will be like regional hubs, but then other spaceports around the world. You've heard there are ones in Norway and Sweden. There's some in Australia, and they may have just a runway and an easy access footprint. And so the ground equipment that you see in that picture above, plus the plane, that's what we would then transport. We could bring it in for a campaign, or we could leave something, there, like maybe just the ground equipment. So there's a lot of flexible ways to do this. And you start, I think, imagining now, like some cool things that that can happen with kind of this global network. So this is just, I kind of touched on this, and it really is just demonstrating that things are just mobile, flexible, and ready to go. And the top two left pictures, you can see some pictures inside our factory floor. We have a lot of ship sets, the rocket. So at any given time, there'll be 6 to 10 ship sets. Right now there's 6. Of course, we're ramping up, carefully and slowly, but we're not quite there yet. On the right, you see our, the second from right, sorry, you see our mobile clean room trailer, and I'll show you a picture of the inside, but we can take basically an encapsulated fairing and transport that in a clean room environment, and the actual mating of the rocket and the fairing happens right on the basically on the hammerhead where the plane is stationed right before the launch. So it's pretty cool how quickly we can roll that up from any facility, your facility, our facility, another facility, and roll it up, mate it with the rocket, and then we attach the rocket to the underside of the plane. And then on the bottom, you get the point. The plane is mobile. It's your flying launch pad, and it can access lots of different spaceports, as I mentioned. Here's a quick shot of our clean room. The one on the left is in Long Beach, and the one on the right, you see that same picture of the mobile clean room, and there you can get a better shot of the rocket integrating with the payload, and you see the inside of the mobile clean room. It's got a crane. A dolly will, drive the fairing in there, and then the mating happens. And there's a sleeve to ensure that it always stays in a clean environment, even until it's latched onto the underside of the plane. And then purged air is provided throughout to the payload up until the drop. So you actually get a longer sequence of clean air than you would with a ground launch system. And this is, I think, the last slide I have kind of for this section. And this is just pulling it all together. So we think of a global launch solution. You think about the cadence and everything we're building. It's about responsive launch. And this is really what we want to offer the market. We are building, incorporating a program we call Rocket Ready. And Rocket Ready is about having essentially a spare rocket on the factory floor at all time that doesn't have an assigned tail number. And basically, if for a national security mission or maybe a commercial satellite constellation has an anomaly on orbit, and it needs a quick replacement, so you need a direct inject responsive replacement, you have a rocket ready. Other missions you see kind of here is just looking at doing potential partnerships with the Air Force, where they may have their own dedicated systems, all the way to, as I talked to earlier, kind of stimulating local ecosystems by having a more permanent presence kind of stationed around the world. You'll notice in the center right, there's a picture of Mars and Virgin Orbit. So we're also looking at doing missions beyond LEO. That includes MEO, GEO, cislunar, Mars, asteroids, beyond. We have a partnership actually with a consortium out of Poland, where they're looking at doing 3 Mars missions. And the way we do that is we have a 3rd stage option. So I didn't mention that up top, but with the 3rd stage, we can then, certainly get payloads, between 50 and maybe almost 200 kilograms to GEO and beyond. So it's pretty exciting to be kind of diversifying in that way. All right. So, and I'm promising I will stay on track. So I will just take the next 5 minutes to give you some snapshots from our first launch and just tell you about that experience. And then I'm going to go away from slides and just tell you a little bit about where I think the market is heading and open it up to questions. So trying to stay on track here. All right, so let's talk a little bit about Launch Demo 2. And Launch Demo 2, as is noted, was our second launch demonstration. Our first launch demo happened in May of 2020, and I call it a success. It wasn't a complete success because we didn't make it to orbit, but we accomplished a lot. And it took us about 6 months to turn it around from that launch to this next launch, which is pretty fast, I think. And for those who are wondering, on the first launch, we had a high pressure LOX feed line rupture. And the interesting thing was, part of that was, it just shows how important testing, like actually going through a demonstration or a Pathfinder demo, is so important, because there's only so much you can do on the ground before, that you can't quite simulate with an air launch system, especially the drop itself and how that, shakes things. I mean, we did do many drop tests and everything of that nature, but nonetheless, just getting through some of that, our models couldn't predict everything. And that first launch, though, I would say really turned the page for us in terms of shoring up the holes that our models had, especially for things like getting right up to max Q and doing the drop on air ignition and everything else. So I'll just tell you about the day. Hey, it was flawless. I mean, that's not honestly an exaggeration. Clearly, we got a lot of good data, and we will take that data and we will make improvements like any good rocket company will. But it was an amazing day. This just captures a little bit of the drop with the in-air ignition, and then you see the stage step, and then the fairing, was deployed, and you see the satellites exposed in space. So the money shot in space, if you will. So it was a flawless launch. I got some funny anecdotes I'll tell you, and I'll just kind of take you through the day. So, I mean, what was the mission? First off, it was a NASA mission, part of the VCLS program that had 10 satellites on board. And pleased to say that every single satellite was dropped into their exact orbit, exact inclination. It was awesome. I mean, plus or minus within the wiggle room that we have in our user's guide, but the orbit was a little over 500 kilometers to 60.7 degrees, and we hit like 60.69, for some of them, 60.7 for the others. So it was pretty amazing to see the accuracy that we're also able to deliver on the first flight. So this is the punchline up front. Made it to space, happy satellites, made it into orbit. And, that's not always a given. I mean, it's a new world. So it was definitely an interesting day. So let me take you through the day a little bit, because air launch is different than ground launch. And I think this is of interest. Here's an overhead view of that day on launch preparation. So the day really started about 4 a.m. for the ground launch crew. We call them the Wolf Pack. And that is really just making sure that all systems are nominal. None of the sensors and things that we have attached to the plane and the rocket are giving us any, red flags. And, so they do all the checkouts and everything else. About 4 hours prior to launch, they start the fueling process. And that takes, about 2 to 3 hours itself to fuel the rocket. And then about an hour prior to launch, you basically, the pilots they're in their the ready room where they're doing the pre-flight checks. They board the plane, they go through their checklist. That takes about 30 minutes. And then if everything is good, they proceed to the taxiway and get ready for launch, so for takeoff. And I will say this day, we got within 20 minutes of our predicted launch time. So that's pretty good. And that was even with, a lot of unknowns that were potentially happening. So here you can see, of course, the takeoff. So we take off like any other airplane, which is another advantage, at least for national security purposes. It's just another plane taking off. It's not off-gassing a lot of LOX. We're governed by the FAA, I'll point out. So we don't have the same range support requirements as the ground launch vehicles do. And that means that we have an FAA, basically civilian license that oversees our launch activity. And we use an autonomous flight safety system to ensure that, you know, if anything were to go awry, the rocket would safely, you know, shut down. And of course, we have a flight path that is meant to avoid flying over populated areas, almost any kind of populated area. And then we look at different trajectories, of course, our analysis, and then we drop over the ocean. So the ocean drop is key to safety and everything else. What you see on the right there is the racetrack. So you notice that racetrack formation. So that is part of the planned operations. We take off from Mojave. It takes about 40 minutes. We fly over Catalina Island, for those of you familiar with this area. And right past Catalina Island is St. Nicholas Island, and we start entering into the racetrack. I'll mention the plane is at about 30,000 feet, 10,000 meters. And she enters into the racetrack, and that is basically the staging area to get ready to do the launch itself, the air launch itself. Typically you can do one run through, and then on the second run through, the pilot's like, okay, all systems go, let's hit it. So when we go into the launch formation, the plane, and it's a big plane for those of you who remember the 747, it goes into about a 30-degree pitch maneuver. So it's pretty steep. I mean, it'd be a fun ride if you could be on the plane. And it drops the rocket. And that drop, which you saw in the previous pictures over there, the rocket drops for about 5 seconds before the first stage ignition occurs. And the plane kind of banks off to the right. And that is a safety maneuver, which they practiced for like 2 years, just this maneuver. And it was very successful. So that's just a little bit on the plane. So now you see the drop, and you have stage 1 ascent. Of course, demonstrating engine startup and controlled flight. That's St. Nicholas Island on the left. And if you see the contrail kind of off to the left, that's a chase plane. This picture obviously is coming actually from the Cosmic Girl. So I believe this is a camera we had installed kind of in one of the windows or the belly of the plane. And then you see the chase plane there, and the chase plane, our 24-year-old photographer got a ride in the back. It was a T-38, pretty wild ride. You know, on launch day, he had really the best view and was able to capture a lot of these cool pictures for us. So maybe one day I'll raffle off a ride on the chase plane. That could be kind of fun. And then, oh, sorry. Let's go forward, not backwards. And then, you know, one thing that was really interesting was it's really hard to model kind of the transonic flight of the rocket. And so that and the Max Q Alpha pull-up, where we have like the harshest environments also on the payload, was really the hardest. That I would say that was the most. That's the part where we all kind of held our breath during the Max Q, which is the pull-up, and then the transonic portion of it, because she doesn't go straight. The rocket doesn't go straight up like a ground launch. It sort of travels an upward trajectory horizontally over the curvature of the Earth, and that's how she achieves escape into space. And so, at any rate, here you see the stage SEP, and then second stage burn commences. And so that was very clean. And I'll tell you, throughout this process, I mean, you hear, so I was in Mojave, and because of COVID, we're all in like kind of separate rooms. And then there was a mission control where we had like 6 people that were socially distanced. And you just hear the walls, like, you know, rumble with excitement and cheering for every one of these like little, you know, stages. I mean, an engineer would tell you, hey, if we had just gotten that, you know, Max Q, and that would have been great. And the next one says, man, if we can just get stage SEP, that'll be great. And then, you know, you start raising the expectations, and as everything, you know, kind of went through, now we're holding our breath like, okay, stage 2 burn, let's go. So that was really exciting. Stage 2 burn happened. And then of course you had the fairing separation and exposure of the satellites, the NASA satellites on board. And that went great. And then, you know, as the stage 2 fires, there is a stage 2 engine cutoff. And then we circularize for about 30 minutes before the second stage relights, and then places the satellites into their final parking orbit. So there is, that was another test. And then of course, the funny thing I thought was, you know, as the business guy, I'm looking out for the customers and making sure their satellites get there. So I think a lot of the engineers were wiping the sweat off their brow just because the first stage SEP happened, the second stage relight, all these crazy milestones and key milestones occurred. And then some of these, and I remember when we were circularizing during that 30-minute window, you're kind of waiting. Somebody goes, I heard of the comm system. Somebody goes, wait, so what happens now? Like, oh, are we done? And of course it was an innocent kind of question, because operationally, I'm like, no, the payload, where are the satellites? Like, we have to deploy those. And the other thing was the CEP system, the dispensers were new. I mean, this was a new company, hadn't demonstrated it in space before, wasn't TRL-9. So getting that proof point, was another one. So then it was all on really that company to make sure that all the satellites separated appropriately, and they did. So it was really, really a cool day. And then, as one does, you get a champagne shower and, lots of bubbles. The guy holding the champagne bottle is Dan Hart, our CEO. And so needless to say, if you compare this launch with our first launch demo, it was a much better day. All right, and then next up, you can see our rocket here on the left. That is, it's in our final integration. It is even being fully integrated as we speak, and we'll be heading to the, we're going to be doing the payload integration in just a couple of weeks for the satellites, and then we're shipping off to Mojave. So probably in a little bit over a month or so, we're going to be doing our next launch. So we're pretty excited. I mean, late spring, the windows are still a little open because as a new system, we take a lot more precautions, and the wait between the first launch and this one, it normally wouldn't take that long. It's just because of all the new data we got and all the amazing new information we received. It was really important that we incorporate it into this launch, and that we do incremental improvements for performance purposes and optimizing, just the engineering and the configuration of the launch vehicle itself. So pretty cool. All right. So let's talk about what's new, what's going to happen in new space, and it will look different. I mean, what does the future hold? So in my opinion, like, the last 5 years have moved the new space industry faster than the last, 30. You can argue SSTL, Sirius Satellite, was sort of the founding father of the small satellite. My former company, so I have to give a shout out to them. But but there's still a lull. It wasn't until the 2000s where with the onset of the CubeSat and kind of more standards and things like that we started seeing a space economy happen. And the last 5 years, I can't tell you how much has changed from cost savings. The cost perspective, building your own satellite with, even a CubeSat, which was always low cost, but thinking about the capabilities that it had, like the performance that you're now able to package into a small CubeSat and deliver, meaningful data and services to customers. Whereas before, I know I'm preaching to the choir here, but you had much larger satellites, school buses, size down, on down, and we can pack a lot more power and data processing and capability in those. So the first trend I'm seeing is just the amount of new space startup companies. I think like cumulatively over $1.9 billion was raised just this past year. And they're all planning, 80% of those satellites are going to be part of a constellation. The other 20% are, I would say, probably more like science demos and things like that, one-offs. But if you're a business, it's not going to be many one-offs. And excuse me, the business case for space, the theory basically is putting up a constellation of satellites in order to get as high of a revisit and coverage as possible in order to deliver data down to the customer. And that's sort of the first part. And so the last 5 years, it's been going on for 15 years, but I will say this cycle has really picked up. 10 years was a milestone, but not quite there yet. 5 years has been a real push, which has accelerated in so many crazy ways. So the business case of space is about the data primarily. And then it's about, okay, diversifying not only to send satellites to sun-synchronous, but looking at mid and lower inclination orbits as well, which weren't, available too often. I mean, we're still one of the few that can do low. There are some other providers now that are providing mid inclination opportunities. So that's changing. The other thing I'm definitely seeing, and then as I mentioned earlier with the fundraising, you're seeing now companies, frankly, that had never built satellites before. You're seeing a lot of student groups, university spin-offs that, I am talking to folks who, there's business guys like me who know very little bit about how to build a satellite, and they have this idea and they're just getting funded. And it's basically just a business layer. And now they're looking for partners, for launch and for satellites and for payloads. And that was never how this, market was conceived, of course. It was sort of like, people in a lab, people with the know-how. And that is because things are optimizing and things are standardizing and things are really moving so much quicker in terms of, mission solutions. So the other trend I'm definitely seeing is things are being bundled. And that is enabling, the business layer to come in and get a turnkey mission solution. Customers these days don't want to build hardware. And I know that hurts everyone at AIAA's head. I mean, hardware is sexy to engineers, but higher profit margins and data is more sexy to the business world. And so it's not about the hardware anymore, really. It really is about the pixel, and it is about the data, and it is about, the revisit, and it is about, beating out the competition. And so we're seeing definitely trends in having things delivered in a more turnkey package. And so that really is like having, one signature on one contract to give one solution. And, to this day, you still have segmented verticals in the space ecosystem. You need to get your ground system, your launch, your satellite, and so forth. But the idea of bundling is definitely been picking up more and more. Where we're looking, and Virgin is doing this, we are looking at partnering with satellite companies to optimize their spacecraft for our system, making sure the environments, the loads, the form factor are all within a standard that fit us. And so that not only will you have the best package in terms of how you stack and fit the satellites into our launcher, but you also have a business opportunity where we can kind of sell a capability. And so, you augment your business arms basically by doing that. So that's definitely a trend. The other thing is, how do you sustain this market? So, 80% of future satellites, and they're predicting 8,000, 10,000, whatever number, it's a big number in the future. You've all probably seen the reports. We all see this, hockey stick basically, where it just goes up and then it's eternal. I mean, we're seeing more and more satellites are being built, cheaper, and they don't need to, most of them don't need to survive that long, frankly. And most companies in the new space side aren't looking to build, immortal sats or sats that last more than 5 years. In fact, many I'm seeing are programmed to have lifespans of 1 to 3 years, with a little bit of margin on the end. And that's because they want to do technology upgrades more readily. The other impact naturally is when you have a constellation, a lot of satellite customers are putting spares up. And when you have a spare in a constellation, it's not being actively used. It's needed to be called up if there's a gap in the service or an anomaly with another satellite, or you have an infant mortality rate issue. But that spare is degrading while it's in orbit. So that's, doesn't guarantee you much life. So what do you need? I mean, you have to populate your constellation. Then after 3 years, you're probably repopulating it. You have to, then you may need to augment it. So not only are you doing, not only replacing, satellites, but you may be augmenting. So you're doubling, maybe the number. Then you have to, so many customers are providing, think about it, internet service, comms, aggregate data, maritime shipping tracking, train tracking, all that kind of stuff. I don't think most logistics companies or customers could go a day where they can't track their shipment, or they don't get internet, or they don't, and so on. And so when you have gaps, 10 years ago, 20 years ago, 50 years ago, you put a satellite up, it's like, yeah, guys, there's gonna be problems. Something happened, all right, give me 4 years or I'll replace it. There was an expectation back then that, okay, this stuff takes long, I get it. So we didn't use it for so many real time, things. We didn't use it for all these different market verticals that weren't traditional space players. All these new guys are proposing basically to provide satellite coverage for consumers who are used to having data through ground sensors or connectivity or whatever practically instantly. So how do you stay on board with that? How do you compete with that? And the answer is you have to have a plan in order to be able to replace and replenish and augment, like we talked about, but then gap fill if you have an anomaly. And so you need, that gets back to the original, I think, scope of the discussion today, and that is you need to have rockets ready on the ground. You need to have satellite spares on the ground. It'd be another advantage to have an ecosystem that could really tie into being able to direct inject something quickly. You no longer have to do on-orbit spares, or maybe not as many on-orbit spares, for example. So we're definitely seeing a trend there of bundling, but also servicing. Like this is becoming kind of, there's satellite constellations of the service model, and certainly launch service in terms of being responsive, I think is going to be absolutely critical for the commercial industry. And then for government, of course, as you can imagine, there's a lot of national security, strategic implications to having a system like this, and ground launches too, of course, that are going to be more flexible and more ready, but being able to direct inject satellites into the correct orbit quickly, have satellites pre-encapsulated, maybe stored somewhere so that you can go quickly, with a rocket nearby, and then the flexible launch side, being able to hit the different orbits, or being able to provide a more low profile launch. So it's not always the same launch site. You can provide unpredicted launch access, for example. So those are some pretty interesting things that are happening in the market. I won't shy away from the question of, well, what about launch? There's a lot of launch vehicles out there, and I agree. And I think and honestly, there's going to be consolidation. The 100 launch companies aren't going to make it. It's going to be a handful. I think if you look at the ground launch vertical players, they're differentiating primarily on cost. So they're either saying, oh, we're 3D printed, we can print this a lot quicker, or we're, we've got some other, fancy accessory, but in general, and they're trying to stay responsive, being more responsive as well. And I think if you're a smaller rocket, you probably, you can store them more easily, you can probably build them a little faster. So certainly that's true. But at the end of the day, you're still kind of, you still have the fixed site issues, and you don't have the flexibility, and you still are going to compete, apples to apples. I think we're positioned ourselves, purposely this way, having kind of seen a little bit of where this market is going, as, the pear or the pineapple, whichever other fruit that is not an apple, because at the end of the day, it is fundamentally a different service and a different kind of ConUps that will enable, your gateway to space, enable space domain awareness, responsiveness, and that flexibility. And oh, by the way, let's look at providing, services around the globe. So it becomes more like an airline model than it is just a pure play rocket model. So that's how I see ourselves in the market. I think we're well positioned for that. We're not the cheapest, but we are, I think, the most operational flexible. And for the partners that need that, we're the service. If you need to go to a sun synchronous orbit and you can ride share, and the timeline doesn't matter as much to you, then certainly some of the larger vehicles and their ride share capacity will be good enough for you. But by the way, that's okay, because we complement those. And those satellites, a lot of the ones that need the lowest cost, but on any timeline, they're up there to do a demonstration. They're just trying to get their business case, proven, and then they're going to move to the next phase, which will be the constellations and so on. And that's where we really will shine and be able to provide that flexible and optimized service. So anyway, I think the market's going to look really different. I'm excited of what the next 5 years has in store for us. I think it's really moving at such an exponential rate. And, I'm seeing a lot of business cases and business models changing, and I'm seeing a lot of financial constructs that are looking very different now. It is not the traditional way of doing things. We are, I think the whole market is being a lot more accommodating, a lot more flexible, and that will create a lot of new interesting business opportunities that are more tailored to commercially minded opportunities. So I think that's it. I don't want to take up too much more of your time. I went 5 minutes over my goal, keeping it to 45 minutes. I apologize. But I hope you guys had some fun listening, and I am happy to field any questions that you may have.
Thank you. Thank you. This is wonderful. This is really amazing. And, you know, new space is really the future of the space program, and everybody is looking up to this. And AIAA has the Ascend, you call it conference or forum in November. That's a gearing tool, you know, also for new space and commercial space, you know, those things. So, so wondering, can you see the Q&A box from your end?
Yes.
Yeah.
Yes.
There are a couple of questions there, and I think we have a gentleman also raised hand, ready to speak out his questions. So if you can first take a look at the Q&A, see if any.
Sure. Let's see. Okay, could you design a business plan? How do you balance flight on demand with low costs? So not sure what could you design a business plan means, but I can. That's definitely what I do. But I'll address the balance of flight on demand with low cost. So that's a good question. And honestly, it is going to be more of a premium service. So it's not going to be from the get-go the same as doing a ride share or dedicated launch, because I mean, you do, if you're going to do on demand, then you really do have to prepare a lot. Number one, you probably have to have your satellites pre-encapsulated, so there's a storage, you know, there's a storage cost and things like that. And then being able to do a quick call up like 24 hours, I mean, you have to have a crew ready to go, and that's really the biggest challenge. I mean, once you can operationally figure out how to fuel, how to connect, do all those things which we're learning, then pretty much you can get to 48 hours, something like that. That's going to be pretty much solid. So it really is just having, okay, where's the rocket, where's the pylon, or sorry, where's the fairing, where's the plane, and where's the crew? That is going to be what it's going to take to be able to really provide these quick call-up services in a snap. So we are working that through. In fact, our next 3 or 4 launches, we will be designing with responsive launch cadence in mind. So we're not doing a true responsive launch, but we're doing small things like a late load process of a satellite, or we will be, we'll have some folks from the U.S. Space Force helping us, with some of the ground ConOps. We'll be demonstrating, I kind of think of it almost like at the race car, on a race car meet, where the guys are like taking the tires and like, they're like so fast and they're just able to do it like that through practice. I mean, that's a little bit part of the plan. So we will be working on that ConOps. So it's a really good question. I think there will be economies of scale still, but it all comes down to how much planning you do. That's how we're going to keep the cost down. Okay. Let's see. Alexander said, where did you launch from? My mom wants to know. All right. Well, to Alexander's mom, we launched from Mojave, California. That's like our main launch site. That's near Long Beach, about 2 hours from LA drive, no traffic. And so that's our spaceport there. We're also launching from Florida, from the island of Guam, from the UK, from Japan. But tell your mom that we can basically launch from any airport that has a long enough, or I should say spaceport, because you have to have you have to have the licenses, of course, and you have to do a lot of safety analysis and things like that. But you can tell your mom that we can launch from any spaceport with a long enough runway to accommodate the 747, which is about a 9,000 foot long runway. So if you have a 9,000 foot long runway and you have a safe zone for us to launch and do our operations, then we can probably launch from there. Let's see, what's the max payload launch capability? So the max payload launch capability is probably 500 kilograms. I say probably because we will be making incremental improvements where we will be adding performance capabilities. So I think in the future, we might be able to add like another 100 or so kilograms, which would be really cool. But for now, the bounds are 300 to 500, and it depends where you go, which orbit you fly. So 300 kilograms is to sun synchronous, 500 kilograms if you go to 0 degrees, because you benefit from the how the Earth is basically spinning at 0 degrees, in order to get the rocket lift off the ground, so or off out of the air. So we can actually get more performance from a low inclination than we can from a higher inclination. And then another question I see is, since you have been government side and commercial lines, what according to your pillars do you need to run a successful business? Great question. So from Pratik. So there's a diplomatic answer, and then there's the not so diplomatic answer. I'll give you the straight answer. The straight answer in my view is it's still a tricky market to operate through just commercially, because as I mentioned, there's still so many startups who have very little money or are just getting going, and they have to conserve cash, and they have to be smart about how they're building up their business. And so naturally they want the cheapest price, and that obviously doesn't always doesn't always work within their budget. It doesn't always get them what they need. It doesn't help businesses like us trying to go forward on a race to the bottom on price. So the commercial market is still really feeling things out, but there's a lot of promise, and I have full confidence they will get there, and they will kind of follow us. We'll come down the cost curve, and they will come up a little bit, because as satellites as their business grows, one, they'll have more cash flow. That's good. But two, as their business grows, they're going to become needier. And what I mean by that is, a lot of startups are fine doing rideshare for cheap on a big rocket like SpaceX, get me to space. But once you've done that and you need to close your business case, that's not a good solution for you to get a satellite up quickly, to augment your capabilities so you can get more revenue, to replace a satellite, and so on. So you're going to get needier. You're going to need more specific requirements. I mean, it's like the bus and the Uber analogy. You can buy a ticket on a bus, it'll get you home. It might take you 2 more hours though, because you got to wait through the stops than if you bought a ticket or an Uber ride, which could cost you 10 times more, right, than a bus ticket. So it just comes down to the service that is required. Now, on your idea of that's commercial. So commercial is still a little tentative. The way I think this needs to be successful is the government does need to be an anchor tenant. So whether it's U.S. government, foreign government, you can't always depend so much on commercial just doing it all. You need to, there's still subsidies happening, of course, all around the world for the different launch systems. So even the market price isn't really the market price. But you need a government tenant, and the government tenant at least gives you assured launches. And it doesn't even have to be a lot, but what it does is it helps keep the lights on, the business going. And at the end of the day, it's also a good signal to investors. So a government tenant can kind of carry you over to the next round or your next investor, and hopefully by then you'll have figured out some of the learning curve issues, the cost issues, so that you can come down on price. So by the time you've got the new investment round in, you can be more in tune with what the commercial companies need. So I do strongly believe that you need a government anchor to bolster your business until, especially the new space business, where it's still not clear. The market, they predicted, it's a $3 trillion market, says Morgan Stanley, but at the end of the day, the proof is still not quite there yet, because it's just starting. So good questions, guys. Sorry. We saw the exterior of Launcher 1. Any comments on its interior architect setup? It's very simple. The interior, we use carbon fiber composites. It looks pretty much like, it's got a skirt, and then it has a tank inside. We have publicized we use linerless tanks. That's an innovation we developed, which helps with mass and cost as well. But it's pretty standard looking, like ground launch vehicle. You've got with the liquid oxygen in the fuel tanks for one stage, and then the second stage.
Yeah, Mr. Santosh Kumar has a question, and he has said something to show. Santosh, we have only 1 minute, so can you do it?
I'll try this quick. First of all, Steve, congratulations on the tremendous achievement for you guys. I'm actually one of the pilots from Long Beach Airport Association. We actually had invited Virgin Orbit, which is then Virgin Galactic, to come to our safety meetings to help welcome you guys when you first arrived. And it's really awesome to see how much you guys have progressed because of your own skill and success and determination. The question that I have for you guys are a couple questions. Number one, any chance in the future you guys would ever operate out of Long Beach? I know there has to be a lot of approvals and things of that nature. And the second question is, are you guys currently operating I know you guys launch out of Mojave, but are you guys literally launching out of Mojave, or are you guys going out to the Pacific Sea range, Point Mugu, to actually do the launch over water? Because if that's the case, that's something I wanted to ask you about that.
Yeah, and feel free to email me or reach out, because I know we're running out of time. But we'd love to launch out of Long Beach. It might be complicated though because of air traffic. You do have to we need about a 45-minute window where you can't have any air traffic. At least that's how the regulations are now. So that could be a challenge. And then yeah, we do use the Pacific Range. So that is where we do the drop, actually, in the ocean. I mean, technically our launch starts from Spaceport Mojave or wherever the runway is, but that is what we call a captive carry flight. So, and I know we're running out of time, but I want to thank everybody for listening and attending, and feel free to reach out if you have any questions in the future.
Yeah, Stephen,
That's
actually.
the Pacific.
Oh.
Yeah, that's
okay.
right. You guys, Mojave is actually up in the Mojave Desert out here. That's
Right.
Edwards Air Force Base. That's Mojave right there. So you guys would take off from there and actually do your launches in this area right here, the Pacific Sea Range.
Yeah, a little past St. Nicholas Island.
Okay, there's St. Nicholas Island. That's Santa Cruz Island.
Yep.
Okay. Oh, here we go. Okay, that's St. Nicholas Island. Okay, wow, that's
Yeah.
pretty cool. I just wanted to show this because I thought it might be of a value for people to actually see where you guys are actually doing your launches. And of course, Long Beach is out here. That's
Yeah.
Long Beach. There.
Right, and so we use a ground station and telemetry tracking from Long Beach actually to track our rocket, at least at the point of the drop. So.
Yep, and that's the headquarters right there for you guys. This area right there.
And if you zoom in further, you can probably see me walking in the parking lot.
Yeah, there you are. Cool. Thanks for letting me screen share.
Thanks.
With this, do you actually the Cosmic Girl does it has ADS-B on board? So people
Yes.
can. Oh, okay. Yeah, thank you. Yeah, one thing I want to say is that Long Beach is within our Los Angeles Las Vegas section responsible area. So anything you need, please reach out to us. We'll be more than happy to work with you. And the other thing is, early this year we heard from the news that it seems that Sir Branson's mother seems to have passed away. Yeah, really, I want to reach out and express our condolences. Yeah.
Thank you. Yeah, we in fact, she passed away maybe it was just a week or two before our launch demo, the successful one. And we actually put her name was Eve, and we put her name on the fairing. So we think Eve helped us, make it to space.
Yeah, Eve, yeah, indeed, yeah. Really, sorry to hear that, but great to see the success.
Thank you.
Yeah, thank you. Wonderful. Yeah, stay in touch. Thank you so much.
All right. Thank you, everyone. Have a great weekend and great conference.
Thank you. Thank you.
Bye.
Okay.
Thank you so
much. Yeah. Thank you, Santosh. Yeah. So this new space, isn't that exciting? Virgin Orbit, Virgin Galactic is the leader in the new space business. But our next speaker from Astrobotic, they are doing very exciting things, for landers or rover. And you will hear from our speaker. Actually, they have just opened a new control center. Actually, so you will see kind of unconventional image from TV in the future that, there's a hugging and clapping, it's not from JBL, it might be from Pittsburgh, from their control center. So our next speaker is Mr. Daniel Gillies. He's a mission director of Astrobotic. He has a lot of great experience, he has a combined experience in space launch, program management, and mission operations. He started a career at NASA Johnson Space Center. He was a flight controller, STS-116, 123, with United Space Alliance and the Space Shuttle MER mechanical support, SS-124 to STS-135. If I'm correct, I think 135 was the last mission of Space Shuttle. After the shuttle program, and we actually had an anniversary event for the STS-1, and very exciting. So after the shuttle program, Mr. Gillies held roles in design, manufacturing, engineering from Boeing CH-47 and 787. He also supported launch of spacecraft ranging from CubeSat and Crew Dragon as mission manager at SpaceX and mission director for Spaceflight and Rocket Labs. Most recently, Gillies was a mission director in the airborne flight crew for NASA Stratospheric Observatory for Infrared Astronomy, where he participated over 20 flight missions. His PhD in astronautical engineering and astronautics science degree. He's also a naturalist, and he's very excited about those old science, very wildlife science, and he also studied there at Oregon State University. So let's welcome Mr. Daniel Gillies.
Thank you. Let me go ahead and get screen share control. And full screen. Cool. Let me hide that there. All right. Thank you very much. As mentioned, I'm Daniel Gillies. I'm a mission director at Astrobotic. And specifically, I'm responsible for Griffin Mission 1, which is the second of our planetary landers missions and the third kind of company's flagship missions overall. And today, I'm going to talk to you about our programs, which include rovers, landers, and Space Tech Oh My. I promise I didn't make up that title. So Astrobotic, you may have heard of us on the point of lunar landers, but that's not all we do. Specifically, we've got areas focused on advanced navigation and computing systems. Our Future Missions and Technology Division is responsible for that, and it's a very large part of our landers and mobility programs. We have a surface mobility group who's focused on rovers, so extending our reach beyond just the landing site. And then, of course, there is our landers group, which, to clarify, it's a planetary landers department, as well as making spacecraft. As at the end of the day, what is a lander but a spacecraft with legs? In terms of who we serve, obviously NASA is a massive customer for us. Our three large missions are basically chartered by NASA. In the case of my mission, Griffin, the Viper, which is a rover going to the South Pole, is the payload on the mission. We also have commercial customers, though, and our Peregrine Mission 1, that mission actually has a number of commercial customers, and they range from corporate entities to other governmental entities to nonprofits, or one other kind of cool element, technically anyone on this call could become one of our customers through our DHL-sponsored Moonbox, where you can buy a space on the vehicle, very small, but you could send your object to the lunar surface, which is pretty cool. Also, I started here a little over a year ago, and when I was learning about the company, I thought it was relatively new. It's not. It's actually been around since 2007, and it spun out of an effort out of Carnegie Mellon University, who we still work with today. Really, you don't associate Pittsburgh with space, but there are other space activities going on here, whether they're at Carnegie Mellon or the Space High Performance Computing Center out of University of Pittsburgh. I like to think, though, given that we're the ones that are operating at a mission level, we're kind of at the forefront of space tech here in Western Pennsylvania. So why the moon? I think a lot of you, number of space architects, I think on the call, can understand that it really is a stepping stone, whether that's in technology demonstration, whether that's for supporting the human missions that'll be going to some of the destinations that we're going to on our robotic missions, or it's a pathway to Mars or elsewhere in the solar system. Our missions are contributing to each of these elements in some way as being that initial pathfinder, particularly with respect to commercial entities being able to go to another planetary body, to the moon. All of these things, from fuel depots, mining, manufacturing, just expanding the reach of our species, will all be made possible through these small steps. So in terms of our programs, first, the services side, and I'll talk more about these in the following slides as well. We've got two primary landers. The first is Peregrine, which is designed for that roughly 100 kilogram payload class. And that number can go up and it can go down depending on where you go on the moon and what the mission specific configuration is. You can always think of these landers as, if you come from the aircraft world, being configurable with mission kits, things that might matter if, are you carrying a rover, or are you only doing drilling per se at a site that you're gonna be landing at? Well, that'll help determine the configuration of a given vehicle. Then there's Griffin, which is capable of taking surface payloads over 500 kilograms. In the case of Viper, that's a 475 kilogram payload, and that is just the rover and attached hardware alone. That does not include the mission-specific hardware, like the ramps, which are obviously very specific for that specific rover. Then we also do the mobility side as a service. We have two primary vehicles that we offer from a service offering perspective. And the first of those is Cube Rover, which I have a bunch of slides on because I think it's a really awesome little platform. Think of it as the CubeSat equivalent when you're thinking of something much larger like Viper or our Polaris vehicle. Instead, this is meant to be small, agile, and low cost. And that's for surface payloads ranging from 2 to 6 kilograms. Then there's Polaris, which can handle surface payloads up to 90 kilograms. And that really was designed with a vehicle like Griffin in mind. In fact, those programs were mated together once early in our development history. So we're not just services, we also are designing hardware and actually doing quite a bit of R&D, and that's at the PI level, which is really exciting. So a large part of that technology is in support of our missions, and it boils down to precise pointing and navigation, particularly in GPS denied environments, which for now, the moon is that until someone sets up a lunar navigation system. I look forward to that day. Autonomous navigation, we are not driving the vehicle down to the surface during powered descent. It's an entirely autonomous process. And that also means it needs to be able to avoid obstacles that you might not even be able to see on the best of the LRO images that you're really going to be finding out about once you get to that last moment of terminal descent. In order to do this, it's not just about building the hardware capable of detecting those obstacles and doing those calculations, but also being able to simulate it. And we've put in a lot of effort to physics-based rendering, and I'll show you some videos of that I think are really exciting that illustrate the capabilities of Astrobotic beyond just the hardware side. Space computing is the last element, and there's some elements of this that are really being pushed forward right now in support of deploying some of these elements of hardware, but also for our other future missions, maybe even for the lander. Space computing, especially in deep space, is hard, especially when you're talking about rad-hard components. It's bad enough that there are chip shortages around the world right now. It's harder when you're talking about rad-hard parts. Costs are high, lead times are long. So being able to bring that in-house and provide a custom tailored solution that we can use again and again is really important, I think, for the commercialization of the moon and other deep space destinations. So this is where it happens. I know there was a tour on the agenda. One, time isn't going to support that, but also two, the facade that's shown in this picture is actually going in right now. So everything is a bit of a mess. But right now I'm in one of our manufacturing areas, and I've got the Peregrine structural test article that went through qualification behind me, which is just a small piece of our facility. But we have our headquarters here in Pittsburgh, Pennsylvania. It's where we do everything from manufacturing, some levels of test, to mission operations. We have a mission control center, as shown in the next slide. This is a rendering, but this facility actually is online now and was recently completed, which is pretty exciting. There'll probably be more about that in the news coming soon. So going into our manifest, so I can give you a little bit more details on those missions. This is mission 1, Peregrine, going to the moon later this year. Is going to a landing site called Lacus Mortis. So that is on the near side of the moon, hence the solar panel on top, radiators on the side. You'll see some big differences when we look at our polar configuration with Griffin. 16 customers from 7 countries, $80 million program from NASA, very exciting, one of the first winners in the CLIPS program. Really cool mission, really as a pathfinder. And we've been making a lot of great progress. This happened last year, so this is actually old news, but it's still really exciting to see. It's when we actually first moved into this facility that I'm in today, and this is our structural test model. On the next slide, I can actually show you on the center image is that article going through vibration testing. In the upper right-hand corner, that is one of our axial engines for the vehicle, actually coming out of Southern California, out of Frontier Aerospace. The cool thing about those engines is that they're also part of a NASA program in order to have other deep space bi-prop engines available for the new missions beyond just going to the moon. And in the lower right-hand corner, we've had a number of payload checkout activities that have already begun to occur for this mission as part of the payload integration process. Already mentioned, Peregrine, 16 deals signed to date. There were 3 that came post-CLIPS. So we started this process in 2012. And I will tell you, it is hard I'm sure as the other speaker later today from our competitor will also attest, the commercial lunar market is burgeoning, but it's kind of, if you build it, they will come. So we're at the forefront of that, and it's really exciting, but I don't think it's for the faint-hearted. So unlike the small launcher market, you're probably not going to see as many commercial lunar lander companies off the bat, although they are starting to pop up, especially with programs like CLPS able to provide that seed. Just a list of some of our customers. You can tell they're from a wide variety of types of customer bases, everywhere from nonprofits like Moon Arts and Moon Arc to robotics like SpaceBit or Canadensis. So these are just some updates. These have occurred, some as far ago as 2019 in the case of the Vulcan signature, but the program's made a lot of success. Our engines have been going through hot fire. Our headquarters are now online. We'll be doing final integration of the vehicle. Structural test model has gone through qualification. And yes, our launch vehicle has been signed. And in fact, we've just signed another one recently for our next mission. This, pivoting for a moment, is our second mission on the calendar, major mission, and that's Moon Ranger, which we're calling Mission 2. It'll be going to the moon with Masten in 2022 as part of their mission, as this was a CLPS payload. So we're both the payload and the lander, which is kind of cool. This is something that we are partnered with Carnegie Mellon University on. So it's not part of the product line per se, it's more of a unique mission, but it will be testing autonomy on the surface of the moon. And this is a picture of one of the engineering models of that rover during some fit checks effectively to our vibe table. Not quite at vibe at that point. Next, Mission 3, which I refer to as Griffin Mission 1, as it is the first of many Griffin missions, hopefully. That will be going to the South Pole of the moon at a site to be determined by NASA very soon. That'll be going there at the end of 2023. It will be carrying NASA's Viper, which is shown there on the right. A $200 million program for us, pretty exciting, pretty amazing considering where our companies come from back at X Prize days to now carrying a nationally important payload to the lunar surface, and not just that, but to the pole. This is GLAM, an acronym that I invented, the Griffin Lunar Analog Model. This is being used for prototype testing, and I think, yeah, I've got another photo here. It's being used to test the ramps. So there will be a Viper engineering model in the coming weeks that's actually going to be driving down these ramps with a variety of different positive engagement features, whether those are high friction surfaces or actual engagement tabs. We're testing it all out to find the optimal solution and safest solution for the egress of Viper onto the moon. And then on the right is that STM model that's right behind me. So cool progress here on this program. We've had a number of procurements already occurring with respect to flight, as well as hot firing activities. Going along the top of the screen and then down to on my right, looking at it at least, that's our axial engine. It's actually, this was from a prior program, so that's not a hot fire in support of Griffin, but on the program that it was a legacy from. However, on the lower left-hand side is our ACS engine. That is part of the hot fire, and I've got more images, I think, on the next slide. Yes, from Agile Space Industries. I will mention Frontier, that Southern California company, also testing out in Mojave. They're providing the axial engine for the program. Agile is our ACS engine provider. These engines have already started to go through hot fire, which is really exciting. Launch vehicle was signed. You probably saw that news very recently. We had selected the Falcon Heavy to take us to the moon, launching out of 39A, really exciting. I'm excited to work with SpaceX again, but it was a very hard competition, very difficult decision to make, but SpaceX is our selection, and I'm looking forward to getting into mission integration with them. And then on the right, of course, is the GLAM that I was referring to. Not only was it assembled here, it was delivered to Johnson Space Center. That's in Building 9, where the other mock-ups are stored. And it's going to be used for engineering evaluations imminently. So quickly talking about space as a service. So in terms of surface service, let's say you want to send a payload to the surface today. Well, we advertise our prices on our website. It's $1.2 million per kilogram. However, it's not just mass to the surface. It is a hosted payload. So that includes surface operations. Right now, our mission's baseline operating during the lunar day, although the next step will be to operate through the lunar night. So that limit shown for surface ops just assumes that it's lunar day only. provide comm on the surface, power, and of course, a place to be. If you have a deployable payload, you don't have to stay hosted. We have rovers that we are carrying to the moon, other than Viper, that can be deployed to the surface as part of the mission. We also, as I mentioned, can provide that rover for you. So this is the Cube Rover product line, and it's been sized using that CubeSat standard of 1U, 2U, 3U. So what you're seeing here is a 2U, a 4U, where they're kind of 2 in front and 2 deeper into the screen, and then a 6U. It similarly provides you power, data, communications back to the lander, which provide communications back to Earth. It can host instruments, it can host ISRU, you name it. It is a cool little spacecraft, and we can provide it as a complete mission solution. These are just some examples of applications. To give you an idea, it's on the order, I think it's in a following slide, of $4.8 million, gets you a Cube Rover mission. So if you want to start your own space program and you won the lottery or you're really great at fundraising, this is your opportunity to do so. Could be outfitted with instruments, it could go to support another mission, or it could run on a mission of its own, kind of space program in a box. Oh yeah, and then this is a video that I will play. I don't know if you'll hear the sound. If you do, that is not the sound of the Cube Rover. That is a generator at the rock yard that is being done at night. But just an example, that's Cube Rover operating autonomously. It is small, but small means lightweight, and lightweight means low cost to get it to the moon. So if you're interested more in learning about our services, we do have payload users guides, both for Cube Rover and Peregrine, and I believe the Griffin users guide is coming quite soon as well. There is an IDD, so an interface design document, like you'd find on any other common spacecraft bus, so you can determine how will this meet my needs? What are the interfaces that it has? Whether those are physical, electrical, or comm. Also, with every mission, you get an Astrobotic Payload Manager. Customer service is a very big part of our way of doing business. It is one of our key priorities. So look forward to having you on our missions in the future. Going forward, and to close this out, I'll end on talking about our space technologies. So first, and this goes back to 2018, I believe, is SoundSea, and this is on the station right now. Just to give you an idea of the wide breadth of activities that we do at Astrobotic, this is a payload that was built with Bosch, and specifically it was autonomously listening for sound signatures on the space station. So imagine you have, and this is in its kind of subsystem level form. It is meant to be integrated into a larger robot. That robot then can live, if you will, on a space station, a future vehicle, and listen for anomalous noises like machinery that's not beginning to work properly, and provide that diagnostic off the bat. So sound detection and taking action based on it. More autonomy, autonomous mapping. I love this one. I don't think it gets enough press because this goes back also to 2018 or 2019. Autonomous mapping technology, which, as you can imagine, evolves into what we're doing now for the mapping technologies to land on the lunar surface. These are products of LiDAR, and I will actually just show you a video on the next slide to save time. So equipped on a drone. Drone's a little bit loud, but to do autonomous mapping of a cave. And of course, the application here, imagine this on a rover or on another vehicle on the surface on the moon. You could explore lava tubes and begin to build, as you can see in the map up top as this is sped up, build maps for future explorers to utilize, or for resource exploration, which I think is just awesome. There's if you've seen Prometheus, they deploy a little sphere and it goes and maps out the whole ship. It's just like that. Except it can't float in its own on the moon. TRN, that's terrain relative navigation, and then hazard detection and avoidance, HDA. So this is a very big part of going to the moon, especially for the South Pole, where hazardous features on the surface, like a rock of, say, 20 centimeters, that could provide a hazard to the lander. That could provide a hazard to the rover as it's coming off. So we need to know about those and be able to avoid them. As I mentioned, there's no GPS on the moon, so you need to be able to navigate without that external reference while you're descending. And that's what terrain relative navigation allows us to do by using digital elevation maps that are then recreated on the vehicle, terrain feature mapping. So using machine vision basically to, I know what this surface should look like. Oh, I see that surface. Provides a reference when you take into account the altitude and the speed you are moving. Suddenly you know where you are, and you do that constantly as you descend, which is what the bar here is representing. Then as you get very close to the surface, now it's time for detecting hazards. And with that, we use LiDAR to be able to determine, oh, is there a rock where I wanted to land? A big one. Yes. What do? I divert, I hover, I go to another site that's safer. So that is a very important part of going to the South Pole. And that is technology we have developed entirely in-house. Really proud of as being part of our product line here at Astrobotic. Also available for other lunar landers and other programs that are interested in using this technology, and their applications far beyond just landing on the moon or planetary bodies. So in terms of the tech that allows you to go do that, this is pretty awesome. This is part of that rendering that occurs. On the left is imagery, I believe, from LRO, and on the right is what gets generated on board. So it's taking into account not only digital elevation maps, but also lighting, timing. This allows you to know based on when you are, where you are, do the lighting conditions match? It gets rid of all the unknowns as you're going down to the surface. If people have questions on this, I will take them as an action because I am not the expert on this technology, but it is key for us to get to the surface of the moon. Lastly, and which I'll end with and try to get us back on time, we are hiring quite a bit. This came from our website this morning. There are 17 positions open, some of these for more than one position. And that's in support of all of our programs. We're really making a push to continue to expand our R&D efforts. So if you are a space architect, if you are an engineer, and you are looking to get into the R&D environment, this is an awesome place to work. People get scared of, oh, I'm going to Pittsburgh. What if something happens? What will I do? Well, hopefully nothing will happen, and we're going to be quite successful. We have funded missions through 2023, 2024 already, and more soon to come. But this is still an area for tech development. Autonomy and Pittsburgh go hand in hand, whether that's in autonomous vehicles, drones, or lunar landers. That is my last slide, so ready to open it for questions.
Thank you, Daniel. This is amazing. You know, the new space is booming. This is really fantastic. And you are wonderful. You're a leader in this field. It's really amazing. The TRN is also what Mars 2020 was using, right? For landing.
Yeah, that's
fantastic.
Right. There are different applications. Some are using LiDAR, some use imagery, same on the HD hazard detection. Some use optical sensor. They're all optical, but an image-based versus a laser-based. So there's all different flavors, but yeah, indeed.
Yes. So yeah, they just lander and rovers. They are key. You know, we have the space architecture events, and they are pumped up. They have all the kind of design, but they need your rover. They need the lander to do it. Otherwise, you know, they talk about very nice, you know, habitat building in the South Pole, but without the rovers and the lander, they cannot do anything. I think Shantanu, I think you raised hand. Do you want to say something? You can unmute yourself.
I just had a quick question. First of all, thank you for this awesome presentation. I noticed in your bio you were a Purdue alum. I'm currently a Purdue student, so boiler up. I just had a quick question about kind of the unique challenges, or if there were any, with relation to like achieving autonomy with lunar rovers. Because I know that like on Earth, obviously, you can use a variety of different sensors to get different data. And I was just wondering if compared to, for example, creating like a car that can drive itself on Earth, what types of challenges do you have to face in like a more rough terrain, or in a terrain, you know, where there's like hardly any light, or maybe just super cold or super hot? I was just wondering like if there was any specific challenges you've faced or have had to focus on, especially with regards
everything
to
you've just said. I mean, comms are a massive one, right?
Yeah.
Especially when we're talking about the South Pole, not to mention comms being right now with the rover and lander line of sight. So if there's no orbital asset, which China's got a great orbital asset, but we don't yet, It makes it hard to do that rover beyond line of sight unless it's carrying its own, X-band transponder back to Earth, which that makes it very big. That's what Viper does. They communicate directly back to Earth. So that's definitely a challenge. It's one we're looking to help solve. Our lander helps solve some of the challenges for navigation. As we're coming down to the site, we're collecting as much imagery as possible using our TRN, using our high definition cameras, and we're going to be able to use that to create maps that can then be used by our mobility team or by Viper. Those things are of key interest. So you try to make them go hand in hand, but yeah, South Pole, especially if you're going to operate for more than the daytime, it's going to get really, really cold. And when you're talking about a very small rover, you've got to begin to get really creative in terms of how you can make it survive. It's not going to be batteries alone, although that's the Viper approach. It might be finding its shelter, maybe on the lander. Lots of cool concepts there to explore, but that's kind of the cool things that we get to do here at Astrobotic.
Awesome. Thank you so much.
You're welcome.
Yeah, thank you, Daniel. This is wonderful. I think there are 3 questions in the Q&A, but I think the time is not enough. So maybe you can continue to look into the Q&A box. You can type your answer there. See if you can address that something there. I think some of the questions you mentioned, you probably have to take note to about the model, mathematical model. But anyway, thank you so much. Thank you. This is really fantastic, and we love Astrobotic. It's just amazing. I was in Pittsburgh, and you were in from LA, so it's a great combination. Stay in touch.
Indeed.
Yeah.
Thank you very much.
Yeah. Let us know anything you need. Let us know. Thank you.
Absolutely.
Wonderful. This is amazing. So everybody can see this amazing, new space. That's really what I think NASA has been picturing for, the vibrant economic activities for business in space. Sorry. So our next speaker, actually two, Brandon and Parker. They're from Booz Allen Hamilton. They are going to tell us more into story. They actually have some new idea proposal for the artificial intelligence. So let me say a few words. And Brandon is a senior consultant at Booz Allen Hamilton in Los Angeles, California. He is focusing primarily on the acquisition development of next generation space systems. Prior to joining Booz Allen, he has worked for the DC-based space consulting firm Anduril Global and for the U.S. House of Representatives Committee of Science, Space, and Technology. His publications on evolution of human use of outer space have received recognition at national and international levels. The co-speaker, Mr. Parker Southey, is the lead engineer at Booz Allen Hamilton, also in Los Angeles, California. He has been focusing on the software engineering, product development, data science. In addition to facilitating acquisition lifecycle management at the Space and Missile Systems Center, his software solution have enabled mission-critical operation across government agency, military installation, global commercial firms, and the aerospace program. Most recently, with the NASA JPL mission Mars 2020. His expertise in software architecture, and also he's been recognized, throughout widely in DoD and the industry. So let's welcome Brandon and Parker for this exciting presentation.
Hey, so great to be here. First of all, I want to check, are you able to hear me? Can you see us all right? I want to make sure we're all set up here.
Yeah, can see you very well.
Perfect. So I'll start sharing my screen. It's a pleasure to be here with everyone. Let me just pull up the presentation. I'm thrilled to be able to give this presentation with my co-presenter and co-author, Parker Southey, who was tremendously helpful throughout the entire writing process as a subject matter expert. And I think that actually this topic of applications for artificial intelligence piggybacks really well on a lot of the really amazing presentations we've seen so far. Just to set the stage a little bit, what I hope to cover is not necessarily a specific deep dive on cutting edge artificial intelligence capabilities, which are, don't get me wrong, they're very interesting papers, and having read a lot of them, there's some really fantastic groundbreaking work that's being done. But rather, I'd like to use AI as a lens through which we can examine some of the challenges that currently face the the rollout or the development of the new space age that we're all really excited about, and that a lot of the other presenters in this conference are actually helping lead, and talk about how AI in particular is a tool that we believe is especially well suited to address some of these challenges and actually help catalyze the development of a real robust new space economy in which outer space is developed for the benefit of all of humanity in new and exciting ways. So to give a quick overview, I'm gonna spend a few minutes at the beginning just setting the stage, talking about where are we, why does this matter, and how does AI fit into the picture. Then I'll turn it over to Parker to give us a little bit of a background on AI, just explain some of the basics and some of the technological foundations for the future discussion. And then go through the actual applications that we believe AI is especially promising for space systems, not only because they're applications that have the capability to dramatically enhance the capabilities of certain space systems, but also because they are applications that we believe are especially important for the overall development of the space economy. So real, real kind of hard-hitting applications, some of which are immediately applicable, some of which will become more and more useful over time. And we'll conclude with just a couple of considerations that are important to this topic, and some recommendations that we have that we discovered in our research and also just in our career experience that are important for bringing about the new space age, and specifically one catalyzed by the new and innovative use of AI. So just zooming out really all the way, we wanted to examine what is this new space age and why is it important? Well, from a foundational level, I personally believe, and I've written a lot about this and studied this a lot, that the human space relationship is one that is special and has been special throughout pretty much all of human history. On the left here, you see a couple quotations we have extracted from our paper that dig a little deeper on this. In particular, when you consider the impact that outer space, and specifically the study and exploration of outer space, has had throughout all of human history, dating from the earliest cave paintings, which have been shown to be not only artistic representations of the stars and anthropomorphizations of the stars and constellations, but also tools that they use to track migratory herds and everything. That as the foundation, moving up all the way to the Enlightenment and the findings of Copernicus and Galileo, and then of course more recently the moon landings and the resurgence of a true space age as we're trying to accomplish these days. I think that outer space has certainly played an outsized role, given how remote and difficult to understand it can be, and really shapes our collective sense of identity very well. So I think that with that as the background, kind of the importance of the human relationship with outer space, we can turn now to the latest development in this exciting and important relationship, which is the potential for a new space age, which is what we're all excited about, what many of us have devoted our careers to, and certainly why we're gathered here today. So to give a little bit of a definition to this new space age, it is been made possible in many ways due to the rapid advances in space technologies, various space technologies, from launch to hardware and software capabilities, some of which we've heard about today from certainly from the previous presentation, and also from the Virgin Orbit presentations as well, the keynote earlier. And it's a really exciting space age that I think is not just exciting, but also it is becoming tangible. Certainly over the past decade, is certainly manifested into real growth and real activity in this sector. Just a couple numbers from FY 2020. We saw nearly $6 billion invested across 135 distinct startups, which is another record-setting year for investment in the space industry, as well as a continuation of the pronounced growth in space systems launched year over year, which I think are good signs that the space domain is becoming increasingly developed, or at least we're moving in a direction towards developing that. So with this acceleration in mind, it is understandable why there is such a fervor around the development of the space domain, and why many people believe that it seems inevitable that, you know, with all the excitement we have now, we are certainly moving towards a time in which outer space will increasingly be used for human benefit, both here on Earth and then wherever we find ourselves. But I think it's also helpful to remember, and certainly the other presenters and folks who work in this industry are aware, that achieving this new space age and all the possibilities it entails is far from guaranteed. There are innumerable risks and challenges that are associated with this. And I find it helpful to reflect when I find myself being over optimistic about the accomplishment of this new space age, that this is not the first time, certainly in human history, that people have prophesized that we were on the cusp of a new space age. Going back to the original rocket pioneers and Konstantin Tsiolkovsky, a famous space futurist who imagined that before too long, we would certainly be using outer space for farming and for agrarian purposes and for you know, all these different utilitarian purposes that would allow Earth to become a paradise, you know, before too long. Now, this is someone who was coming up with these ideas over a century ago, and obviously that hasn't come to pass. Obviously, another example is Wernher von Braun, who, after famously designing the Apollo program and the tremendous success that they had in sending the first men to the moon, less people know that he also developed just as ambitious plans for the first men on Mars, and actually creating streams of rockets and space vehicles that would ferry American astronauts to and from Mars, creating more or less a permanent presence of Americans and humans on Mars in the 1970s and 80s. And he certainly thought that that was going to happen, and he went to the administration at the time and presented that plan for NASA. And they were shut down for budgetary reasons. It was a huge cost and was just not feasible. And so that was another instance in which a new space age that seemed inevitable actually did not occur. And so with that in mind, I think it's helpful to assess the challenges that we currently face and how we can address them systematically to make sure that this new space age, which we're all so excited about, is not another instance of believing it to be inevitable and then ultimately having it fall far short of our expectations. So some of these challenges, which actually have been mentioned throughout the day so far in the presentations I've seen, some of them are obvious. Cost, risk, and distance of the space domain makes it an inherently hard place to reach. And if you are going to reach it, it's expensive and dangerous. So it often is the last choice for any company who wants to do business, because it is dangerous and expensive and far from guaranteed. There's also developing the space ecosystem and a real space economy involves an interdependency of lots of different space companies, you know, one providing services to another, and it can form a sort of house of cards in which if one key link should fail, as we've seen certain space companies fail, like Planetary Resources or other space companies that have folded, it can create a certain fragility that can impair the business models of otherwise strong space companies. So that's a consideration as well. And then there are other considerations that I won't get into, but which I think we're all familiar. Among them are regulatory, environmental, and other national security considerations, some of which are likely to grow over time as the space environment becomes increasingly complex and increasingly crowded. For instance, space situational awareness, space traffic management, and also legal questions, particularly those involving domain rights and the surface of the moon and other planetary bodies. So this is the stage as we see it at this point. And certainly I hope I haven't painted a pessimistic picture, but rather a realistic one in which the excitement that characterizes the current moment must also be met by a methodical approach to tackling the challenges which are inherent to the very challenging environment in which we're hoping to increasingly develop. So into this picture comes AI as a specific technology that, as you see on the quote on the right, we believe has the unique potential to dramatically enhance the capabilities of space systems and also systems of systems, and in so doing serve as a key tool in addressing systematic space domain challenges and catalyze the development of outer space for human benefit. So in this paper that we wrote, we highlighted it as one technology in particular that we believe can play a critical role in catalyzing the development of the space domain and bring it about more quickly and more effectively, and encouraging more and more activity in the space domain. And we go on to identify a few specific applications that we believe, for several reasons, are particularly important. So we'll discuss those later. But first, I think it's helpful to discuss just a little bit of what we mean when we say AI, what it is and what it isn't. And for that, I turn it over to my co-presenter, Parker Saucy, who's the subject matter expert on this. So Parker, take it away.
Yeah, thanks so much, Brendan. I appreciate it. I hope my audio is coming in clear for everybody. I just want to say, Brendan, it's funny that you talk about optimism and pessimism and realism, because I feel like if you work with AI for long enough, you lose the optimism pretty quickly. Realism definitely takes over a fair bit. So yeah, to Brendan's point, what I want to do here is, I originally started this out, I wanted to kind of give a long sort of background on examples of AI, how AI has been applied before, what that might look like here, but I'm not going to do that. I think most of us have a pretty solid idea of the applications of AI. We can talk about facial recognition, we can talk about self-driving vehicles, autonomous vehicles, things like that, autonomous mapping, these sorts of rule-based analyses and things like that. Not going to get into that. I think what I want to do here, and this gets to one of Brendan's points, is I want to really stress the way that we have sort of started to think about AI and the way that I tend to think about it in the context of this greater new space age. About 100 years ago, when we first saw the rise of automation, when we first saw, very, very rudimentary machines that were replicating the ability of a human to do a thing, your ability to make a car, your ability to hammer something, your ability to do something else. Technology was replicating your actions. It was replicating a thing that you're doing. With AI, we're taking that a step further. This is the way I like to think about this, is AI is taking that and saying, all right, well, you've replicated a human action. Now you're replicating a human decision-making process. You're taking a machine and you're giving it some ability to replicate the way that a human makes a decision or arrives at an analysis point or performs some kind of heuristic reasoning or something like that. And the way that I like to think about it is that AI is really the capacity of a machine to do that one thing really, really well. And that's something that I think is really, really key, because what that allows us to look at is it allows us to say, all right, well, how many times with something that we build with a complex system are we arriving at something where humans have to make a lot of decisions and we are in a position where we can't really make all of those decisions live? One of the key examples of that comes to mind is if you take a satellite and you send it into space. You can't apply a ton more addendum human decisions to that once it leaves Earth and once it leaves the atmosphere. And over on the left right here, we talk a little bit about sort of what the implementation of AI is aiming to do. And I think this comes down to the second point right here. What you're mainly trying to do with a lot of modern applications of AI, and a lot of this comes out of how we've talked about it in DoD, how we've talked about it in space systems, how we've talked about it in cyber analysis, things like that, is what you're trying to do is you're trying to mitigate operational risk by enabling systems to basically respond on their own. The same way that if you saw a stimulus come in, if you saw a problem arrive or an issue arise or something like that, you could make a decision to respond to it. You're training your system to do that without you needing to be in the loop. This is something that we talk a lot about in DoD with human in the loop analysis, no human in the loop, things like that, I think are a really key way to look at this. And the other thing I want to do is kind of dispel some of the illusions about AI. I think more than really any other topic in technology, there is a giant gap between what AI is, what artificial intelligence is, what machine learning is, and the way that we like to discuss it. Thanks to Elon Musk and Westworld, it's now very fashionable to say, oh, but AI is going to take over. AI is going to replace us. Didn't you see that Black Mirror? Don't you watch TV? I think Elon's doing all right, but I'll burst his bubble a little bit here. That's not the key danger with AI from my perspective. What we're looking at right now is not the potential that, at least at this moment with current AI, with sort of the view into the future right now of AI that we have, is not that it will get so smart that it will effectively supplant us and replace us. But really, yeah, Black Mirror is definitely weird. The danger is not that it will get so smart that it will replace us and that it will, that effectively supplant our reasoning. The danger is that it will get smart enough that we'll think it's a lot smarter than it actually is. Right now, we're not really at that point where AI can totally get past us and do all of that. So I think a lot of the dangers that we see in AI are really that we will end up thinking that it's way smarter than it really is. As I say here, AI is not magic, it's not foolproof, and it is most certainly not objective. One of my big catchphrases in design is design deliberately. If you don't design deliberately, what you will do is inherently any biases that are in your own rule sets for determining things, things like that, these will make it into your AI models. We see this all the time with facial recognition software, with resume screening applications, things like this. They develop our own biases very, very quickly. And like I said, yeah, AI is not an inevitable replacement for human decision making. The sort of human in the loop, AI assisted human analysis is very much, I think, what we're on the cusp of right now. Completely AI human, like supplanted human decision making, probably a ways off, if even possible to that extent. I think Brendan talked about this with the new space age. In the 80s, we thought that AI was going to basically have completely supplanted us by the 2000s. If even 6 years ago, Uber was under the impression that self-driving cars were going to replace a lot of their own workforce. What we've thought, there's been a very big gap between what we've thought AI would do for us, what we thought it would be capable of, and then what it was actually capable of in those times. And I think in the space field especially, this really comes back to that initial purpose that we talked about, which is mitigating risk in a place where our human responses, our human stimuli, cannot respond to things in the same way as we could if they were on the ground. If we launch something on Earth and it blows up, we can see things right away. If we launch something into space and it blows up, well, there's not a whole lot we can do until we can get up to space and actually see it. And I will hand that over to Brendan, just so that he can get into a few more examples of how I think this applies to the modern AI space and how we can speak about it more. Brendan, over to you.
Awesome. Thanks, Parker. Yeah, so with that in mind of what AI is and what AI isn't, and with the background of how the new space age has developed, how important it is, and the challenges that we face, we have selected 3 particular applications for artificial intelligence that we believe will be especially important. And they move kind of sequentially in terms of their immediate applicability. So the first one, which I'm pleased to say is something we've actually heard a lot about today from the other presenters, is data processing, which I put into 2 different categories based upon the level of implementation of AI in that action. Data processing is a hugely important topic for the development of the space age. I believe that the foundation of the new space economy will not be moving objects, moving kilograms from the Earth to space, but moving bits. And I think we've seen that so far. The companies that have grown the fastest and that have had some of the most startling success and unexpected success early in this new space age have been companies that are doing new and innovative things with remote sensing. So applying AI into the data processing process, you can do it a few different ways. If you apply it passively to a satellite, meaning that the satellite collects information and you apply artificial intelligence to sort the data, to identify points of interest and achieve a higher yield of useful data, as we call it, that is automatically a really interesting and cost beneficial application of AI that allows a smart satellite to achieve a much higher scientific useful yield of data than a non-AI powered satellite. So that's one immediate application. I think one application beyond that that's actually even more exciting is what I call active observation, which is where you have an AI-powered targeting system that is not only handling the data as it comes in, but also using those inputs of data to alter the satellite's manipulation, what it's looking at, how it's moving, what tools it's using to conduct its remote sensing mission to achieve an even higher yield still of useful data per system or per unit cost. So active observation is something that obviously would require different kinds of satellites that are better able to manipulate themselves and have the fuel to do so and the energy to do so and everything. But it's a very interesting application. And the sum total of all this is that satellites and systems which are conducting either Earth observation or any kind of lunar observation, any kind of observation mission, are not only better able to conduct the functions that they are currently used for, but they are also able to now be used for whole new uses that we didn't even think of before. One example I like to give is the company Hawkeye 360, which is using AI-powered observing systems for uses that we have not seen in the past. For instance, looking at oil refineries and the emissions from oil refineries to determine the speed with which the oil is being processed and be able to trade on oil futures and things like that. So whole new uses. It really is a brave new world in terms of what you can do with AI-powered data processing. I'll move quickly through these next two because I do have an eye on the time here. The second one is constellation architecture, which we or categorize, I guess, as the health, efficacy, and then risk of a constellation, which obviously put up these mega constellations of thousands of satellites and sometimes even 10,000 satellites. The intention of having an AI brain kind of at the center of the constellation that has the ability to process the data that is coming in, not only from the satellites themselves, but also from different space situational awareness data inputs and what else is going on in the space environment. It allows the constellation to, number one, prioritize its health and minimize risk, but also should there be any kind of events that do occur or individual failures of systems within the system of systems, it can allow the system to readjust itself while prioritizing efficacy and optimizing efficacy within the parameters of health and risk as well. So that is something that is really exciting, I think, and gives a greater sense of security, not only that your constellation will be safe, but also that it will retain its efficacy and be able to weather storms over time. That I think could be a really interesting application. And then the last one is actually one that we heard talked about in the last presentation, which is facilitating exploration and autonomous exploration. This one is particularly important because I think if we are to fully develop the space economy, that will require developing beyond the parameters of orbital domains. That will mean moving beyond low, medium, and high Earth orbit, and even cislunar orbit to different bodies themselves, whether it be the moon, Mars, or asteroids, comets, what have you. To secure that potential, we would need exploration and highly efficient and effective exploration that can find data that is scientifically useful, that would allow us, whether as scientists or as citizens, administrators, or businesses, to be able to make responsible decisions about what we will explore, what future missions we will send, and how we will send them, and where the real opportunity is in our solar system. So I think that these are three applications that are especially important and can help us address systematic challenges developing the space domain. In closing here, just a couple of considerations that are especially important for allowing AI to have the impact that we would like it to. The first one is just the availability of relevant data. And relevant data can encompass a lot of things. In particular, I think data pertaining to the space environment, so space situational awareness data, is critically important and is necessary for allowing AI to make decisions that are in the best interest of a specific constellation. This is especially challenging because, as many people are aware, and certainly people on this call, space data today is still highly siloed, often for a good reason, but in ways that become increasingly aware the more you, or obvious the more you dig into it. There's not always a good reason for this siloing, and it's worth prioritizing a way to responsibly share data amongst benevolent space actors. So that's one consideration. The other is governance, and this goes back to a topic that Parker covered, which is the well-founded concern about allowing space systems, often which are growing in capacity and in numbers, to behave autonomously. This brings up privacy concerns for individuals. This brings up safety concerns for the systems themselves. And if something disastrous enough should happen, it can bring up safety concerns for folks on the ground and certainly folks in space. So another thing that should be prioritized is certainly the establishment of certain industry standards, as well as potential regulations and best practices around the use of AI in space systems and systems. How should we use it? If there are any instances in which AI cannot be used, for instance, increasingly invasive remote sensing applications, that certainly is one to consider. But we at least need to start having those conversations and implementing them with the same vigor and efficacy that we have been putting systems up in space and kind of going down a path without fully analyzing the potential implications for it. So those are two considerations in particular. And we wanted to leave you with this conclusion, which is really the gist of our paper, which is that the capacity of AI to improve space systems' ability to perform their conventional applications, as well as entirely new use of space systems, makes AI a real special technology and gives it the unique potential to disrupt the space, the most exciting chapter in humanity's space story. So on that, I thank you. I thank the organizers for putting together such a terrific conference. I've loved the presentation so far, and I'm thrilled to have the opportunity to contribute in some way. And if we have any questions or time for questions, which I'm not sure we do, I would be happy to answer them. If we don't have time, I'd be happy to address them in the chat. So thank you all so much. I appreciate it, and looking forward to.
Yeah, Brandon, Parker, this is amazing, and you point out very well that the new space is not really yet there yet. You know, there are a lot of challenges and issues, and that's very, very important. And the AI, as you see, is being used, asteroid, Mars exploration, everywhere. And you just heard from the Astrobotic they're using, so it's everywhere. So it's very good. But one thing I want to mention is you mentioned about the standards. Actually, AIAA has the standard committee, which play a very important part as it has been, for the industry and the benefit of a lot of people. So maybe it's something you can consider. You can help out in a standard committee in AIAA. The AIAA also has the intelligent space technical committee. Maybe that's something that can expand from you already have here. Yeah, you're right. We kind of run short. So if anybody have any question, please type in the chat or Q&A. So Parker and Brandon will, when they while still here, they can type their question. Yeah. So thank you so much. There's a wonderful presentation for your paper. It's really amazing. So stay in touch. So our next speaker, who is also here, is another exciting, new space activity. A company who is a Mason Space System. Along with our speaker is their VP R&D, Mr. Matthew Coons. Our speaker today is Ms. Eva Pettinato. She is a guidance, navigation, and control lead for Mason's XL1 lunar lander. So Eva applied this passion while earning her bachelor's and master's degree from ASU in astronautical aerospace engineering. She was more than 6 years experience as a ground navigation, GNC engineer as she prepared for Mason's first mission to the moon, with Artemis. So yeah, let's welcome Eva. This is all yours.
All right, thank you so much. Thanks for the introduction. I'm Eva Pettinato. I am Maston's GNC lead for the XL1 lunar lander. I'm going to pull up the presentation here. All right. Okay, will someone confirm that you can see the screen with a hexagonal lander and not the remaining pieces of my screen?
Yeah, we can see your main page and a list of other slides on the left. Yeah, you might need to share again for the full screen. Yeah.
How's that?
It's typing. Okay, now it's good.
Excellent. All right. Okay. Well, so we have reached an inflection point in the space market. So it is no longer a question of when we will see the next generation of space exploration. It's happening today, and it is starting with the moon. We actually expect to see 95 missions to the moon in the coming decade, and that's just government-funded missions that are planned. That doesn't include all of the commercially funded missions that we will undoubtedly see. These missions will support a variety of different lunar markets, including science and exploration, education, infrastructure support, and resource extraction. The moon will also serve as a testbed for deep space exploration. What is driving this market? So there are a few major factors here. From a government standpoint, there are growing interests to achieve a sustainable presence in space and advanced science as technology advances and the costs to space decline. From a commercial standpoint, there's a growing interest to develop infrastructure that can support space exploration and utilize the resources that can be extracted. Then there's national security. From that standpoint, there's a growing interest to leverage space for situational awareness. And there's also an opportunity to manufacture large defense systems in space. These drivers will create a thriving lunar ecosystem where lunar landings are commonplace. We will have refueling stations. That's going to enable us to have sample return missions. We'll have established base camps that allow for sustained human presence to actually stay on the moon. We'll have autonomous manufacturing and resource extraction equipment to take advantage of the moon's resources. This is the ecosystem that is our future. So how do we make this future a reality and within the next 5 to 10 years? This challenge is applying an appropriate level of risk and agility to accelerate missions and unlock the value of space. Traditionally, of course, the industry has adopted pretty much a zero risk policy. And what this does is it slows down innovation and limits early stage testing. A new approach is required that applies the right mix of agility, experience, and risk tolerance. So in practice, this approach requires the use of small operational teams, smart autonomous systems that'll increase speed and reliability. It also requires iterative testing with reusable technology to quickly iterate and detect failures before it's too late. This calculated approach is the key to accelerate access and utilization of the moon and beyond. That's exactly the approach that we've pioneered at Maston. We are a rocket company that's enabling sustainable access and utilization of the moon, Mars, and beyond. We're applying our flight experience, agility, and rapid iterative approach to accelerate the realization and impact of space ecosystems. Ultimately, what we aim to do is unlock the value of space, maximize the industrial, economic, and environmental value for humankind. So Mastin's foundation, actually Mastin is a leader in commercial vertical takeoff and vertical landing rocket technology. We pioneered the rapid iterative approach in the new space market by adopting higher reusability and operability standards. We actually have 17 years of experience flying reusable rockets, and it's prepared us for future space missions. For our innovations, in terms of those, we have the most successful vertical takeoff, vertical and landing flights in the industry. We launched the first independent testbed to advance tech readiness for space missions. And now we are even one of 4 companies selected by NASA to deliver payloads to the moon. Mastin's vision, this foundation that we have is enabling us to realize a future where lunar landings are commonplace. The space ecosystem is thriving and humankind is benefiting from the resources across the solar system. We do this in several different ways. Essentially, we have our terrestrial testbed, lunar delivery, and tech development. The terrestrial testbed, within this terrestrial testbed, we test and iterate space technologies aboard our terrestrial landers. That reduces risk on Earth before we end up actually going into space. For lunar delivery, we are able to provide end-to-end mission services, including everything from payload integration and testing to lunar delivery and operations. So our XL-1 lander from the GNC Lead 4 is currently in development. So we have our first mission to the lunar South Pole, and we're progressing towards larger landers too for heavier payloads and even sample return missions. Tech development, we're developing technologies to solve the most pressing space exploration challenges. So for example, we're developing a next-gen landing pad technology to minimize lunar dust. We'll talk about that a little bit later as well. And we're also building a metal oxide warming system, and that's going to help the landers survive the lunar night. So our terrestrial testbed. To give you a little bit more context, so Mastin operates one of the only independent testbeds to mature space technologies and reduce risk on Earth before we fly to space. So we will work directly with commercial customers, in addition to companies that go through NASA's flight operation programs. And what we do, we actually we do a closed loop tethered flights. Then we'll go and do our open loop flights. And because of this high reusability and operability standards, we actually can iterate the technology and retest within 24 hours. We've iterated and tested. So this is for our entry, descent, and landing testing. We have done this for terrain relative navigation, hazard avoidance, and actually several different guidance algorithms and systems for dozens of customers. So one example is we've worked with JPL's Lander Vision System and a G-fold algorithm that we tested on our Zombie rocket. This allowed the LVS allowed Zombie to precisely determine its position without requiring GPS, which is very important as we leave Earth. And the G-fold algorithm calculated the optimal path to divert Zombie to a target landing site in real time. So this approach actually helped JPL test the technology early in the life cycle so they could quickly advance technology readiness for the Mars mission. We all know about Perseverance and the rover that's now on Mars. And just to give you an idea, so here is the landing site. So you can see the Mars Perseverance landing site there, and how precise they were able to be on that landing site in comparison to Curiosity, Phoenix, and Pathfinder. So it's actually quite a bit more exact. So we also actually do a lot of payload integration, surface interactions, and sample collection for dozens of customers. Recent example, we did this for Honeybee Planet Back. we tested and matured to validate its lunar sample collection capabilities. So PlanetVac works by blowing gas into a planetary surface, stirring the soil and rock up into a collection chamber. And in its simplest form, PlanetVac attaches to a spacecraft lander leg. So the device is ready to work as soon as the lander touches down. We worked directly with Honeybee and NASA to test the sample collection technology, again on our Zodiac rocket, and advance its technology readiness. So these tests helped Honeybee to get their payload sponsored by NASA on a CLIPS lander in 2023, in addition to a Martian moons exploration mission with Japan in 2024. So lunar delivery. We are now applying our terrestrial flight experience to lunar delivery missions using the same rapid iterative approach. With our mission partner, we provide full mission services to transport customer payloads from the Earth to the moon. And that's everything, including payload integration testing to lunar delivery and also surface operations. Mastin was selected by NASA to deliver payloads to the moon under the Artemis program's Commercial Lunar Payload Services Initiative. So that's CLIPS. The XL-1 will be put on a translunar injection by SpaceX. We're working with SpaceX for the launch vehicle. Once in lunar orbit, we're going to fire, we have 6 main engines and 12 RCS thrusters to slow down, and it will autonomously descend for a soft touchdown. Upon landing, the XL-1 will actually operate for more than 12 days. So once it hits lunar night, not so much anymore, but this will be the first of many missions to help enable a thriving space ecosystem. So a little bit about our landing site. XL-1 is going to land near the Hayward crater at the lunar South Pole. And the South Pole, it's actually in the midst of several mountains. These are called massifs on the moon. And Hayward crater is adjacent to the Malapert Massif. And the change in elevation exceeds 8 kilometers. Now, 8 kilometers doesn't seem like a very big value when you're talking about horizontal distances, but this elevation change is actually very close to the elevation of Earth's Mount Everest above sea level. So this diverse topography offers the potential to explore both near and deeper ice reservoirs with the purpose of searching for signs of water. So we may actually may find water, but we also have the possibility of detecting volatiles like methane, carbon dioxide, and ammonia. So the XL-1 lunar lander draws heritage from Mastin's 5 terrestrial landers and benefits from 5 years of collaboration with NASA through the Lunar Catalyst program. So the lander is actually equipped with advanced propulsion system. We're also going to have a terrain relative navigation system to increase landing accuracy and mitigate risks. And to date, we've manifested 8 NASA-sponsored science and technology payloads to fly on XL-1. Their purposes to assess the composition of the lunar surface, detect volatiles such as water, methane, carbon dioxide, but also to evaluate radiation, to kind of go through and advance those human missions that are planned. So these payloads will consume a fraction of the lander's total delivery capability. So we are welcoming additional partners to join Mastin Mission 1, in addition to future missions that will be available at all near-side lunar locations. We're also progressing towards larger lunar landers to have more payload capacity, but we also are advancing technologies to survive the lunar night. I mentioned before, XL-1 will be on the moon for 12 days, but that does not yet survive the night. So we are working towards getting those future technologies. And that will actually enable us to have far-side lunar missions where the conditions are much, much colder and also harsher. So as the lunar ecosystem grows with pre-placed equipment and infrastructures, these landers will be equipped to refuel and return to Earth with samples. So lots of future development happening for future landers. And this is all kind of involved in these technological developments that we have going on. So for example, for surviving the lunar night. So lunar nights last 354 hours. So that's 15-ish days, just under 15 days. And surface temperatures reach 283 degrees Fahrenheit below zero. And permanently shadowed craters can actually reach negative 382 degrees Fahrenheit. So these extreme temperatures will cause lander and rover systems to fail. What we're doing is we're developing a warming system that uses a chemical reaction to deliver heat through the oxidation of various metals like lithium, aluminum, magnesium. And this will enable the landers, rovers, and payloads to survive the lunar night and operate in permanently shadowed regions. Another really big problem landing on the moon, we need to mitigate lunar dust. High velocity regolith ejecta, lunar dust, caused by robotic and human landers is a major challenge. And this dust can actually damage the lander payloads and surrounding infrastructure, and it can pose a hazard to astronauts. So to solve this, we're developing flight alumina spray technique, fast landing pads that use plasma spray to inject feedstock particles into the rocket engine nozzle and coat the landing area prior to landing. So this unique approach will minimize the harmful dust particles and enable more landing locations for complex lunar, Martian, and even asteroid missions. We're also developing a new additive manufacturing technique that enables cooled engine components, such as injectors, to be 3D printed in a single piece using a wider variety of rocket metals, such as aluminum, copper, and such as aluminum, copper, and inconel. So this approach enables injectors to be 3D printed as one part instead of 100 individual parts that would have to be assembled. So as a result, we can actually reduce costs by 60% and reduce production time by 92%. So this helps improve the performance and thrust of novel engine designs. When we are also using the additive manufacturing techniques to 3D print high power density electric cryogenic pumps. These actually can be used in 5,000 pound thrust engine propulsion systems and provide superior throttling capabilities over traditional turbopump cycles. These pumps will enable a more affordable propulsion system for smaller launch vehicles and landers, and they will allow propellant transfer and refueling for sample return missions at the moon and Mars. So you are welcome to come fly with us. If you have a payload that you would like to have fly on XL1 or lunar landers, you can definitely let us know. And we have, as you can see, tons of technological advancements that we are working towards. So I will go ahead and close this, and we can go through and see what questions everybody has.
Oh, great presentation. Yeah, that's wonderful. Yeah, Mason is just amazing. You know, has been doing one, and I'm very, happy to see you're developing this dust prevention system, also the ISRU. These are really pioneering and leading the industry. It's fantastic. It's what really people need. I was actually about to ask you about the dust, and you mentioned it. You're really ahead of everyone. That's just amazing. Just while we're waiting, folks, you're welcome to type your question Q&A or click raise hand to ask question. But while people are actually have a quick question, why the XL1 is the first? Look from your there's a description. It looks like SL1 is going to be the first to go to the moon. Is there any specific reason for that?
So XL1 is going to be Masten's first lunar delivery. I don't believe that we are going to be the first one as part of the CLPS.
No, I mean Mason's first. You are right, Mason's first.
Yes. is your question, why is it the first?
Yeah, why Mason pick XL1 as the priority? Is there any specific reason?
So we're actually designing XL1 to be able to hold all of the different payloads that have requested a ride through the NASA program. So we're actually developing it and innovating with the XL1 lander. But we're pulling on a lot of our terrestrial landers and all of the technological advancements that have been done with those landers. So we are pretty good at landing, but it'll be the first time that we land on the moon.
Yeah, this is going to be ultra important. As I said, earlier, we have this space architecture events, and the space architect has been designed all kind of beautiful, safe habitats, bases, or those kind of things. But you cannot do anything. You cannot deliver to the surface, or you cannot have that is not going to be anything useful. Especially they are talking about ISRU, but how do you do it? How to deliver those things? It's going to be critical what the Mason can provide at that time. So I have more questions, but I think there's a question in the Q&A box. I'm not so sure exactly what you mean, but I think he was talking about. But take a look. I think he was referring to your rocket engine. Or maybe it's something else.
What do you use for the plasma spray? Actually, I'm going to go ahead and let Matt take that. Matt has done quite a bit for the Fermi AM and some of that work. Matt, do you know what we use for the plasma spray?
Yeah, so I think this question is probably about the fast landing pads that we're working on through the NASA NIAC program. And right now we're using a alumina ceramic particles for that spray process. So they get heated up in the engine and then blasted out towards the lunar surface where they'll create a landing pad as you land.
Yeah, it's a very good point, because you can see a lot of, that's why AIAA comes in, why we are doing all the space architecture work with Mason or company, because personally, I've seen a lot of, space enthusiasts. They're posting some pictures that, the landing pad was right next to their habitat, but there's a very interesting question, it's going to be very hazardous if you're landing, as Matt just and Eve also mentioned. So you need to design something safe. There are a lot of chemical, poison, hazardous issue. Thus, you need to be safe. All right, so I think Alexander also has another question. Then it will be Steve, yeah.
Okay.
Hi, Eva. I'm shamelessly leading into my presentation next, so I have to apologize for that. But I wanted to ask you about the system you use for power. You're talking about chemical power to heat the thing up when it's on the far side of the moon, and you're talking about solar panels to power that thing. And when it's on the dark side of the moon, of course, that doesn't work either. And you have a rover that operates. I assume that's all through electrical battery power. Is that right?
I'm going to go ahead and let Matt take this one
Okay.
too, just because he probably has a little bit more. I've been very focused on the XL1 lander specifically. Matt, do you know?
Yeah, let me take a crack at this. I think you're asking about the MOWS technology, the metal oxide warming system, and how
That's one of them, but you also power your rover and you power your systems in your lander as well. And I'm thinking you're around the 100 kilowatt or 100 watt to maybe a kilowatt at most power. And I'm just wondering how the solar matches with the batteries, matches with the heater system to give you the power you need for the whole time you're up there.
I don't think we've released any specific numbers on powering the XL1 vehicle, but
Okay.
I will say it is, of course, complex systems and thermal and EPS design problem. I cannot speak to the rover. That's actually Astrobotic. Feel free to chime in and talk about that if you would like.
No, that's fine. I was just curious.
Yeah.
Yeah, actually, this is another interesting, another new design, pioneering design to heat the, the lander. That's actually over the night, lunar night is very important. And you can probably get, figure out why Steve is asking this, because his next talk he's going to talk about nuclear power. So I think maybe Mason can consider, thinking about nuclear power. something like that.
I think we would love to have an RTG or something on board so we live indefinitely on the surface, but they're kind of expensive and can be hard to get at least as far as I'm aware. So
yeah, I understand, but I think Steve is probably not going to just try to limit himself as RTG. And from your and this and a while ago we saw a Caltech paper. I think they were proposing something for the moon base. They also need a lot of power. So I think Steve's power is not just the RTG. Maybe it's a power unit that's sufficient to support, maybe charging for the lander or rover or for the operation. Well, here's the next speaker. Now, if you stay a little longer, you can see what he's going to say.
I will be listening with rapt attention.
Wonderful, wonderful. Yeah.
Well, I appreciate the spoiler alert.
Yeah, this is fantastic. You guys doing a wonderful job in the new space. It's vibrant and so we'll stay in touch. This is fantastic, and really appreciate. So come back again and tell us your wonderful progress. So thank you, Eva. Thank you, Matt. It's fantastic.
Excellent. Thank you so much for having us.
It's our great pleasure. Wonderful presentation.
Thank you.
All right, so our next speaker is here, Mr. Stephen Curtis. He has a very diverse and a very excellent background, everything you need for space exploration, especially in regards to power systems. He's the former president of Health Physics Society and American Nuclear Society. There are many more titles, but we just focus on this one here. He has 30 years. He's a 30 years resident of Nevada. He was, and with a close association with this to the Spent nuclear fuel issue and a 50-year career with DOE Nevada. He attended his first Yucca Mountain meeting in 1981 and has been associated with the project academically and educationally ever since. As a student employee, Mr. Curtis was employed at the Whole Body Radiation Counter for people at the Environmental Protection Agency campus at the University of Nevada, UNLV. He began his tenure at DOE Nevada as a project and operations officer for the Soviet verification program. After the testing program ended, he was recruited into nuclear emergency response, where he served as a nuclear technical team leader for nuclear emergency support team and the radiological consequence management teams associated with the Federal Radiological Management and Assessment Emergency Management Intra-Agency Nuclear Response Posture. He concurrently served as program manager in such program as NEST Research and Development, the Non-Proliferation Experiment. Well, basically, he also had worked on the counterterrorism effort and also the DTRA and Omega, the several important things related to the Soviet testing tunnels. Mr. Curtis also served in both the active duty Army and the Nevada National Guard for a combined 11 years as an armor officer and a strategic communication expert. He was responsible for all Army communication strategic testing throughout the European and the Middle East major commands. His tactical experience includes a rotation at the National Training Center as an armor company commander, and 7 years as staff officer and a company commander in the 221st Armor Battalion in Las Vegas. After departing the DOE, he was engaged in development and integration work at UNLV and the Desert Research Institute, DRI, in areas of national security. As proposal manager, he led successful team in Nevada to secure the FAA designation as a FAA National UAS test site. He currently works as a subject matter expert and a senior consultant to Readiness Resource Group in areas of training, exercise, counterterrorism, local responder, emergency management, nuclear technology, and health physics. He has served as president of the Nevada section of both Health Physics Society and the American Nuclear Society, and is currently working under a small grant from American Nuclear Society Operations and Power Division to develop and conduct education seminars in Nevada for the public and for government officials. He holds BSEE and a master's degree in health physics, both from UNLV, and he has been active in STEM activities for schools as a 27-year volunteer coordinator for high school science bowl, co-founder of the Skybot Challenge, engineering-based competition for students in 3D robotics, UAS, and a consistent speaker in Clark County School District classrooms to engage students to find their passions through continued education. So this is really fantastic, and a lot of things Steve can work together with us, and as he has been with the Las Vegas chapter. So without further ado, let's welcome Mr. Stephen Curtis. Oh, you are muted, Stephen, you are muted. Great.
Let me try to share my screen.
Go ahead.
Okay, let's bring this up. Let's see if I can get a slideshow on here. Okay. I hope you guys can hear me, and I'm stepping through this. So I just wanted to give you an overview of space power. I'll tell you, I'm not a space engineer or a space scientist at all, but I was very, as a child, very into the space programs, watched the Mercury flights and all that stuff. But my background is in health physics, as you know, and nuclear engineering and nuclear science. So I want to talk a little bit about nuclear power on Earth, because this is very misunderstood by most people. And part of my focus right now is to try to get this better understood by people, because nuclear power really has some advantages that we can use. It actually has the best industrial safety record of any power producing technology. Many people seem to be worried about nuclear technology, but it has the best industrial safety record. It produces 20% of all power in the United States and 55% of all clean energy in the United States. Okay, next nuclear generation plants, next generation plants are 100% protected from meltdowns because of their intrinsically safe denied. In other words, you can walk away from them; they will not melt down. There exist fast reactor designs, and this is my program I'm focusing on right now, that can use the existing stockpile of reactor used fuel, and there's enough of this used fuel around to power the U.S. for 100% clean for 20 years, 100% clean energy. So I want them to start moving in that direction. And there's no more compact source of power in use today, which is why it's good for space power. And so we'll talk about that a little bit. And I just want everybody to know that we're way falling behind that technological and economical advantages of nuclear behind other countries like Russia, China, India, and even South Korea. Okay, so we heard all about power systems today, and what's amazing to me is that the power systems they talk about them as already being there. That's not part of the risk assessment when they're going to space. We talked about all kinds of navigational things and space radiation and all the problems that they seem to anticipate, but power was not one of those. So that's a tribute to the history of how these people in the space program have designed energy systems. And I want you to keep that in mind when we're talking about this. And there's several different kinds. We talked about the RTGs a little earlier, and they're basically work on the fact that plutonium-238 decays with an 83-year half-life, and that decay causes heat and builds it up to about 600 degrees Fahrenheit in the RTGs that you're talking about, and they extract that energy through a thermocouple, and they produce on the level of hundreds of watts. And that's all of these RTGs depend on the half-life of the radioisotope, but plutonium-238 has an 80-year half-life, so it's essentially, for space missions so far, it essentially lasts forever. And we're still talking to Voyager before they turned the antenna off and went into interstellar space. So the other part is fission reactions. So as you know, fission heats things very, very quickly. There's a lot of energy released when you put fission products in, and there's designs, like I said, that can actually work as the fuel inside the cooling liquid, and they're liquid salts. So there's two types of reactors, basically the slow neutrons, which are the light water reactors we use today. They use water to slow the neutrons and react with the predominantly U-235 isotope of uranium. And then there's fast neutron reactors that work on things like thorium, and we can actually fission other aspects of the uranium and some of the higher elements that are formed in the light water reactors, which is where you get the great advantage of recycling the used nuclear fuel. So again, fission reactors split atoms, and they can produce, every time you split an atom, you get about 50 million times more energy than you do if you burn a coal atom. It's a hugely advantaged, hugely dense system. And so there's a lot of advantage to using those in the space system. Okay, so we know that solar is not good for deep space, and it's not good for anywhere you can't see the sun. And so there are systems developed in the system, early days, that called the Systems for Nuclear Auxiliary Power SNAP systems. And there's SNAP numbers, SNAP 1 through, I think there's one up to 50. And they're all, so that's the two types of the SNAP systems were the radio thermoelectric generators we just talked about, okay? And the Russians even have one that's using polonium-210, which is 147-day life. There are also experiments with some fission products, strontium-90 and cesium-137, and cerium-242 is a transuranic element that comes from taken out of the reactor waste. And that it's 147 days for polonium-210. So that's actually more efficient than the 238 because it's a shorter half-life, but it doesn't last as long. Still, for going to the moon and powering systems, that seems to work okay. So there's only been one reactor launched on a United States mission, and that's SNAP-10. The rest of them have all been RTGs. Now there is one called SNAP-50 that's actually a fast reactor, and we'll talk about that later, but that's all experimental right now. This is the nuclear rocket development system on that was done out here in Nevada on the Nevada test site in the early 60s, 1961 to 66, they ran that program. And it is a propulsion system, not running power on the spaceship itself, but propulsing into space. And it truly was an application that could work. It actually could work. And they had two huge hot cells out here. One's destroyed, one's still there. The EMAD facility is still there, but they're going to want to destroy that as well, which I don't like because it's hugely useful, but they move on. So this is actually a system that works best for going from the moon to Mars or beyond. It really does have applications where the propulsion system works best out there. It wasn't really great for moving systems from the Earth to space. It could work, and there are applications that it can work. And there's a very good description of it on that YouTube video. I won't show it to you, but you can look at it if you want. And it's pretty interesting. Here are, oh, I didn't change out my title on that. Okay, here's some reactors that they've used in the past, and you can see the pictures of them on the ref. So we talked about wattage and applications of how much power you need to run the actual space systems. You need on the order of hundreds of watts, not megawatts or like kilowatts or megawatts. And so those are fine for running systems that are not going to be forever systems, not running forever. And they work well now on missions that are out in space now, especially deep space missions where you can't get the solar applications. And again, the Russians used that polonium-210 system on a couple of their lunar missions, and they're still up there. The RTGs is what you were talking about before, the Pu-238 radioisotope that lasts a very long time. And here we see the bottom, there's a little design of the SNAP-50 fast reactor, something I did not know about until I did my research for this. very, very interesting. And you can see that approaches 5 megawatts. That would be a power source that could supply a space colony with sufficient power for actually people being up there. And that's something you're going to have to think of in the future. If you're going to put people up there, you're going to need a lot more power. And so here's where some of them, the power systems were used. Voyager 1 and 2, like I talked about, they used something called a mega 100 watt power source. And that was still operating, plutonium-238 was still operating. Like I said, when Voyager went into interstellar space, they were still getting messages from it, and basically just turned the antenna off because it wasn't sending any data worth knowing. It's in interstellar space, but it was still working, which is amazing. New Horizons, that was a different design of an RTG. And then Viking 1 and 2, Pioneer 1 and 2 used Snap 19, which is very, very effective, much less power. So it just operated the systems on the Explorers and the computers, but a lot less weight. So we all know that weight is a big issue when trying to put things into space. Okay, the Soviet Union and Russia, kind of the same thing when I think about them. They usually mostly use fission reactors. We talked about the polonium-210 issue on the Likud. You've probably heard of plutonium or polonium-210 as the one that killed the spy when they gave him some in his food. But it's also a decay product. It decays with alpha and heats up the material that it's in, and so can provide a thermocouple and provide energy. And they've also used plutonium-238. And there's a very, very good reference down there for if you want to look. There's lots of others. These are just examples of ones I've found. So what are we going to do in the future? Where are we going with this in the future? Okay. Now, the thing with fission power is it is heavy. Okay. And so we don't need any more weight when we're trying to launch things into space. And so as dense as the power source is with it, it's also heavy. But guess what? Chemical propellants are heavy, and any other idea that we think batteries are heavy. So you're going to weigh those design perspectives as you're looking at this. And so what I'm trying to get you to do is think of nuclear not as dangerous and expensive, although plutonium-238 is expensive, but like anything else, if we mass produce it, it'll come way down in price. We can make all the plutonium-238 we want to because we got stockpiles of neptunium-237, and all you do is launch neutrons into it. You can make plutonium-238. We just don't do it. And we've counted on the Soviet Union and Russia to make all our plutonium-238 for many decades, and now we're running low on it, and we're going to have to start making our own, which we are. But it's just a matter of when you talk to space business, what aspect of it are you going to need to do? How much power are you going to need? And you're not going to do everything with solar and chemical propellants when you start putting people up there. So these are thought processes you want to go through, and nuclear provides a very, very advantageous way to do it. So we talk about fusion. We're not quite there on capturing energy with fusion, but the nice thing about fusion is done with light materials. So fusion, you're fusing hydrogen, so it's the lightest element. The trick with that is you need high energy systems to fuse it, and plasma systems, and they're working on that now. And there's some companies that claim they can have a working reactor in 10 years, but excuse me, I don't think you'll see any of that for at least 3 decades or maybe more. But that would be ideal for space. If you could decide how to contain fusion reactors in space, a very light material produces even more power density than fission. We also are talking about this space-based solar, where you just put up a huge array of solar panels, and you can radiate power with microwaves, and that works well, although they still haven't quite decided how to do it radiated to the earth. I think it's possible in the future, but they're not there yet. So if you did launch a bunch of solar panels into space, they'd work for a long time. I think probably by then you'll have a longer life on solar panels. The panel life for solar is about 20 to 25 years right now, but I think that would be expanded in that period of time. So you might be able to put something up for 50 or 60 years and just relay energy down to the earth. And a lot of scientists thinks that is possible. China's going to develop a space solar power station called Omega. And they are way down that road, and they are way advanced on this system. And so again, this is another thing we need to maybe think about stepping up our game. So what we said, that nuclear rockets like the NERVA rocket maybe not make sense to launch payloads to space right now, although they can. And a large factor in that is people are so afraid of nuclear that they just politically have not advanced that system. But when you're looking at going from the moon to Mars, it makes a whole lot of sense, because you get a lot of thrust off of that that engine. And basically how a nuclear rocket engine is, it heats up hydrogen. So you have a supply of hydrogen and you send it through the reactor. Well, the nice thing about hydrogen is it moderates neutrons. So when you don't have much hydrogen in there, there's little power coming from the reactor. But as you flow hydrogen through, you get the hydrogen heated up from the propulsion, for the heat and the propulsion and the Bernoulli's principle. But you also mitigate, you also slow down your neutrons. You moderate your neutrons. And so that means you get more power out of the engine. So the more hydrogen you flow through it, the more the power will ramp up. And then of course you get more thrust from that. So that's a very simple idea of how the engine works, the nuclear rocket works. And so there actually is research going on. After that rocket program stopped on the test site, a lot of the money went out of it. But there are people that are looking at it now, and DARPA has some money putting into it with General Atomics, developing a rocket called Draco. Okay, now they're going to use high assay, low enriched uranium. So the uranium you use in a light water reactor is about 3 or 4% enriched. If you get above 20% enriched, they call it high enriched uranium, and we don't use that for anything except reactors. Naval reactors use it. Reactors we can defend. We don't put that on the commercial market because of the proliferation efforts. So there are going to be commercial reactors with enrichments up to 19.99%. Can't be over 20. So by definition, it's not going to be over 20. And this Draco rocket is one of those developing. I know HALEU exists right now, but there's a company that's negotiating with the government now to produce some. So that rocket looks very promising for launching into from Earth to space. Okay, so this is a very, very quick overview, and I was really, really hoping you guys would ask me a lot of questions on this, because like I said, I will mention one more that I forgot to put in there, and that's called the KRUSTY, K-R-U-S-T-Y, which is a kilopower fission reactor developed down at Los Alamos, and they actually tested at the test site, and NASA's putting a lot of money into this one. So this wouldn't be one that would work as a rocket. It would be one that would supply power to a base or to a lander, and that's now not 100 of watts. It's into the kilowatt range, and so NASA's looking very, very favorably at that. So you guys who don't really routinely think of nuclear power as a space-based power option, I think you ought to ask me some questions, okay? Because there's a huge amount of potential in this whole technology, and I think that's the way it's going to go. I think you're going to see a lot more nuclear power on Earth, because there's about 30 or more companies now privately capitalized that are developing next generation reactors. You just don't hear about it all the time, but that's the way things are going. And there are, again, a lot of advantages to nuclear power. They're very, very compact. They're not spread over square miles like solar panels and windmills are. So it's something our society needs to look at in the future. So I think you're going to see more nuclear power on Earth as people become more comfortable with it, learn more about it, and as politicians start moving in what I believe a sensible direction is. It's like I said, you need to educate the public. There's a lot of misinformation out there. I hope you guys ask me a lot of questions, because probably what you understand about nuclear is probably not all you can understand about nuclear. And I'd like to clear some of that if I can. And we all worry about the used nuclear fuel, which you guys call nuclear waste. but you can actually use that as fuel for next generation reactors. That's what I'm trying to inculcate now, because you can get clean energy equivalent to the current use of the United States for 250 years if you do that. But again, people are afraid of nuclear, and it's not a real popular idea right now. The issue now is that there's so much of a skew towards renewables and so many subsidies for renewables that they're pricing base load power out of business. So coal, natural gas, and nuclear energy is the base load power that you need to have on all the time. There's complications with solar being only when the sun shines and wind only being power when the wind blows. So there's other renewables to that include burning wood, burning garbage, and burning biofuels, which are polluting types of energy, but they're classified as renewables eligible for subsidies, and nuclear is not. It's a real problem right now, and it's actually kind of causing the free market to shrink up. And we all know when the free market is artificially skewed, that customers for that product do not come out well. And so if you understand that the energy business in America is more than $1 trillion a year, it's a huge, huge business. So how that business gets divvied up in the future is something that we should all be concerned with. I will say that the national grid system is in a situation now where it could fail. There's cyber threats against it all the time. There is cybersecurity is a terrorist threat, as is something called electromagnetic pulse, EMP. There's actually weapons they can develop and explode that can cause enough electromagnetic pulse on the system that it blows out all the transformers in the United States. We don't have power for months on end. So these threats exist with the national system, and I'm advocating for Earth Power to be microgrids powered by next generation reactors. Again, very radical. And I'm the Galileo of nuclear power now. I'm not finding a lot of friends in the existing energy business, but such as it is, it's much better for people. So space nuclear is viable, and it has a long history. And I will stress again that you guys, when you talk about your systems, do not talk about energy and power as an issue, as a risk factor, because they've done their job so well that you count on these existing systems to be there for you. I haven't heard anybody today talk about any space system that they talked of having energy and power as a risk. There's lots of other issues they talked about, but they always say that the energy will be there. And so it's a real tribute for people who have worked on this in the past. Of course, lighter is better than heavier. So if you ever develop fusion, that would be a great advantage over fission. If you use water coolant, that could be problematic. Maybe the moon's got water, but Mars probably doesn't have water, or if it does, doesn't have enough. And water to haul around would be very expensive. So any kind of system that uses something else besides water as a heat transfer system, that's why they're using thermocouples in RTGs. And so the long-term view of power looks to be something akin to fusion power on Earth. And there's a lot of people talking about these large solar arrays floating in space and geosynchronous orbit, microwaving power down to the Earth, but I won't live to see that. And I think it's going to be half a century away before any of us sees that. I think that's what I have. I will show you some of my references. This is a very good book, Space Nuclear Power. I found this one for $9 at a book sale, but they're selling for about $120 on the market. And that book was published in 1985, has everything you want to know in every detail that you probably can't understand of the systems I talked about today. There's a NASA document out, that one there, and then the Flights to Nuclear Power and Advanced Space Exploration is actually an AIAA publication that's very, very good on this stuff. And there's a reference for space-based power. So I am ready to turn it over and take questions. Did anybody hear any of this?
Yes, this is wonderful. First, I think Joseph has been waiting. I think he has
okay.
Yes, Joseph, go ahead.
Hello, Stephen.
Hi.
Thank you very much. I think it would be useful for the audience to understand that there are two different types of nuclear systems using either isotopes or fission right now. In the future, perhaps plasma fusion devices. Also, there's a difference between power and propulsion utilization. But in all cases, nuclear systems are basically just providing a heat source.
Correct.
Which is then utilized through either static energy conversion technologies or dynamic energy conversion technologies to produce electricity. That electricity can be used in electric propulsion systems for nuclear electric propulsion. In the fission side, you mentioned kilopower. Kilopower was kind of a fission system test that was done in Nevada in 2018. And it probably will not survive through what's going on today. But a contract will soon be let for fission surface power design and development. And what's needed is, I think they're going to start with a 10 kilowatt electric system. Very likely will use dynamic energy conversion on the surface of the moon. And that system could potentially use water. You mentioned water as being a bad actor, but it is not a bad actor. It's just a question of what regime of temperatures are available. And on the moon, you also have 1/6 gravity, which is advantageous from natural circulation cooling standpoint for any shutdowns or accidental issues that might occur. The real focus today has been on nuclear thermal propulsion. And that was looked at back in the late 50s, 60s, and into the early 70s under the Rover NERVA program by NASA and the Department of Energy. And 23 reactors were tested in air at Nevada at Jackass Flats during that period. And we learned that it is feasible. That program died, however, because there was no follow-on to Apollo to go back to Mars. The intention was to go to Mars then. But during that era of the early 70s, we had an oil embargo. There were all kinds of things happening geopolitically. And Apollo died, and we retrenched, if you will, and spent our dollars on cleaning up the legacies of the past, as it turns out. Today, there is a need by NASA. They want to go back to Mars. And the reason that you want to use nuclear thermal is because it provides high thrust, but also high efficiency in terms of specific impulse. Twice the specific impulse of liquid hydrogen and oxygen systems. And that means that you can get there faster and get back faster, which is critical because being in zero G has detrimental effects to the astronauts and also subjects them to very, very high energy charged particles that make up galactic cosmic radiation.
Correct.
And you've got to do things faster. Either that or you've got to carry along a lot of passive shielding weight, which, as you know, and you mentioned, mass is king in space. Okay?
Correct.
So I just wanted to bring those to your attention. Also, it was never intended that nuclear thermal propulsion would be used for launching from the ground. There were some wild analyses that was done back in the 60s and 70s, but no one in his right mind would do that. I mean, you're building up fission products. As soon as you turn this thing on and develop and operate it at power. And so everything that's being pursued now on nuclear thermal and nuclear electric propulsion is basically in-space propulsion or high velocity transport. Okay, because that's important from a safety standpoint. Otherwise, we'll have people shooting at us and eventually killing those programs. So from a safety standpoint, you have fresh fuel at launch. You don't turn them on until you're in space in a nuclear safe or orbit or trajectory. And excuse me, you also design them so that for any overpower or undercooling events, you don't have a disruption of the core, loss of mission, and the potential for radioactive stuff coming back within the Earth's atmosphere. The reentry of a hot reactor back into the Earth's atmosphere is unacceptable. And the Russians did that. Actually, the Soviet Union back in 1978, we had a reentry of Cosmos 954 into northern Canada. Fortunately, it was in an unpopulated area. Okay, thanks.
Oh, yeah, it's great summary. I appreciate that. I agree with all of that. I think that there's a perception of people in the United States and maybe throughout the world that are way over afraid of nuclear. And like I said, I'm happy to talk to anybody and answer any questions about that. But radiation is not nearly as dangerous as they lead you to believe in the media. And there are very safe ways to handle nuclear. And that Cosmos reactor was, and they did search for that. They searched for that in Canada. That was part of what the teams I was associated with did, although that was before I got there. They went up to Canada for months and they finally found every piece of it, which was no easy task in the middle of winter. So yeah, there's risk in everything, but we got to put risk in perspective with benefit. And I think you're going to see nuclear with a huge benefit in space power.
Curtis, if I might add, the difference between launching radioisotopic systems and fission systems is quite different. I mean, in a fission system, you have uranium-235 to some extent, whatever the enrichment is, and uranium-238, either with oxygen, oxides, carbides, nitrides, oxycarbides, for example. With a isotopic system, you have an inventory of radioactive material that has a relatively short half-life. Plutonium-238 oxide, plutonium-238 has a half-life of 87.5 years. Uranium-235 and 238 are 10 to the 7th and 10 to the 8th years half-life. So they're not very radioactive. Okay, they do present an inhalation issue if you can vaporize such that those small particles can be inhaled into the deep lung. And the same is true with isotopic systems. So for isotopic systems, what you have to prevent is the release of that material into the biosphere. And that's why they're designed very robustly with multiple containment barriers. For fission systems, you want to ensure that if you have a launch accident or a reentry accident, that you do not have an inadvertent criticality that could produce a fission product inventory and produce a direct shine to anyone or anything that happens to be around it. And that
it has to be well contained, which actually that Cosmos one was
contained. It's not a
pretty
question
much
of
well
containment
contained
at all. Fission systems do not require containment. What they require is ensuring that you do not have a criticality. And that can be done with fast spectrum systems by having spectral shift absorbers. They normally operate on a fast spectrum, but if you happen to dunk them in water, wet sand, or propellants, which normally would give you a positive reactivity insertion that could create a criticality, having those spectral shift absorbers built into the core do not affect you during normal operations, but provide that measure of shutdown margin if you have an accident that involves a positive reactivity insertion that thermalizes the neutrons.
Well, you want to stop the neutrons from fissioning. You want to absorb the neutrons. That's the idea. And so, yeah, there's plenty of safety systems that can do that. And that's pretty well understood. So you're right. I haven't heard anybody talk about launching into space lately, but this Draco system they're talking about that DARPA is developing with General Atomics, I got to look further into that.
It's in space also, Stephen.
Is it?
Yes,
okay.
It's totally an in-space system.
Okay.
Okay.
You still have to get it out to space though. So, but there are risks, and all my point is that they're probably worth taking. I mean, yeah, we might have an accident. We're going to prevent damage from that accident as much as we can, and we're pretty good at that. But if you're so afraid of it that you don't even look at the benefits, then you're really selling yourself short. And I think that's what people think of when they think of a nuclear today. They don't think of the benefits. They think of the risk outweighs the benefits, and it's just a
Even
matter
there
of
is a
education.
document that's been signed. It's called the National NSPM 20. It was issued in August of 2019. And that document, which is a presidential directive, requires that for a launch of a fission power system or propulsion system into space, that the probability of a inadvertent criticality, regardless of the consequences, must be less than 10 to the minus 6.
Yeah.
Okay. Now, we know that basically you can have a launch accident with a probability on the order of 10 to the minus 2. So what that means is the conditional probability of having an inadvertent criticality given an accident has to be limited to 10 to the minus 4 or less.
Okay.
And that can be achieved.
Sure. Yeah, we got a question that asked about using spent nuclear fuel in space. I doubt that we're ever going to move spent nuclear fuel into space. So what I was talking more as a system that would work here on the Earth. But if you do have any other reactor besides a fast reactor will produce what we call nuclear waste. And some of even the advanced reactors now do a light water system that will produce more waste. All I'm saying is we should probably think about using that waste beneficially instead of burying it. And it's been 40 years since the government's trying to do it, and they still haven't figured it out yet. So my opinion is turn it over to private industry and let them do what they were going to do 50 years ago before the government decided they'd get in the business. And so, but I'm just saying that. But no, I don't think they're going to take spent fuel into space, although if they do use reactors in space, they'll have spent fuel out there. And it might eventually be to a point where they could use those fast reactors to do that. But they take processing and some designs are pretty efficient and pretty slick at that. And we've had prototypes that have done that. So it's not far-fetched.
Spent nuclear fuel is a misnomer. It's really should be called slightly used nuclear fuel.
Slightly used nuclear fuel, exactly right.
It's only 3 to 4% of the fissionable material
Correct.
is actually burned. And I don't think I know of anyone who is a proponent of launching spent or slightly used nuclear fuel into space because it contains fission products.
No, it's not. You're not going to do that. We're not going to do that. But it makes sense to do it here on Earth. And we essentially, if you consider all the what they call the tailings from enriching uranium, they only use 1% of the possible energy in uranium. So there's 100 times more energy sitting in the, like you called, slightly used nuclear fuel, which is actually a much better name for it, than we used in the original light water reactors, which is now supplying 20% of our power in the United States. And people want to get rid of it. It's just unconscionable to me. But
Stephen, have you looked into molten salt?
Yes, absolutely.
Okay, well, they are ideal.
Yep.
For the utilization of slightly used nuclear fuel.
I call that liquid fuel. You just dissolve it in the salt, and it produces power. And you can tolerate the fission products for a long time because it's fast reactor. It's a really elegant solution. Absolutely. So any other questions?
Yes.
By the way, thank you, Stephen.
Oh, thank you, Joseph. Stay with us. Santosh, I think.
Yes, excellent presentation. I'm a big fan of nuclear power, of course, since the days of the Nautilus, thanks to Admiral Rickover and, of course, President Jimmy Carter, who was then a naval officer, one of the first nuclear engineers under him. We have a nuclear Navy now. Our nuclear submarines, Ohio-class ballistic, and LA and Virginia, and Seawolf-class attack submarines, of course, are nuclear-powered aircraft carriers. Nimitz and the Ford CVNs are all powered. So the Navy has done very well with nuclear power, very safely. We've never had an incident. with the nuclear power. But the big concern is since the days of the Convair B-36 nuclear power test project, if what happens if the thing comes back down to the Earth, range safety issues, specifically put on a rocket, so that's what I wanted to ask you about. How are those mitigated? Because that's, I think, is where the public would be concerned with all the great benefits of nuclear power terrestrially, putting it aloft until it exits our atmosphere and or orbit. There is a little bit of apprehension there because things can and do go wrong. And when they do go wrong, oftentimes they'll come crashing back to the Earth.
Correct. I think for our applications, at least until it gets into space, I think we can contain the reactor no matter what happens to it. And that's the key. So it doesn't disintegrate in space, and it's not so much chunks of radioactivity, it's the dust that might be taken into the lungs. And of course, the more that gets diluted, the less of a problem it becomes. But you're right, the public is just so afraid of it. I remember when we were launching RTGs out of Cocoa Beach, our teams would go down there. Great duty. We could sit down the beach for 2 weeks, waiting to chase radiation signals from the RTG that might have blown up, but that they never did. So they're well aware of that issue, and they're well aware of the public perception. But my way to combat that is to try to get more education to the public. They just very greatly misunderstand nuclear, and more precisely the danger of radioactivity.
Sure. I think the big issue isn't so much nuclear power itself. People who are proponents and support nuclear power are just concerned about having it go aloft if it ends up crashing back down. That's the big issue. I mean, they're fine with it terrestrially and on ships and submarines and so forth. That's really the way they were concerned, because of the unknown there.
Well, now they're attacking reactors and they're shutting them down before the end of their life, and it's only because of political and business reasons, and I think that's a travesty. So if my approach is to try to get people to understand it better, which is a big job, and I'll need a lot of help. And then the other part of it is if we can if all we need to do is convince one governor to say, I will accept the used nuclear fuel, the slightly used nuclear fuel, into my state, and they can call their shots. Like there's a $45 billion fund in Congress to do nothing but take care of this spent nuclear fuel problem. And if you're a nuclear engineer, this is the simplest part of the entire nuclear power system is the back end, what we call it, the back end. And it's immensely technologically simple compared to the rest of it. So it's a little kind of embarrassing for people like me who are nuclear engineers that we haven't solved that. But much of that is political stuff, which I will say nuclear engineers are probably not very good at dealing with anyway. So how you deal with that as a nation and as a population is a real big issue coming up. But I see nuclear coming back. I don't see wind and solar being the solution. If they were not subsidized now, they wouldn't even be considered. And as power sources, and it's such a low density power source, and it's ludicrous to try to use it as a baseload power source. It never worked. You can talk about batteries, but even if they do figure out the battery situation, they'll be twice as expensive. So right now, you either put a battery system in or you build another fossil fuel plant. You'd probably natural gas, but in Germany, they're building coal plants. So every time you put a solar or a wind farm in, you got to build another power plant to take care of the energy deficit when you don't have wind blowing or sun shining, and there's no other solution to that. And that's what's happening right now. And I'd be glad to talk to anybody for as long as they can listen about that. And I see I have Santosh has a question, looks like. So go ahead, Santosh. Do you have a hand raised?
Oh, yeah, sorry about that. I forgot to.
Okay, no worries.
Thank you for the answer. I appreciate that.
Oh, you had an answer. You already got your answer. Okay.
Yeah,
All right.
I just want to say thank you. Sorry, I forgot to put the hand down. I'm still working the Zoom thing.
Okay, well, if you guys don't have any questions, I'm going to talk about some more stuff.
Oh, I do have a question, Steve.
Okay, go ahead.
You go ahead. because recently there are two news. I want to hear your advice and the view on this. One is the Bill Gates TerraPower, the news on CNBC, the next generation power system, and the other one is Fukushima is releasing the wastewater into the ocean, which caused a lot of eyebrow these days. As you say, the 3 miles Chernobyl, Fukushima really caused a dent in the public reputation, for nuclear power. So how do you rescue, how do you change the public views?
Well, let me take the TerraPower thing first. There's a very elegant design that Bill Gates has put together with a sodium cooled system. And I'll tell you right now why people use sodium. It's dangerous to use among air because it's pyrophoric and you need to use it in an argon system, but it's very easy to use. The advantage is it has very high specific heat, which means it can hold heat for a long, long time. It can deliver heat when you need it. And it also has a low pressure, works at atmospheric pressure. Water has to be very, very high pressure to produce the steam needed at the volume you need it. And the pressure is a huge issue with light water power plants. Well managed over the years, but still it's something to deal with. So that's the two advantages of sodium. And now TerraPower has designed their sodium system to have an extra heat sink so that you can use existing solar and wind to provide heat and heat up the sodium as sort of a battery storage system for making reactors work with wind and solar that's already existing. So that's the TerraPower is a very elegant design, and it's he hasn't got that approved yet. There's only one next generation reactor approved right now, and another one being approved. But I think you'll see that the system for approving them will simplify quite a bit in the future, and we'll start seeing some more come out in the next 5 to 6 years that can actually sell. In fact, the market for them right now is overseas. All Poland and Hungary and all the Balkan states are all buying reactors. They want to go 100% nuclear, and they want to do it with small modular reactors. So the first ones that can come and give it to them are going to be the winners in the market. And NuScale is the name of the company that has produced the only approved small modular reactor, and they're over there talking to those guys. But Russia is too, and China is too, and South Korea is too. So it's a huge business. Now let me address the Fukushima issue, and I could talk for weeks on this, but I won't. The deal with Fukushima was that they had a tsunami and a tidal wave that killed 19,000 people. Nobody died from the reactor accident, and in fact, the reactor accident that's sitting there is very well contained. I don't know when they're going to take it out of there, but it's not causing any trouble to anybody. Their problem was cooling that reactor because they stopped the fissions instantly, like it was designed to do. But without water cooling it, you have the decay heat coming off of it, and that is enough to melt the fuel itself, which is what actually happened. So right now they're in a very safe situation in Fukushima, and the release of radiation, which actually was the big fear for people there, was maybe on the order of 100 times background. And that is not going to cause, it's not something that you'd want to try to do every day, but you're not going to cause these people as much problem as they think it does. They evacuated an ICU unit because of that radiation and killed 1,600 people because they put them in a high school gym. There's people over there that are advising their kids not to have babies because they think the radiation is so bad. It's just that perception that is so devastating to them. Now, the tritium in the water is, let me explain that. Tritium is an isotope of hydrogen. It has 1 proton and 2 neutrons, so it's called hydrogen 3, H3. So that becomes regular chemical hydrogen, so it attaches itself as one of the hydrogen in water. So it's not like something dissolved in the water that we have to try to get out. All the dissolved particulates in that water are out and way below drinking water standards. In fact, the water with the tritium in it is below drinking water standards. But people are afraid of the tritium. Now, tritium has a very, very low energy beta particle that stops very quickly when it's in the body. it takes a lot of tritium to really be a health issue to people. But when they hear about it, they're worried about it. Now, if they dump that in the ocean has almost an infinite sink for dilution. Okay, so this tritium is going to go in the ocean and get diluted 1,000,000 times to 1 before it ends up in anybody else. It ends up anywhere where somebody would worry about it. So it's really not an issue to do what they're considering doing. In fact, I would encourage they do that, and was kind of surprised they saved up all the billions of gallons they did now. So really, as I can tell you as a health physicist, that I would not worry one bit about that. And I know you heard when this happened, which was 10 years ago, just in March, 10 years ago, people were predicting that there'd be huge radioactive particles on the west coast of the United States. And I know at UNLV, when that happened, they ran a high volume air sampler for 24 hours to capture, and they didn't capture enough particulates to just barely see that they could see it. They could understand it was there at levels that were not actually dangerous at all. So they were way below any kind of danger level. And I think they're handling the situation in Fukushima just fine. But we got a press right now that's picking out the bad stuff and telling everybody. And I'll tell you, be careful what you listen to in the press. Things I know about that they hear in the press are vastly overstated. And for what reason, I don't know, and I'm not going to speculate, but they're sensationalizing things that really don't need to be sensationalized, in my opinion. So anyway, just remember, it's part of water. Tritium's in the water. It's a hydrogen that's part of water. You need a lot of tritium to cause you trouble, and there's none of that's going to make itself way back in. It's not like if I dissolve cesium or strontium into the water, and then fish got strontium or cesium in them, because water's everywhere. You have water in your body. Fish have water. Everybody uses water. So when they inculcate it in their bodies, they're going to have it so diluted, it's going to just act like other water, and it's not going to be a problem. So go ahead and ask your next question.
Yeah. I'm saying, and this is very exciting, and stay in touch. You work on this topic view things. But I think Alexander has a question.
Sure.
Alexander, go ahead. You can unmute yourself. Yeah, he raised hand. So to see.
Okay.
Well, I mean,
did he write it down, or?
I think it's. Go ahead.
I always tell my mom how we should put radioactive waste into space. And now we can actually do that for reactors.
Well, we talked about that a little bit. It's a dangerous situation, but in space, it's a lot of weight, even though it's very compact, and it just doesn't make any sense to do that. We can handle it very easily down here. Like I said, when you hear about it, you've heard a lot of information on it that's sensationalized. The situation is really well in hand, and where it's stored now is very safe. It's just because the government accepted it and now has no place to put it, it's expensive for taxpayers to keep it there, because the government has to pay the reactor utilities to keep it there. But the tragedy is that they're saying that they need to close reactors before the end of their time. And that's totally wrong, in my opinion. And I don't see any other reason to do it, but because somebody's trying to make points with the population. And it's to me, morally wrong to do that. We got to keep reactors going as long as they can. Some of them are approved to go up to 80 years. So they originally, their original life was 40 years. They got extended to 60 years. And there's 4 or 5 of them that are now approved to go up to 80 years. It's a huge source of power that's very, very cheap. Once you pay off the reactor, which they do after 30 years, now you got 50 years of power that you can. It's relatively free. It's very, very cheap. And most people don't know that the amount of fuel in a reactor is only 4% of the cost of operating a reactor. So you get gas and you get coal, the fuel cost is 80% of the cost of operating a reactor. So over time, you're really saving money using nuclear fuel. And I can tell you that the 3 Mile Island accident that everybody worries about was a perfect example, kind of like Fukushima was, of how a nuclear power accident can happen, but nobody gets hurt. So that's like safety in a car. You want to have a car wreck, you don't care if the car gets hurt, but you want the people to be okay. So they try for safety efforts on that in cars all the time. Same thing with reactors. And 3 Mile Island was a perfect example of that, but got way overblown. And Jimmy Carter ran down there, he knew better. Jimmy Carter knew better because he was a nuclear engineer. And he was the one that said we can't reprocess. So there's a lot of politics involved in all of this. And I would just say people be careful and get the facts, because if it goes the wrong way, you get very disadvantaged as a public. And that's what I'm trying to prevent.
Yeah, exactly. Very important. I think Seth has a question. Seth, go ahead.
Yeah. Hi, Mr. Curtis.
Hi.
You may have spoken about this a little bit earlier. Well, you've sort of been touching on it, but as far as nuclear on the Earth versus nuclear in space, so you think it's necessary for it to become popularized and normalized in everyday culture on Earth before its utilization will be possible in space? Or do you think that nuclear in space will maybe pave the way for increased acceptance of it on Earth?
That's a great question, and I'll try to answer that with some examples. We talked about the nuclear Navy. Nuclear Navy operates 500 reactors all over the seas all the time, okay? And nobody in the public cares one little bit about it. Although it's the same technology that's being used in the light water reactors. So the military now is investing in small modular reactors. They're going to create what they call microgrids with each base, and they're going to develop reactors that can go out in the field and supply power at least 7 years, some of them up to 30 years without being refueled. It's a huge advantage to the military because now they cut down on their convoy requirements, and that's where everybody's dying now, is in the convoys, not in the front lines. So the military is looking at that, and I think they're going to lead the public into small modular reactors over time. But the space, I think, is much like the Navy. The NASA has a great reputation. I don't think people ask a lot of questions about what NASA does or worries about the safety of what NASA does as much as they do the commercial reactor side of it. So if NASA decides that a reactor is important to have, I don't think the public will worry about that as much as they do, unless somebody comes out and tells them that NASA, I mean, the media could tell them that NASA's wrong and they don't know what they're doing, and then maybe the people will believe it, but they haven't so far, and they haven't said that about the Navy. So I think the reputation of the military and NASA has overcome the perception of the public much better than the commercial side of it. And like I said, I think much of it is political because people that don't like it won't even debate it, which is suspicious to me. Does that answer your question?
Yeah, it does. Thank you.
Okay. Well, gosh, I'm almost out of time. I guess if you guys want to hear the rest of the day, I'll talk about it, but there's probably more to do.
Yeah, I know there's way much more. So Steve, please stay in touch. You know, we can give you 90 minutes, 2 hours next time, you know.
Happy to come back next time.
Okay, great. Stay in touch.
you.
We'll learn more from you. Fantastic. Okay. So after this exciting
great presentation.
Yeah, great. Yeah, it is. Thank you. After this very exciting presentation, we actually have two more. Two more. One is very exciting. The next one, Nicole is going to talk about this exciting thing involving young professional. Then we have another Mars Flight VR is ultra exciting. So we'll have more fun. So let's see the next speaker. So Nicole is here. So Miss Nicole Chase is the she worked in the Mayo Clinic as economic pathology data analysis. She is also director of a project of SEDS USA, and she's also an emergency room medical scribe. She has a great passion, you know, for space project. I think here the biology. I think she means that you know at the graduate from the Bowling Green State University and Bachelor of Science in Neuroscience and Bachelor you know in Geography in May 2013, and also with a graduate certificate in GIS Portland State University in 2016. Research-wise, you're interested in the intersection of space and medicine. We are also very interested in this. We have space medicine event all the way, which is very important. Intersection of space and medicine, along with the importance of diversity and the inclusion within both space and medicine, of course, very, very, very good. So they have, you have aspiration to attend a post, so as a master program student in order to prepare to attend medical school. You're also one of the 3 recipients of the Patty Grace Smith Fellowship that was awarded in January 2020. Congratulations. Sorry, I was a little bit because the file used they, so I was a little bit confused. But but this is wonderful, very good resume. So without further ado, let's welcome Nicole for this wonderful presentation.
All right, I'm gonna go ahead and share my screen.
For some reason, your face is also blurred. Are you using the blurring feature of the filter?
Oh, I don't think so. It might just be my connection. My internet connection is,
right.
I think
No
it's
problem.
very volatile right now.
Okay. No problem. Go ahead.
All right. So thanks again for the introduction. I will be talking to you about the importance of the young professional voices in within the space industry. So agenda. What is SEDS? What is SGAC? And then based upon the survey that the survey went out last year, I presented this research a couple other times. So I have it broken down to the demographic related results from the survey, the non-demographic results from the survey, further considerations based upon the results of the survey, and then questions for people to ponder. So what is SEDS? SEDS is Students for the Exploration and Development of Space. Like the introduction mentioned, I am the Director of Projects for SEDS USA. It was founded 40 years ago. It consists of high school, undergraduate, and graduate students from all over the world. I'm part of SEDS USA. I'm from the national organization, but there's a SEDS Canada, there's a UK SEDS, there's a SEDS India, a SEDS Tokyo, a SEDS Brazil. Like we're SEDS is in many different countries, and within those countries, each country has its own set of chapters, high school or collegiate related chapters that all feed up into the national level. So SEDS USA's mission in particular is to have our students, have our student members be empowered to make an impact in space exploration, to develop technical leadership skills based upon the projects that we offer and based upon opportunities that we offer, to enable students to attend space conferences, whether they be industry conferences like Satellite, Ascend, et cetera, or Space Vision, or the Space Fusion Forum, or our flagship conference, which is Space Vision, which is held at a university every single year. This upcoming year, this year it will be at Rice University. They are scheduled for it to be in person, by the way. That could obviously change, but it is scheduled to be in person. And also to encourage students to enter their careers, whether they be going into the industry, in academia, or in the government, with as much preparation as needed in order to ensure that they are successful. So SGAC is the Space Generation Advisory Council. This is a global organization. It was founded as a result of the United Nations Conference. Think of SGAC as kind of like an offshoot of the UN. It isn't, but think of it as that, in that because it is a global space organization, it's made up of people from all over the world. Every single country, every single region of the country, or of the world rather, has its own like delegates that they meet on a couple of times a month to kind of give updates and stuff like that. There's also like, it's very organized. I was a part of it for a couple of years as one of the scholarship chairs. And I'm kind of tangentially involved in it right now. And their mission as well as SED's mission are very similar in nature, but theirs is, like I mentioned, just on a much more global sort of level. So the importance of both, just to honestly, I'm not going to read it to you. You guys can all obviously read, but the importance of both is to essentially give students who are interested, or give students, young professionals who are interested in space, whether it be just from like, I'm an English major, but I really like watching rocket launches, all the way up to I'm an engineering student and I really want to work at space company X or space company Y, and how can I get my foot in the door sort of situation. Both organizations cater to both individuals as well as everywhere in between those two extremes. And as such, this was looking at these two organizations was really pivotal for my research, because I was really curious to see, of the people who were going to take the survey, how many of them were actually, how many of them had either heard of or were part of SEDS or SGAC. So demographic results from the survey. So in total, there was 105 people who attended the survey. As you'll find out, not every single one of those 105 people completed the survey, but that's something I need to take into consideration. 99% of the people, 99 people selected that they were between the ages of 18 and 35. Like I indicated, this age range is used because this is the age range of active SGAC members. I recognize that goes anywhere from, senior in high school all the way through, post-bachelor and graduate and PhD level sort of people. However, I looked at that because A, it's a major demographic of SGAC, and B, it's a major demographic that's used just in like regular ordinary, just in regular reporting. I was really interested to find out that there were other people who weren't in it, were significantly older than 35, in between 60 and 70 years of age, which is really cool. So the bulk of the people who attempted this, who answered this question, identified as a student, and identified student as high school through, doctoral student, if you're in some sort of academic related program, essentially. 55 people indicated that they're involved in the space community in some capacity. And I define space community as someone who is actively involved, either engaging with or following kind of in a like offshoot sort of situation with people in social media who have to do with space. So whether that be engaging in people on space, Twitter, as I have on the slide, or, reading blogs, that sort of thing. 36 people indicated that they hold a leadership position. And I defined that as either within a space-centric organization, whether it be AIAA, SEDS, SGAC, et cetera, or as part of an engineering project, like their senior design project, a rocketry project, so on and so forth. And then 40 people indicated that they currently work within the space industry. So within the space organization, this is the question I was really interested in that I was really interested to know that the bulk of the people who responded to this question were part of SEDS and or SGAC in some sort of capacity. And like I have on the slide, I combine these two groups because it shows the importance of these organizations. And that even though there's such a strong presence, there's still work to be done, because ideally that number should be 100%. So gender identity, I wanted to break it down by other demographic related stuff, because I was just curious to see what the representation was. So unsurprisingly, the bulk were male, and then with female being the second highest majority, and then tertiary genders representing a very small population. Within the location, this was a really interesting response, because I naively assumed that the bulk of the people would be from the United States because I live in America. The bulk of the people who I shared it with also live in America. But I was really surprised to see that I had a pretty global response, to be honest. And I feel like that was a really good representation of the space community as a whole, despite it being a very small amount of individuals. That it wasn't, I mean, yeah, it was United States dominated, but it isn't like heavily dominated in that there's a lot of other countries that are represented and a lot of other voices that are being heard. So one of the questions I asked was like, what do you want to have? What do you do you think the space industry or space community should be changed in any sort of capacity? And I intentionally left it vague because I didn't want to influence their decision by me indicating my own potential preferences or biases or whatever. I wanted to make it as completely like, you know, I wanted to make it as like specific as possible without like going into like any sort of information. So the bulk of the people wanted to see change in the space industry and the space community, which I thought was really cool. It means that people, from that response, I definitely understood that people were really, you know, gung-ho about like they're seeing issues within the space industry and or in the space community that they actively want to see something be changed. With a few other people who indicated that they didn't want to see change or that it was impossible to try, didn't give any sort of justification for why they picked what they picked, unfortunately. So the general idea of what they want to change, and there is a lot more, I'm just generalizing it. A lot of them are not surprising, like relaxing ITAR regulations. That's something that's talked a lot about between people who are in SEDS who aren't who weren't born in the United States and therefore, and who aren't, you know, naturalized citizens. So obviously they have the ITR breathing down their neck, as well as increasing outreach and educational efforts. That was also not surprising to me, as well as the second to last bullet point about ensuring that there's not only an increase in opportunities, but that those opportunities are accessible by everyone, as opposed to just certain groups of individuals, or feeling like maybe there's no way that they can ever apply to opportunity X because they're so far out from like the niche sort of population that opportunity is targeted towards, that there's no way that they would ever think about applying because they would never get it. That sort of mentality, that's unfortunately very prevalent within the space community and in the space industry. So I have indicated the interests that people have, because I wanted to know, like, okay, here's a list of interests that that I have listed with how they relate to the space industry and or the space community. What are you most interested in? I was really interested to see that there was, some of them made a lot of sense, like the settling on the moon and on Mars, like, and rocketry, being some of the highest. But I was really interested that policy was up there, space medicine was up there, research in general was also incredibly high. And then the statistic that I have on the far left side of this slide, that 37 people indicated that they do have support of their interests, within their circles, but 24 people indicated they do not have support, which is a problem because everyone's voices should be, heard, regardless if, they go against if they go against, the grain, so to speak, of the mentality within the space industry and or the space community. So missing out on opportunities. So opportunities were defined as attending space-centered conferences and getting scholarships. So like the Brooke Olins Fellowship and others. Of the 61 people who responded, 48 people indicated that they felt like they were missing out on opportunities. And I kind of alluded to this earlier, but some of them weren't aware of it. Some of them couldn't afford to attend the conference or because of geographic location or just because they're a poor college student, which is understandable. 17 didn't feel like, they probably were dealing with imposter syndrome in some sort of capacity, which is incredibly unfortunate that they didn't even want to try because they knew they were probably going to fail, even though they might not fail, but they didn't even want to try because of the niche sort of people who usually get those sort of opportunities. This one made me feel really awkward when I read the results, just because there's people that don't feel safe within the industry or within the community. Yes, it's not that many. However, 12 people is 12 way too many. And who's to say that of those 67 people who indicated that they felt safe, that some of them were borderline and didn't want to say that they didn't feel safe because maybe, for whatever reason. which is alarming. The next statistic is definitely the most alarming, that they feel like half of the people who responded to this question don't feel like their voice is being heard, which I really feel like is a major concern, because if the younger generation is supposed to, if the young professionals, 18 to 35-year-olds who are, who made up the bulk of the people who responded to this, to the survey, they're the ones who are going to be in the industry, leading, making decisions, maybe running NASA at some point, running other space organizations, creating their own space organizations, that their voices aren't being heard at this point when they're trying to foster those relationships so they can, eventually become the administrator of NASA, or that they can become the CEO of their own company or of a current space company, and so forth. That how is that going to impact their lives if they're not getting that sort of encouragement and that sort of mentorship, or just like, positive reinforcement, for making sure that they're doing that, if like life affirming sort of things. So like, this is truly what I want to do, but I don't feel like I have the support that I need to actually go out and pursue it. And this kind of is related to the last question, that they feel like the space community, the bulk of the people who respond to this question feel like the space community and the space industry aren't respectful of all ideas and opinions, which kind of goes with the last slide, in that, if they have ideas to, try to change something that maybe is broken about the current state of the space industry and or the space community, that they don't feel like maybe it's even like worth it to even think about doing it, because, no one's going to listen to them. So in the future, make all the questions required, because I did not do that. Make smaller surveys to encourage people to finish it. Doing breakout sessions with space leaders, who are at space companies and who are more experienced, and whatnot, to connect with leaders, so they get an idea of like what's happening more. Looking at like racial breakdown a lot better, because white people dominated the survey. Looking at demographic data, i.e. academic background, what major you are, that sort of thing, because I did not ask anything about the academic background. And I like to argue the point that space is the most interdisciplinary field on the planet, pun intended. And as such, every single major could ideally be very much represented within the space industry, from a job standpoint, just because of just how vast, the industry is. And then finally, looking at what first encouraged people to get into space, whether that be something from their childhood, something from school, maybe it was because they joined a certain organization, or maybe it's just something that was like a thunderstruck sort of situation. Who knows? Every single person is different, because every single response will probably be different, because we're all different. So questions to consider. These are definitely not, they could be rhetorical questions, or they're just questions to kind of get y'all thinking. What experiences influence people to respond the way that they did about feeling safe, and also feeling like they could be encouraged within the space community and in the space industry? How can those who are established within either support young professionals? How can those who feel like they're being left out being made aware of opportunities? Because not everyone, outside of email blasts and social media and stuff like that, there has to be better ways to do that. How do we increase accessibility of educational outreach opportunities, particularly for people who are in certain countries that may not have those sort of opportunities, or, because space is a global opportunity, as like I mentioned with SGAC, how do we make sure that those opportunities are accessible to different people from different backgrounds, as opposed to, just a super niche sort of population like engineering, for instance. And then finally, this is kind of something more for SGAC and SEDS, but how can those two organizations and other organizations that are similar in nature increase their presence even more to reach out to them, so that way they can be made aware and kind of join the space fam, so to speak. And I included some references, and I can answer any questions. I just have my email address and stuff like that, and I can stop sharing so that way I see that there's a lot of chat responses. So I will stop sharing. All right.
It's excellent point. Very, very important. Just a point. AWS has the mentor-mentee link. So you also want to take basis, as a possible resource. And also, what I say earlier this afternoon, Astrobotic speaker actually mentioned that they have 17 jobs opening for their, the way Los Angeles Las Vegas section definitely care about young generation or all people, all the people, all generation, for possible opportunity. That's why some of our events are set up to bring you to meet the CEO or the company leaders. Today we even have a vice president from Virgin Orbit. It's really, we try our best, to do this. And the other thing is we actually had several speakers from Space Generation in the past few years. So we try to engage as many as possible. So there's a great, Nicole speak with us today. And I think Steve want to speak. Steve, go ahead.
Just real quick, Nicole, I get your points, and it's sort of ubiquitous to all of professional organizations that some of the students get left in the dust a little bit. And I'd like to know your ideas about how that could be fixed, and how could more students feel more comfortable within the professional ranks?
Yeah. Honestly, it's kind of just more of just telling students that you don't need to fit the mold. You don't need to fit the stereotype that the space industry has, because you were made to stand out. And I know that's incredibly cliche, but allowing them to kind of, take chances, and for them to, if their passion is truly there, if they truly want to work in space, if they truly want to be an astronaut, if they truly want to do, something within the realm of space, that I would encourage them to, find resources, and being able to know where those resources are and stuff like that. Whether that be like, some sort of curriculum, like some sort of like, global curriculum that everyone who's in a certain age, learns something about like space and like how to broaden their horizons and how to join certain organizations and stuff like that. I don't know, I'm not a policy person, but I feel like there's something that could be done at, the country, at a state, country, or global level that could expose more of space to people, particularly in countries that don't have a space program, or if they do have one, it's very like it's currently being built.
And we just look at things differently at different ages, and you're very young, and looking at it from that perspective, you might have some ideas that some of us older folks might take to heart. That's what I was pushing. But thanks for your answer.
Hello, Seth. I think you make some comment. Do you want to say something, Seth?
Oh yeah, I was just I'm a student right now, so I'm hoping to join SEDS sometime next year. So it was really cool hearing everything that you said. If I had a question, maybe just you talked a bit about students feeling like they aren't qualified enough, or feeling overwhelmed. Do you have any words of encouragement as far as that, or what do you tell students to sort of, or maybe what resources do you recommend
right,
in order to sort of get over those fears?
That it's okay to ask for help. It's okay to, kind of throw your hands up and just scream out into the void. that, you know, your professors are there to answer your questions and stuff like that. And, you know, they might have answers to your questions about how to get involved, and being able to not, most importantly, being able to not like give in, so to speak, to, you know, your inner demons that tell you that you're never gonna, you know, do X or Y because you don't have the GPA, you're not from an affluent background, or so on and so forth. Like that's the most important thing, because that's something that I have done throughout my entire life and I'm currently doing as a potential non-traditional applicant to med school. Just to make sure that they have to make sure that their hope, I guess, isn't squashed by outside forces, essentially. Because if you believe in yourself, you can truly, you know, that's the most important thing. If you believe in yourself, then that's all the motivation that you need in many respects.
Awesome. I appreciate it. Thank you.
Yeah, of course.
I mean, a very, very good point. And that's also the goal for AWA and those Los Angeles Las Vegas section. So is there any more question? You're welcome to keep typing in the Q&A box. And if Nicole is still around and she can type an answer, or we can forward the question to her after the presentation. All right, so I think it's about time. So yeah, thank you, Nicole. This is fantastic, really amazing. Of course. Yeah, we need young people, you know, there's the future, you know, for aerospace. All right, so our next speaker is here. Actually, it's a very, very exciting talk. It's going to be very fun. So Mr. Connor O'Kane is here. So let me pull. Yeah, okay. So he's a game developer and a teacher, originally from Ireland, now living in Melbourne, Australia. He works primarily in simulations and virtual reality, and is also interested in 3D printing. He teaches game design and mixed reality at RMIT University in Melbourne. His most recent release is Mars Flight VR, which is available on stream for all PC VR devices. In this talk, he is going to explain how Mars Flight VR was done, and why he made it, and how game engines can be used to rapidly develop prototypes and simulation of real-world scenarios. Also exciting, I can tell you, Aerostar, they are company game developers. So I think not only from private companies, it's a great importance, and I'm personally so excited about this. Further, let's welcome Mr. Connor first.
Hi, everyone. Let me know if this video is working. I'm going to try to present using the webcam view, because I have a lot of videos in my presentation. So please let me know if you can see this okay. Just type in the chat if it's working. If you set your view to speaker view up here, you should be able to see me. I'll just type in the chat. Yeah, my presentation involves a lot of video, so I thought using the camera overlaid over the presentation will give you a better frame rate.
Yeah, good idea. Yeah, that's right.
If you have any trouble seeing the videos, I'll post a recording on YouTube later so you can see it in more detail. Okay.
Okay, thank you.
All right, so this is Mars Flight VR, simulating the Ingenuity helicopter on Mars, and how can game technology help in aeronautics and astronautics. That's my email address. That's my Twitter if you want to follow me for updates. Thanks to Ken for inviting me. It's a pleasure to be here. I'm going to talk about what is Mars Flight VR and show you what the game looks like, talk about how it's made and why I made it. And then I'm going to show you some of the stuff I'm working on, the research projects I'm working on, which involve using game engines as simulation tools to solve prototyping issues. So yes, as Ken said, I'm actually from Ireland and I now live in Australia. I direct a company called IONormal, where we make game simulations, VR, and augmented reality apps. I work as a researcher at RMIT, and, and I teach games, game development, game design, and 3D graphics. So what is Mars Flight VR? Well, the easiest way for me to explain it is to show you a video so you can see what it looks like. So hopefully this will play okay. If you have trouble seeing it, like I said, I'll put a recording on YouTube, but I'm hoping this will stream at a reasonable frame rate. You can see what's happening. So this is a recreation of Jezero Crater, where Ingenuity is about to fly. It's been delayed, so it hasn't actually flown yet. You take control of the helicopter using an Xbox controller. So you fly it with a gamepad like this, and you wear a VR headset so that you can freely look around and see the landscape. I've recreated the landing site and 35 square kilometers of the surrounding area. I've added gameplay to make the game entertaining to the general public. So the purpose is not solely simulation, but to do some science advocacy and outreach to get the general public interested in Perseverance and Ingenuity. So you have little quests where you take photographs. There are races where you can race around on Mars. There's a first-person view like this where you can fly inside the helicopter view. This is very popular on Earth for people who fly FPV drones or first-person view drones. They like to race drones with a camera mounted on them. And so this simulates that sort of point of view. And as I said, the game covers a lot more terrain than Ingenuity will actually ever see. This view from the top of this hill gives you a nice overview of the whole landscape. So here we see the whole river delta. Perseverance has actually landed way down in the bottom left here and is going to drive over behind that outcrop, which is one of the outcrops of the river delta. But in the game, you can explore much further. So that's what it is. Let's talk about some of the key features. So the landscape is based on the HiRISE digital terrain model. So the HiRISE camera is an instrument aboard Mars Reconnaissance Orbiter, and it's flying over Mars, taking photographs, but it also generates digital terrain models, 3D height maps of the terrain. And this is one of them here on the right. The X is the landing spot for Perseverance. Can you put him as the only person? Yeah, if whoever's in charge of the presentation could mark me as the only speaker, that would be great. Thanks for that comment. The white box there shows the area that's playable in the game. This X is the landing spot, and the rover will actually just travel west from here, so the game allows you to see a lot more. It simulates the correct Martian gravity and atmospheric density, so the helicopter falls at the right rate. There's extremely low drag. Unlike flying on Earth, it's difficult to change directions if you reach a high speed because the drag is so low. And it's in VR, and everything's better in VR. It supports all the PC-based VR headsets, and it's available on Steam. So that's the Valve Index, the HTC Vive, the Windows mixed reality headsets, and the Oculus Rift. Okay, how is it made? So the short answer is it's made with the Unity game engine. There are two main game engines that everybody uses to make games these days, the Unreal Engine and the Unity engine. And in this case, this one is made with Unity. But it didn't just come out of nowhere. So I want to talk about how I developed the skills to make this game and what led to it. So I actually made a science fiction game in 2018 called Ice Caves of Europa, which already had helicopter style physics, but in 2D. So I'll show you a clip of this. So as you can see, Ice Caves Europa was a flying game, but it's locked to 2 dimensions. The camera is locked to a side view. It's a science fiction story where a comet hits Europa and cracks open the ice. And so a rover is sent to explore under the surface to look for life under the ice in Europa. And this hypothetical flying rover is exploring, and you take direct control of it with the gamepad. So I made this in 2018, and towards the end of the project, I started thinking about full helicopter physics. As I had done a two-dimensional physics-based game, I started to think, well, maybe I could take this and develop it into a full helicopter simulator. And so I made this prototype of a VR helicopter simulator to explore some ideas. Let me just turn that off. So here you can see one of my early prototypes. I'm wearing a Dell mixed reality VR headset. I'm using a flight stick to fly it. And so I used this prototype to look at ideas of a virtual cockpit where you're flying an unmanned vehicle, but using VR to look around. And also to explore the ideas of a VR HUD, a heads-up display, or a heads-up display that incorporated depth, that wasn't just a flat display. So you can't see it in the video, obviously, but when you're in VR, the heads-up display is projected on a sphere around you, and you can perceive the depth of it. And it's projected 5 meters in front of you so that your eyes are very relaxed, that you don't have to pull focus to change from looking at the landscape to the heads-up display. And the little dot, you might see the little green dot in the center of the view there. That's your velocity, and it moves forward and backwards in the z-axis to show you how fast you're going. So traditional heads-up displays really only work as a flat surface. But in VR, your HUD can incorporate depth. And so I used the depth of the VR to show you how fast you're going. It's a very intuitive way to show the viewer. And I'm very interested in incorporating user interfaces into VR. I think it's a fascinating area of research. So I had a helicopter simulator. And as you can see from the sky, I was already thinking about putting this on Mars, but I didn't have a specific location in mind. This was just a randomly generated scene. However, in parallel to this, I'm very interested in 3D printing, and I have been 3D printing landscapes and then painting them to look realistic. On the right here is a crater lake in Oregon, and on the left is Valles Marineris on Mars. And these are taken from NASA's public domain height data, which are available to everyone. But I was also printing the high-rise digital terrain models. So these are available for free at this website. University of Arizona maintains the high-rise instrument, and they're beautiful. They're let me just get my large view. So this one, for example, this is the landing site of the Curiosity rover. This is looking at Mount Sharp, and here you can see a riverbed, and Curiosity is driving up towards this right now, and may eventually climb up onto this riverbed soon. So I really enjoy printing these slices of Mars. They make it seem more real, more tangible. They're very good to show to students, to show to other people the topology of Mars. These aren't realistic colors, by the way. These are exaggerated or stretched false colors in the style of the high-rise press release images. Mars isn't really this blue. So I thought, I wonder, could I get a high-rise digital terrain model of the landing site? So when NASA announced that they were going to land at Jezero Crater, I had a look on the high-rise website, and I found they had a very nice digital terrain model of Jezero Crater. And so I thought, well, why not put this in my sim? This seemed like I had a thank you, KH. This seemed like I had many skills all coming together and allowing me to make this thing a knowledge of the high-rise digital terrains, experience in VR, and experience making a helicopter sim. And it seemed like, well, obviously I should make a sim for Ingenuity. However, it's not that easy. It's not that easy. First of all, making the color of the landscape is difficult because the high-rise images are not photographed in RGB color. It has an infrared red and blue filter on the color camera, but also it only takes a very narrow strip of color photo. The instrument is on the Mars Reconnaissance Orbiter orbiting Mars. If any of you remember those old scanners, those old document scanners, which had wheels on them, and you would drag the scanner along a document to scan the text, HiRise's data is a little bit like that. It flies over Mars, looking down, scanning a long, thin strip. And the central color region is very narrow. It's about 1 kilometer wide. So I needed a lot more color. So I couldn't really use the HiRise textures as color. Handheld scanners, that's right. The older members of the audience will remember handheld scanners from before you could photograph everything on your phone. Yes. So I needed to texture 35 square kilometers of landscape realistically, and I didn't have a good photograph to use. So I used procedural mapping techniques. I used a plugin for Unity called Map Magic, which looks at the height map, looks at the concavity and the slope and things like that in the height map, and then automatically paints the texture. So I assembled a collection of textures by photographing rocks on Earth and color correcting them to Mars-like colors. And then I use just some formula, and it uses this node-based network for generating the masks to create the colors. So for example, at a certain slope angle, it paints it with this dark rock. At other slope angles, it detects lighter. And these ripples that you see here are present in the height map. So these are actual sand dunes, which are obviously dynamic. They're probably not in the same place now. And the procedural texturing has picked up the variation in the height and textured them as sand dunes for me. Similarly, the level was too big to place all the rocks manually. So the resolution of the HiRise scan is about 30 centimeters. So features smaller than 0.5 meter are really not visible. They're blurred or they're just not visible. So I had to invent all the small scale rocks. And again, I used procedural scattering techniques to do this. Doing this by hand would be too time consuming. And so what it does is it randomly places rocks on the terrain, but then it does some calculations. So for example, if there's a rock perching on the edge of a cliff, it will simulate it rolling down the hill to the base of the cliff. And then more rocks will gather at the bottom. Wherever there's a large rock, it will simulate erosion and scatter some small rocks around it. So it tries to make a reasonably realistic random rock distribution. I'm looking forward to seeing when the rover gets over here closer to the river delta, what the actual rocks are like. I'm sure they're not the same as mine, but I hope they're similar. Unity has what's called an asset store, where you can buy assets that other people have made to make your game development faster and cheaper. And so I used Map Magic to make this. I used Shader Forge and I used Microsplat. So these little tools saved me months and months of work, and they're not very expensive. They cost under $100 typically, and they save you months of work. So using a game engine like Unreal or Unity allows you to get something done, even as a solo developer. So this project is made entirely by myself in my spare time, and I wouldn't have been able to do it without these tools. So next, why did I make Mars Flight VR? One, personal enjoyment. I wanted to fly around the landing site and explore it in VR before the helicopter got there. No one else had made a helicopter sim. I should mention that my friend Alan Chan had made a very interesting game called Red Rover, where you can drive a rover around on Mars. And it includes VR too. And I contacted Alan and we've become friends because we've discussed the techniques for building Martian landscapes. Alan's game has many more different scenes in it, and it allows you to drive a rover, and it has some, well, hypothetical Mars bases, what a Mars base might look like. You can explore those too. But I specifically was interested in helicopters. So I wanted to fly a helicopter around. And so I really made this game for myself because nobody else was going to make it. Second is science outreach and public engagement. It baffles me constantly why everybody else is not interested in spaceflight. Spaceflight, exploring Mars, exploring the moon, sending probes to Europa and Titan, are the most interesting things I can think of that we should do with our time. And it's strange to me that not everybody else feels the same way. And so I want everyone else to feel the same way. And so making a game like this is a very good way to reach people who weren't interested in the first place. If you make a book or a documentary about Mars, the only people who it's going to reach are people who are already interested in Mars. They're going to buy that or watch that, right? But if you make a video game about something, then you have a much broader audience. The general gaming audience will be interested to try it. And so my hope is that it will reach children. Children really get immersed in VR, and I want them to get excited by, thank you, I'm glad you agree, Oliver. I want children specifically to get excited by visiting Mars and to think of Mars as a real place, not just some alien distant planet that we'll never go, but a real place. And VR is important for that. VR induces a sense of scale and awe that you don't get from a photograph. So when you see a video or even a picture of Mars, it's very easy to go, yes, that's lovely, and then just keep scrolling and not think about going there. But when you see it in VR, you see how far those hills are and how tall they are. And you look up and you see that Mars has clouds. And you look at the sun and you say, oh, the sun is smaller than it should be. That's strange, and it's dimmer. And when you look down, you realize you're up 30 meters in the air and you can see the sand blowing around. It's completely different to a photograph or a video. When you see Mars in VR, it feels like a real place that we could go. And you can imagine astronauts walking around there and exploring it. And it's particularly effective for children. Children have the capacity to completely forget about the real world when they're in VR, which is terrifyingly dangerous if you're a parent, because if you put a VR headset on your kids, they forget about their body and they'll run into a wall and hurt themselves. But my game is played seated. So my game is what's called a seated VR experience. So you sit down, you hold a controller, and you don't run around. So it's a lot safer for kids to play. And I found that VR is extremely effective on children. They lose their sense of self and they become completely in the game. And so that's a very effective way of getting young people interested in space flight, space travel, and Mars. My hope is that after COVID is no longer a problem, that I'll be able to put Mars Flight VR in science galleries and museums so that people who don't have a VR headset at home will be able to fly around Mars and see what Ingenuity saw and take photographs and be amazed by the fact that there's a river delta on Mars and a 4 billion year old lake bed. Most people don't even consider the idea that there were lakes on Mars, never mind river deltas. But to see it and fly around it will change their mind and make them realize this is somewhere we can go. And then lastly, of course, profit. That's a joke. There is no profit in VR video games. VR is a very, very small market at the moment. So in terms of the whole video games market, VR is less than 1%. So less than 1% of people who have a gaming PC have got a VR headset installed. So there's not much money in this. I basically made this in my spare time and funded it myself, although I was helped, and I'm very grateful to the assistance of Film Victoria. So Film Victoria is a government body in the state of Victoria where I live, who fund film, television, and video games. And when I told them I was making this Mars experience, they got right behind it and they gave me a sizable grant, which allowed me to fly to LA and show the game at the Mars Society convention in 2018. And they provided funding for me to promote the game and to make the trailers and things like that. So I'm very grateful to them. Yeah, I'm reading the comments and there's a suggestion that it would be good to get universities to try this. I agree. And so I'm giving the game away for free. So while I have released it on Steam for the general public to buy, if any of you are interested in trying the game or showing it at universities or showing it at a museum, please just contact me and you can get it for free here. So if you type in this web address into your browser, you can fill in the form and download the game for free. And I'm happy to give as many keys as you require for your school or university or museum or anyone who wants to use it for free. So that's Mars Flight VR. So I'm going to move on to, sorry, yes, there's a comment in the chat about doing more demos. And obviously, if this was a real conference and we were face to face, I would ask you to come over to my desk and play Mars Flight VR afterwards. But obviously, with a remote conference, the best we can do is just send you a free demo. Hopefully next year we'll be able to meet up again and you'll be able to play this with me. I'm going to move on. I have a little more. I'm going to move on to talk about game engines in general for simulation and how they can be applied to aerospace, aeronautics, and astronautics, and to talk about some of the research I'm doing at RMIT. So this is just a smaller second part of my presentation, which I hope will be useful to any of you in the audience that are interested in robotics, simulation, remote missions, rocketry, anything like that. So I work as a researcher at RMIT, and I'm working on a project called DIMSIM in collaboration with Rheinmetall, and it stands for Deep Intelligence Machine Simulator. This DIMSIM project is made in the Unreal Engine, and it uses Microsoft AirSim. AirSim is a free expansion, an open source expansion, which works in Unreal and Unity, and it provides you the tools to simulate drones and vehicles very easily. It's specifically designed for training autonomous vehicles and research in autonomous vehicles. And so we are trying to develop, Rheinmetall are trying to develop an autonomous off-road vehicle. Let me show you what I mean by off-road. So this is the Australian Automotive Research Centre, and this is their four-wheel drive test track. And so we want to develop an AI that can navigate a tracked or a multi-wheeled vehicle through landscapes like this, and can take instruction from human operators with hand gestures, can follow humans, and can navigate safely through mud and water and trees and things like this. So this is a much harder challenge than autonomous vehicles on a road. You've got no traffic lights, no street signs, no white lines to follow. And part of the challenge is getting the AI agents to recognize high-risk terrain, in particular mud. You can see here there's a mud pit in this landscape, and there's a water trap here. So our AI agents need to be able to recognize high-risk terrain. And so we use DIMSIM to train them to, DIMSIM to train them to do that. I should stress that this project is a major collaboration between RMIT, Rheinmetall, Queensland University, and CSIRO, and there are many other people working on this. Let me show you that where we're at the moment in DIMSIM. So I'm going to skip to later in this video to show you why we're doing this. We want to train an artificial intelligence to recognize different terrain types. And in order to do that, we show it loads and loads of video of landscapes, and we ask it to guess, what do you think is the tree? What do you think is the grass? What do you think is the mud? And when it provides the answers, we then verify those answers to tell it if it was right or wrong. So this is called reinforcement learning. It improves by reinforcing. So in order to do that, you've got to record real video of off-road landscapes like this. But then you have to annotate the video to mark which area is mud. And so this is, a person has gone through and marked that this is the sky, this is the trees, this is sand, and this is mud. So that when the AI guesses, I think this is grass, we can say, no, you're wrong, that's actually mud. And that reinforces the algorithm, and the next time it runs, it gets better. And this is very time consuming. Obviously, it takes a long time to film this footage. It takes a long time for a person to annotate it, and then we run the reinforcement learning agent to get better. We want to use DIMSIM to generate realistic video footage that's already annotated. And so DIMSIM can do that. So DIMSIM can generate, on the left, you see the realistic view of the forest. And on the right, you see the annotated version where it's marked, this is sky, this is trees, this is grass, and this is sand. And so we can now generate unlimited footage, which has realistic view and annotated view in order to train the AI agents, which saves a lot of time and a lot of money. I'll show you the current state of the simulation. We're particularly interested in realistic mud because filming realistic mud and recognizing realistic mud is very difficult, but it's also a high priority because vehicles tend to get stuck in the mud. So we've recreated that site that I showed you in Unreal as realistically as possible, with the mud and the correct trees and the correct rocks. And then we're using this to generate videos to train the AI. We use photogrammetry assets, which are real objects photographed from multiple angles and then converted into 3D meshes to make extremely realistic props. So you can see the logs on the left and the trees. These are all based on real trees which have been scanned into the game engine. And they're crunched down to a lower polygon count so that they're nice and fast. But as you can see, the lighting in Unreal Engine is absolutely beautiful. one of the reasons we chose Unreal for this project is because of its high quality lighting engine and its rendering. We can change the time of day. We can render the same scene at multiple times of day. And that's important because the shadows often trick the AI agents. The shadows are confusing for the AI. It has to know that this change in color is due to a shadow or lighting change. It's not due to a surface change. And the only way for it to learn that is by repeatedly running over multiple videos. So that's one of the projects I've been working on at RMIT. That one's called DimSim. Another project or a smaller tool that I've developed recently is a LiDAR visualization tool. Many of you that work in autonomous vehicles or remote sensing are probably familiar with LiDAR. It's laser range finding. A device shoots out a laser beam, and where the reflection is detected, you measure the time that it took, and you can detect how far away it is. And so a LiDAR lets you build up a three-dimensional image of where you are. The specific LiDAR that's being used on this project looks like this. It's the Velodyne VLP16, and it's mounted on a rotating platform. You notice they're offset at 45 degrees and rotating. And so this tool that I've developed allows us to simulate the returns from LiDAR at different rates, different positions on the vehicle, different speeds of the vehicle, that kind of thing. So let me explain what we're seeing here. This bottom area is the forward view from the vehicle. And the top area is a top-down view of a sort of a test track where we want to see what kind of LiDAR pattern we will get. And so this tool lets me run the vehicle along a test track and record how many of the LiDAR rays miss because they're shooting up into the sky, or hit the vehicle, which means they were wasted, or hit the terrain and return a green dot. And I've marked the LiDAR returns with green dots here. So we can do things like we can move the LiDAR around. Let me show you. I'm going to skip forward a little bit. So here I'm going to change the speed to 60 kilometers an hour to see what the LiDAR return looks like when the vehicle is moving quickly. You can see in the bottom view exactly what it's seeing. So obviously driving this vehicle at 60 kilometers an hour would be quite risky because it doesn't have a very good view in front. Here I'm going to move the LiDAR to a different location to explore what kind of return would we get if we put it on top of the vehicle in a different angle. And so here's the vehicle that's mounted on, and I'm moving it over to the top and then switching its mount angle from 45 degrees to 10 degrees. And then running the simulation again. And now because this is in a game engine, we get the results straight away. We don't have to click render and wait an hour for the returns. We can see them happening in real time. So you can see the points that the LiDAR is detecting in this point of view. So this tool allows us to test different LiDAR configurations, different types of LiDAR, different angles for mounting on it, all in software without having to do any mechanical prototyping. I'll skip forward a little bit just to show you another type of LiDAR as well. That was a Velodyne LiDAR, and this is a Baraja LiDAR, which is a newer LiDAR that uses a different scanning system. And you'll see it returns a completely different scan style. This LiDAR, instead of sweeping 360 degrees around the vehicle, focuses all of the attention in front in a very narrow, high density point cloud. And you'll see when I run it, the different style of return. And so this one is more like a beam focused in front of the vehicle, which is very good for fast-moving, forward-moving vehicles. And of course, you can always mount it at a different location. You can pause the sim and fly forward. These obstacles out here are supposed to represent a tree or a person or something small. And so we can count how many dots are being detected on small items. That's, you know, at whatever range in the future, in the distance you're interested in, to work out if this LiDAR is effective. You can see the density from this return is almost like it's almost 100% coverage. It's very good. Okay, so in conclusion, Game engines provide a cheap and fast solution for developing simulations. They allow for problem discovery and troubleshooting before the hardware manufacturing stage. So I think this is extremely relevant to aerospace and astronautics, because if you're discovering problems in the hardware stage, if you're firing up your rover or your rocket or your Mars plane, and you're discovering vibrations or unexpected conflicts when you've already built the thing, it's going to be extremely expensive to solve. You're going to have to go back to manufacturing new components. If the sooner you can get your product in a game engine with all the moving parts working together, you can then immediately discover problems that you hadn't anticipated. You'll notice pieces that conflict with each other, pieces that during motion overlap, issues that you hadn't considered because you hadn't been able to move around the thing in real time. And of course, if you integrate VR, you get even more immersion and more ability to detect these problems. So I highly recommend integrating game engine simulations into your product development pipeline, whether it's for rockets or for rovers or whatever systems you're working on. These engines, first of all, they're extremely cheap. Unity and Unreal are free to just download and try. You only have to pay for them if you're making a commercial product. And they're extremely fast. They can render photorealistic graphics in real time. You don't have to wait for your returns. You can see them in real time. Okay, that's all I have today. Thank you all for watching. If you would like to follow what I'm working on, you can follow my Twitter. If you'd like to contact me directly, please email me. And as I said, you can get a free copy of Mars Flight VR. If you have any PC VR headset, it'll run. I'll put that address in the chat so that you can download that. All right, thanks. If you've got any questions, please feel free to post them in the chat. I'll go back to the slide with the download address. There it is.
Yeah, this is really amazing. It's so fantastic. So if you have anybody have any question, you're welcome to raise your hand to be able to speak out or type your question in. I think there's one in Q&A. Can you see it?
Oh, I'll have to switch to that. Let me just find that. Yeah, let me just turn off. Okay, Q&A. Can Mars Flight VR be used on phones or just PC-based VR headsets? At the moment, it's just PC. And the reason for that is because the scene is so big. It's approximately a gigabyte of data to load the entire Jezero crater. So it's not optimized for phones. You need a PC-based VR. I hope eventually to release it on the Oculus Quest, which is a mobile VR platform, but at the moment it's only on PC.
Yeah, I have a very kind of different kind of question. Your company called IO Normal.
Yeah.
Is any meaning for this? What does it mean? IO is the computer IO, or is the Jupiter Moon IO?
It's deliberately ambiguous.
Oh, okay.
Yes, I know that there's the moon of Jupiter. The normal is also a computer graphics term, meaning like the vector pointing away from the surface. But to tell you the truth, I had to register a company name in a hurry because a publisher wanted to sign a contract with me for a game. And so I've always used the name Monorail as an online tag, like a gamer tag when I was playing games online. And IONormal is just an anagram of monorail. So I picked a company name that was deliberately vague and ambiguous. It doesn't mean anything.
Yeah, that's cool. Actually, vague actually is more. It actually bring more attention. People,
it allows the reader to impart their own idea on it. It has many possible meanings. So yeah.
Exactly. I think there's somebody raised hand. Oh, Seth. Let's see. Seth, go ahead.
Yeah, hi. I didn't have a question per se, but I just wanted to say that this is super interesting because at my university right now, I'm doing an academic internship that's almost exactly this thing that you're describing. Sort of, we're working in Unreal Engine and using VR to create this like synthetic data for machine learning. So,
oh, great. Oh, well, please send me an email and we'll get in touch and compare compare homework.
Definitely. Yeah, thank you so much. This is super cool.
We are making a lot of adaptations to AirSim. I don't know if you're using AirSim, but We've pulled a version from GitHub that's pretty stable, but we're very likely to need to make a lot of changes. We're going to write a GPU-based LiDAR, which is much faster than AirSim's CPU or ray tracing LiDAR. Now, I don't know if we'll be able to push that back up onto GitHub because there may be copyright issues, but we will probably give a presentation or a talk or write a paper about how that's done. So get in touch with me if you want to find out about our developments to AirSim and Unreal.
Definitely. Thank you. I will do that for sure.
Thanks.
Yeah, actually, our AIAA Los Angeles Las Vegas sector in the past few years, we have not like what you do to here, but there's some, as you said, there are the aerospace either companies or professors. They're doing some project. This is not their main project, but they do have VR as kind of site demonstration. For example, there was a professor, and of course, he's working with a company. They are trying to demonstrate this universal gateway. It's a gateway, space gateway, but they propose to launch some kind of universal unit, so it can change the internal. It can be medical, can be scientific, or different kind of things. So in that event, they actually demonstrate the VR as kind of demo for their proposal. So the people can stop by wear VR and what's the design of their interior. And there is another company they're working on this. That's actually augmented reality. They can actually put on your hand as if you are doing some kind of training, for space station. That's exactly what you said. So you can see this, and if you look at some aerospace company, they are hiring people, game developer. We don't know exactly what they do. That's their secret, but they post a job.
I mentioned that the market for VR games is very small, but that doesn't mean that VR itself as a technology is small. VR is extremely important in simulation and training. There's an enormous market for VR training. It's a lot cheaper than building physical scenarios. Training in VR is an excellent application. And there are many applications in aerospace and prototyping for VR. So while I think that consumer level VR is still a few years away, I think VR is already extremely important for research and for simulation. As you said, game developer skills translate very well into prototyping and simulation.
Exactly. Yeah, exactly. So actually, when you show this, the drone, the AI, the flying simulation, I think you got a very good point. But I actually want to ask you this because earlier today, our speaker Astrobotic, they're talking about using TRN, terrain range and navigation. That's also used in Mars 2020. So do you picture something, since you mentioned the drone and the AI, do you think that in this game platform, I know for the helicopter, you probably want to, manually drive to have fun, but for this AI thing, is it possible to implement this kind of algorithm or approach into this VR system?
Yeah, our hope is that when we have the AI agent that drives the vehicle well trained, that it won't be able to tell the difference between playing in the simulation and playing in the real world. It will use the same algorithms to choose its path. So if you're trying to develop a rover for Mars or anywhere else, or the moon, and you want it to operate independently so that it just receives the occasional transmission and it's not being manually told every single turn, then running it in a game engine is a great way to get real-time response. So you could download your 3D data of the landing site, bring it into Unreal or Unity, run your simulations through it very quickly to work out what's the optimal path. And then if you know that the rover on the moon is using the same algorithm as the one you have here, then you can be confident it's going to make a good choice. You see, you don't have to babysit it and tell it exactly where to go.
Yeah, exactly. Actually, we've been looking into some kind of VR. Actually, I talked to Alan. Actually, before the pandemic, we were working on a kind of exhibition, calling several companies, to show, kind of showcase for the VR. Hopefully after the pandemic, we even if it's in person, we can do hybrid, so we can ask you to join us, to the demo as well. And it is, as you said, it's a very good tool, for education to reach and that more people know about his power and the usage. It's just and some of the thing you mentioned, I think is kind of like a machine learning, right? You know,
Yes.
the video frying, you can annotation, but I think it's just a term, but it's basically machine learning to train, you know.
Yeah.
Yeah. So it's also a very ultra hot topic these days, you know.
Yes, it is. Yes. All right. Thanks, everybody. I'm gonna make room for the next speaker now.
Oh, there's no next speaker. I mean, the next
that's it?
speaker.
Okay.
Actually, I tell you, the next speaker originally is a student presentation, but he just told us his family diagnosed as COVID-19 positive. So they kind of quarantine. He cannot do anything.
Okay.
So
Right.
you are the last one, the most exciting one.
Thanks very much for having me.
Yeah, one thing about this, it's very good. You use the mode for presentation. Indeed, there's no delay. But one thing is the resolution dropped. I don't know if you realize the resolution dropped a little bit.
Yes. Okay. It's hard for me to know what everybody else can see.
Yeah. We'll post the video. You'll see it. We also noticed from from the University of Southern California, they used to have we used to have event, and they try to do this, but realized their PowerPoint, the resolution was not very high. So in that case, we have to switch them to use the regular presentation, which have better resolution. But in your case, we can understand because it's you're running this video, you need the continuity.
Yeah. Well, I've been recording it from my desktop as well, so I can post the full resolution on YouTube.
Yeah. Because the resolution is a little bit low. Because I think it's kind of
Thanks for letting me know.
Yeah. Okay, great. This is fantastic. So this concludes our today's New Space mini conference, and this was very successful event, and we have seen the booming of the new space activities. You know, so we'll keep follow up on this and get people together. So let's look for the future and stay in touch. Look forward to seeing you next time. So thank you very much again. Highly appreciate. Enjoy the rest of the day and the weekend, and have a wonderful week. Thank you very much.